subquanta or self-similar fragments. Okay, and what I'm saying here is, again, referring back to Ken Shoulders, they consider the metal indefinitely, but then if you overexcite them in a way, they can blow up. And this is going to be very important to the technology and the testimony from the technology, which I am going to be concluding and discussing with respect to this vibrations in the steam room. These traveling subfragments can disrupt matter as they travel. And this is the action of strange radiation. We're going to show a couple of examples of that. I did a lot of the work in the previous presentation on that. So is this a unique finding? The unique finding of Stanislav Adamenko and the team of scientists working there by maybe as much as 6 years in the former Soviet isotopic factory in Ukraine? No, it is not. This is in Matsumoto's paper that was published in Fusion Technology in September 1992. And this was in heavy water, deuterium oxide. And he's got these black spots here. And he's saying figure 1 shows spherically symmetrical traces. So you're just seeing a cross section here, but it's actually spherical with different diameters. These traces were recorded inside the nuclear emulsions so that they can easily be separated from the patches that are produced on the surface of the emulsions during the film developing process. All of the traces consist of 2 regions. The inner region is almost completely black, but the outer black dots are radiatively distributed. This suggests that some radiation and the particles might have come out from the center region. Okay, so you're looking at a slice of a structure that's observed inside emulsions. Now, what do I mean by nuclear emulsions? Takaaki Matsumoto, Dr. Matsumoto was a nuclear radiation monitoring and detection expert, and he was an expert in nuclear, and so he knew what he was looking at. He knew when something was a processing error, film processing error, because sometimes when you develop film, you get these little marks and imperfections on the surface of the film. So that's what he's referring to there. He's saying that this is inside the polymer of the emulsion. Okay. Another one here from September 1992, but in a 1993 paper that I've just put here. Figure 7, a tiny black hole was expected to be generated from the collapse of multiple neutrons. Collapse of multiple neutrons. This is something similar to what is later being discussed in a 2003 paper with Vladimir Vysotsky about the work of Stanislav Adamenko et al. And might be used from massive nuclei as the host metal and the electrolyte. In the case of Matsumoto, he was doing explosive cold fusion using electrolysis. So he had a water type, in this case it was D2O, heavy water, some form of electrolyte, maybe potassium carbonate or potassium hydroxide or something, or sodium hydroxide, and he was electrolyzing that, and sometimes he was causing an explosion. And so he was creating a high short duration transient event. So it's quite similar, but obviously with a much more simple technology to that used at Proton 21 Labs, and observing something similar produced like this. And you can see it really, it's all speckling. You have to imagine that this is a spherical object. So if you cut the emulsion, in half, you would see this in the middle of the emulsion, as well as seeing something almost identical from the top with this kind of radiation coming out here. It says, the evaporation of tiny black holes has been successfully observed in heavy water. Figure 7a, this one here, shows Hawking radiation and the evaporation of tiny black hole, which is similar to the traces observed in the previous experiment with heavy water. Now, what does he mean by Hawking radiation? Hawking, before he died, I think he had something to say about whether he still believed in the event horizon, whatever. What we can see from the video captures from the device, this secondary ion mass spectrometry of Adamenko, is that something was going in, something was being assembled and progressively emitted. And it was energetic particles. And so at the very least, they were observing 433, but the device is not necessarily set up to detect mesons coming out, muons coming out, high-speed electrons, high-speed photons and such. It's there to detect these ions coming out. So it's working in a different way. So he could be right in saying that the material is torn up shoulders. He's saying when it absorbs matter, the energy is released in the form of UV, extreme UV, and soft X-rays up to 2 kilo electron volts in the condensation process, and you can have 1 ion captured per 100,000 electrons. Okay? So one would imagine there's a lot of electrons in here. In the case of Matsumoto, though, he was saying that you are producing what are called icons. Now, what is an icon? An icon is a positron and an electron bound together with a neutrino. Now, if you have a positron and an electron bound together, you have positronium, okay, which is a kind of structure itself. And positronium is bound together. What's it bound together with? I don't know. But in the case of Matsumoto, he's saying a positron and an electron are bound together with this neutrino. And if you can imagine an electron cluster collapsing, apparently, according to Matsumoto's book, which you can get from remoteview.icu, we've got over half of that published now, so you can download it with all the papers in there and his steps to discovery of electronuclear collapse. When this thing is collapsed, it polarizes. Let's say you've just got a proton, the nucleus of protium, a monatomic hydrogen nucleus. As it's compressing the nucleus, it polarizes the proton such that you get an emission of a positron and you get an emission of a neutrino. And so then, if you take your monoatomic hydrogen, which is normally a proton and an electron, and this process goes forward, you then have a neutron in the center, and you have a positron, an electron, and a neutrino. And the positron and the electron and the neutrino become into a bound state, and that forms the iton, which is a neutral particle, okay? And a neutron in the core, which is also neutral. So you have a structure at the very basic level which is able to pass into matter and transmute it. Now, any other nucleus in the periodic table has more neutrons and protons, and in fact, up to calcium 40, like calcium 40 is like 20 neutrons, 20 protons, it's dec alpha, it's half and half, but even then you've got 20 electrons, 20 protons and 20 neutrons. The 20 protons can produce 20 positrons and 20 neutrinos. You end up with these 20 forms a cluster around your 40 neutrons in the core. So any neutrons stay a neutron, and any protons take part in producing the itons, and the itons form the clusters. And it's interesting because Adamenko observed that in some of their experiments, they got emissions of heavy nuclei with 5,000 to 7,000 ANU emitted. 5,000 ANU, and somehow these things are flying out of their experiments and remaining stable long enough for them to interact with other matter. And if you've got 7,000 neutrons interacting with other matter, well, it's going to cause a lot of transmutation, isn't it? If you get electronuclear collapse, where the itonic shell interacts with other matter, is able to collapse further. Now, the itonic mesh, and he said that this is detailed is, and he agreed that what he was doing in 2001, he agreed that essentially they were talking about the same thing, exotic vacuum objects and itonic clusters. But Ken Shoulders was not a theoretician. He said often that he's not into theory. He just described what he saw and could repeat what he saw every day of the week. Okay, whereas there is which is important in science, one might like to say. Okay, so now whether Matsumoto is correct, I don't know, but certainly what he's saying produces something that's neutral and can do the things that were observed by Stanislav Adamenko. Now, Matsumoto didn't stop there. In a paper in 1993, he published this. Figures 7b through 7f, these ones here, shows the typical feature of the black hole. The conic shape material seems to spout energetically from the bottom of the cone, right? So he has these cones here, and you get these structures coming out. And whether this is, he said that you had a white hole and a black hole, and this did this material organization. So here, this is a white hole and a black hole. And so you're actually, rather than looking at top down, these slightly more, these are exploded black holes or something like that. It's in this paper from 1993. But the interesting thing for me is that this particular structure, he's often saying that it synthesizes a lot of carbon, and I've discussed in many presentations why carbon comes out. It's because it's triple alpha. Alpha is the most stable sort of grouping of nucleons, and many synthesized elements become alpha conjugate nuclei. And if you make alpha, it floats away. If you make beryllium 8, it decays to 2,4 alpha, it flows away. That's helium. So the first stable element that comes out of these systems when it's doing electronuclear collapse and electronuclear regeneration is carbon. And so you see these carbon marks on here. Now, this is on the fracture sample from John Hutchison in a presentation called Hutchison Effect Magic Incarnate. In this YouTube link, you can go and see a big discussion about this in relation to Matsumoto. But here's one of these structures in 3 dimensions. So this is caught inside an emulsion or on the surface of an emulsion. This is in 3 dimensions. And the interesting thing is, and I've got the whole thing, and it's almost identical shape. And funnily enough, the actual areas here are almost identical in terms of their positioning. So there must be something very regular in what happens when these things blow up here are diamond. And the strands along the edges are magnesium. And the interesting thing about magnesium is it's double carbon. Okay? So out of our black hole, we have carbon predominantly coming and double carbon on the ridges. Okay? So, and the thing is that these structures produce solitons. These are like donuts of 2 different types. A predominantly north pseudomagnetic monopole and a south magnetic monopole. And in the same presentation, they can produce these flux loops. And so we'll have a north or a south here and a north or a south here, and material is swept between the 2. And at the point of the boundary where they meet, it's like a phallico-soliton, like you have in a swimming pool. There's kind of some disturbance. And things bleed out, and when it's out in here, it's absolutely, you have to go and look at that presentation. It's a much more complicated discussion, but here we have what I believe is the pit created by a black hole that would be in this core here. When they say a black hole, it's a thing it has a vortical structure that goes into it in a pole, and it has a space which it's kind of almost quantum locked into the paramagnetic aluminium. And the magnesium, actually, this has magnesium and aluminium in it, probably. And so you have something that's in this area here, and both magnesium and aluminium are paramagnetic. So we can bind to those nucleus, these structures. So are there other ways of doing this? Well, the surest way to create these structures and the quickest way to kill yourself if you want to get loaded up with transported ions that blow up inside your body is to use a hydrogen. And this is the one of Alexander Shishkin and his colleagues at the science city north of Moscow in Russia. And it's basically an industrial electric motor here. And then inside this structure, it has a series of keyways that are radially arranged, and so you get intense cavitation in there. And this, in a presentation which I'm going to go into here, which is a new type of penetrating radiation. He talks about the other ways that we've created these magnetic monopole-like structures. So I'm going to drop out of this now, and I'm going to go to that presentation for you to look at. So this is the presentation. You can go and look at it on our YouTube channel. You can go and see the original Russian presentation and my translation of it. But this is a new type of penetrating radiation, Alexander Shishkin. This is from October 2018. Okay, so he talks about the fact that this type of high energetic radiation, which is often 120 kiloelectron volts, sort of seemingly when it blows up, and it's much more energetic than characteristic X-rays, were observed by Charles Glover Barkla in the 1910s, and after he won the Nobel Prize in 1970. For discovering characteristic X-rays, he literally spent the rest of his life trying to work out J-rays. When it came to post 1989, many people in the cold fusion field observed these emissions of 120 kiloelectron volts. And in this interview here from 1996 with one Martin Fleischmann, that our project is named after, he talks about these not soft X-rays. If you have got high energy X-rays coming out, and this goes back to Stanislav's back, lots of people say, well, it's soft X-rays, but soft X-rays would never get out of the cells, and so that had to be blah, blah, blah. So essentially, are these coherent X-rays? What do they do? Okay, it is coherent matter, it is these structures. But interestingly, in this with Christian infinite energy, the only question talking about anti-gravity is the only time that it goes Fleischmann, and there's a ... between the two things. And he said they were researching 4 different things at the time that they were doing cold fusion. One was cold fusion, one was the behavior of electrons in metals, including room temperature superconductivity, and another one was blah, 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 we're not going to mention that. And then there was this whole discussion about anti-gravity, which they kind of edited out, it would seem. Anyway, I mentioned this maybe before in the previous presentation, that Simon E. Schnoll published this book, which you can get. It's from studying papers from 1951 to 2008, and it's on physical factors in random processes. And in the conclusion of this book, which, like I say, you can download for free, it's in conclusion, Simon Schnoll argues that all random processes in chemistry, biophysics, physics, including fluctuation of the decay of rates of radioactive elements measured at the same time in the same place, are strictly correlated with each other. Based on this analysis, Schnoll, as well as other researchers, for example, Parkhomov, Baurov, etc., concluded that there exists a certain cosmophysical factor, agent, which actively influences virtually all processes occurring on the Earth and in space. And this here is the relic neutrino flux, which was referred to by Tesla in his 1880s, 1890s work as these infinitesimally small corpuscles that come from the cosmos rather than coming from the star. Anyway, Shishkin calls it magnetotoroelectrical radiation, and he believes that this is the agent. And when he ran these experiments with that cavitator I showed you earlier, he observed these, what they call birdies. And if you can imagine a mushroom sliced in half, this is the structure. I talked about this in my previous presentation. And when some guy analyzed these photographic film plates, he said, well, have you got an iron bombarder? What's going on? Because they saw these pits underneath the birdies in the film. And these microcraters and these birdies, they were able to create in these different ways DG from revolving bodies made of various materials, titanium, cadmium, etc. Now, why is this important? This is important because of people using spinning material to create anti-gravity. I'm saying that these things are relating to shielding of gravity or removing the effects of gravity on other bodies. I'm saying you can aggregate them into large self-similar macroclusters. They will affect all kinds of things that I gave in my previous presentation, like light, like radioactive decay, like the crystallization of metals. Plus, they will also cause forces or a perceived force. And I talked about the work of Xu Wenju from 1988, 1999, and of Maurice Allais, that's on the NASA's website from, I think, 1954, where they observed the focal pendulum, in the case of the latter author, changing during three-body alignments. And in the case of Xu Wenju, he saw a sideways movement in a metal plate during a three-body alignment. And this, I believe, is the pressure form of gravity, and the pressure is created by the superfluid, superconducting condensate that pervades the entire universe, which is relic neutrinos. Anyway, so a spinning body. So you might have another, I think the Tupanov device is a spinning body. Many people refer to spinning bodies. These structures come out of things that you spin quickly. And I've got permission now to translate the work of Alexander Shikin into English, and I will be putting that in the next months or two onto remoteview.icu if you want to follow that work. But he took things as these cones of metals and spanned them at something like 5,000 RPM, and this strange radiation is emitted. Okay. From materials irradiated with gamma radiation. So just shooting gamma radiation at something is able to produce these magnetic monopole-like structures. John Hutchison used some uranite in his experiments. He always had this big lump of uranite. And so that will have cesium-137, one example of a gamma emitter, and that will emit gamma rays. So he had seed structures in order to create these things that could produce his effect. From gamma sources specifically, rather than just from a gamma radiation. So you can create gamma radiation by taking a high-speed electron and passing it through a conversion target, or you can create it from actual gamma sources from the gamma. So cobalt-60 here and 137 cesium. So you would have got these sort of things from Fukushima in abundance. And so the idea that you would have these magnetic monopoles binding to the oxygen, producing the weird glow above Chernobyl, and some weird events Fukushima is not surprising, because you can produce these structures by applying a high voltage pulse of plus or minus 590 volts on an X-ray film in an opaque package. So that's one way of doing it. Corona stream discharge. Okay, so corona. This is very, very important to the technology that I will be discussing. That's relevant with the vibrations in the steam room, because a corona was used, a corona discharge was used in that technology. But of course, the corona stream of discharge is what you get in a Tesla ball. Okay, so a Tesla ball, in theory, if it's at the right energy levels, should produce a quanta of these strange radiation. Okay, and these two generated type of generators, I don't know what they. And essentially, he says with his device, he calculated that 1 hour exposure would damage red blood cells from the number of grays produced, and it would basically red blood cell damage and damage to the genetic material in white blood cells. And so essentially, he's saying that 1 hour exposure to his cavitator would kill a man. And Leclerc and his partner, with their cavitation device that produced every element in the periodic table, they also observed strange radiation tracks away from their device, and they almost killed themselves in a 1 or 2 hour experiment. Okay, so be careful when you're doing these experiments. Weird effects can occur around anti-gravity craft, as well as technology that relies on these phenomena. Things like time distortion, anything that uses a transistor will cease to work very effectively if you get within the event horizon, or within this sort of kind of boundary around the event horizon. You need to be careful with that. Now, there's a note at the end here. Jerzy Bazhatov, who sadly departed, probably because he was exposed to this radiation for too much time, he says that there is a way to protect yourself with a fluoroplastic plate. So, for instance, PTFE or boron. And the thickness of the sheet of glass must be 2 centimeters thick. And other authors like Shoulders and Shishkin are suggesting thin layers of conductor and insulator, saying metallized mylar sheet. I build them out of aluminium and cellophane, alternate layers, and so on. Boron obviously is a neutron absorber, so if you've got something with 5,000 to 7,000 neutrons, it's probably good to have that there. And fluoroplastic, I believe that fluorine is a good fuel for this, and so it causes a bit of a disruption to the things as they're flying through the air, and so that's the way that it interacts with that. Okay, so this is the point that I want to add in here from Shishkin. Now we've been talking about him, that he said in a private conversation to me in 2018. He says, after a while, my cavitator stopped producing strange radiation. In order to get it to produce it again, I had to physically move it to a different part of the lab. After a while, my cavitator stopped producing strange radiation. In order to get it to produce it again, I had to physically move it to a different part of the lab. So, what we know from the work of S.V. Adamenko is we've got something that's locked into the metal. We know from Shoulders that these things can stay in metal indefinitely. We know from, and I've shared this in many presentations, we know from Matsumoto, these structures grew on crystal boundaries and the 8 spherical sections out of the material. This is by John Hutchison as early as 1979. Spherical sections inside a piece of metal were consumed, okay? And we have observed this in our own Vega experiments last year and shared this widely. And we can see the whole process occurring on the macro scale. We showed how it grows in the crystal boundaries and it eats out these sections, does the transmutation, and so forth. And so this is very, very repeatable. But what we have shown in many of our Vega experiments, what Matsumoto showed in 1990 in his paper on his palladium deuterated rods, the material that's eaten in those, and other authors, is that it eats up to an area and it completely stops. Like nothing gets eaten beyond it. It's like a perfect boundary. And we've actually created things in Henk's work where we've got a structure that's 10 millimeters across and it's completely cut copper. It's completely cut copper. Now, if it was a thermal effect, the copper would melt and so on, because it's a very, very conductive, thermally conductive metal. But the fact you have a coherent matter structure, and on the boundary layer, it eats everything, and then outside the boundary layer, it does nothing. This is what I'm talking about. And so if you can imagine that you are producing this clusters in the aluminium in that structure, if we go back to it, so for instance here, we go back here. This is producing an area around it where this flux of relic neutrinos from the cosmos is being sucked in and aggregated into these structures. And Shishkin says, in fact, if I go back to his presentation, I missed that, so let me just go back to his presentation because there's one point we missed here. A string vortex soliton is an ordered vortex structure of cold neutrinos. Since the interaction of string vortex soliton with radioactive isotopes changes the decay characteristics of these isotopes. Okay, so cold neutrinos are the technological equivalent of relic neutrinos, or they could be relic neutrinos. So let's go back to our slide here. So he's saying that this device produces this emission of these string vortex solitons, these neutral black EVOs in the parlance of Ken Shoulders, and that they go into X-ray film. But if he runs it in the same place too long, it stops working. And this was observed by Alexander Parkhomov as well. And so he literally has to get this device and move it physically to another part of his lab and turn it on again for it to start producing the strange radiation on the X-ray film. Okay, so this is consistent with the three-body alignment effects, where you get a sideways pressure, because these things are partially reflected and refracted by solid bodies, and they're gravitationally lensed. They interact with neutrinos with gravity and the weak force, and therefore by proxy with the electrons. And so as it rains down, as for instance, you've got like Betelgeuse shooting out a load of these relic neutrino flux towards, or lensing it towards the sun, and then the sun is lensing that as a lens module towards the moon, and then it's wrapping around the moon. There is stuff coming down which is of a higher density around the outside of the moon, and then on the inside it's getting shadowed. And all life uses this, all random processes use this, all matter use this, okay? And so you've got a higher amount on the outside, and it's pressure gravity. You've got pushing in from the outside. And that's why your Morris Elias in 1954 on the NASA website has a Foucault pendulum that moves out of sync when it's in three-body alignment. And that's why you have this sideways movement on the plane by Xu Wenju. And so you can have, this is the thing about a coherent condensate structure, is you can have two bosons or composite bosons occupying the same space-time, and that is a Bose-Einstein condensate. But you can also have googolplex, okay? You can have a googolplex, and they're still part of the same condensate, okay? They're still acting as one coherent body. But in some places, it's more, and it actually occurs with the Earth and the Sun, because these structures are gravitationally lensed, and you get a neutrino sphere around the Sun, and you get a neutrino sphere around the Earth, okay, where it's denser. And the reason things germinate in certain parts of the month, the reason why seeds like to germinate in the spring is because nature knows that the side of the Earth that's in its spring is going into a denser flux of relic neutrinos. The same condensate, but there's a denser flux, and all life is using it to transmute elements to do work within it. Okay, and this is some of the work from Simon Schnoll. And so we know we can absorb this stuff. And so if we're shielding it with the moon, we get a sideways movement. And if we're capturing it by having a spinning body, which can include a reentrant jet from a cavitating bubble, you are going to be aggregating these things from the environment. There's going to be a lower amount of them inside here, and there's going to be a higher amount of them outside, and you're going to get diffusion from the outside to the inside. Now, these things don't see normal matter like you or I. They don't see things like normal gases do. So when you have a vacuum vessel, there's always these things moving in and out, like it doesn't care how good your vacuum is, it's going in and out. Now, if you have an electrical discharge in a vacuum, and maybe a magnetic pinch, pulsed pinch on there, like the Barchaev devices, it's going to be condensing these structures, these relic neutrinos, in there, okay? And then there's going to be a depletion in the environment around it, and therefore, after a period of time, there won't be sufficient to produce these relic condensates, these key structures for forming the exotic vacuum optics, for forming the ectons, for forming all these different names that different authors have given exactly the same thing, because they think they've discovered it first. And so this, for me, here is probably the most important comment I've got today, but it's definitely not the last. You may or may not be happy to hear that, because we're going to get on to the actual point. This is the background. So I want to say it again. After a while, my cavitator stopped producing strange radiation. In order to get it to produce it again, I had to physically move it to a different part of the lab.
Okay, and this can explain why certain people's low-energy nuclear reaction experiments don't work in certain parts of the Earth, even in the same time of year, or sometimes only work in the spring, or sometimes only work in phases of the moon, because there is a different flux of relic neutrinos, and the parameter space in their particular experiment might not be flexible enough to continue working with a lower flux. They might need a higher flux to initiate, because you have to get these clusters to a certain strength before you can get an electronuclear collapse. That is why you want to be technologically producing these, and that's the whole book with that's the whole point about relativistic discharges, disruptive discharges like Tesla used the disruptive discharge generator. Cavitation is incredibly intense energy, highly localized, and so you get these incredible temperatures. Anything over 1,000 degrees, matter colliding together will synthesize cold relic neutrinos and antineutrinos that can start clustering to form these processes. So cavitation is almost the fastest way to do this. Okay, so I'm now coming to the work of Suhas Ralkar. He was trying to mill off-the-shelf particles to produce an energy generator, and he was trying to get them down to a target size of 5 microns. After milling process, he would desiccate these and grade them to 5 microns or less. The resulting particles would be placed into reactor cores, and then he used greater than 1 megahertz vibration of these particles in corona discharge. Remember what I said about corona discharge? We've got vibration here, we've got corona discharge, we've got something that was cavitating, and we've got metal particles. Note what he said here. In his reactor, if he didn't corona discharge but caused a spark, the core would blow up. It would blow up. So, cavitation of metal in water, this makes the charges, the magnetic charges, via cavitation and resonant modes. What am I talking about, resonant modes? Well, I think probably the best way to talk about that is cymatics. I don't really need to go into cymatics. You all know what I'm talking about, okay? And so it almost doesn't matter what your structure of your plate is. It will set up some resonant modes. Now, these things, this is a key point. So let's look at this structure here. These things like to live on a surface. So they like to form in surface boundaries. But if you add sound, then, for instance, if you've got iron or you have aluminium, for instance, you want to make an anti-gravity device using aluminium plates, okay, and you're using discharges, which produces static electricity, which gives you a lot of charge separation, and then you're spinning those plates, which are going to allow you to get towards producing these clusters. And then you are vibrating it. What you're doing is these magnetic monopole, pseudo-monopole structures that are bound to the paramagnetic aluminium are bounced, and they're bounced. And they form on the antinodes where there's no bouncing going on. Now, we've done this every day of the week in a $35 experiment. You can go and find out how to do. A 5-year-old can do it, and it's called Ultra. You use a ultrasonic domestic cleaner for you can get it off Amazon, have it delivered in a couple of days, and you can transmute elements using aluminium and water and sound. Okay, you get the cavitation, you get the charge separation, and you get the resonant modes, and the resonant modes appear almost instantaneously. We've caught it all on camera, and it's all shared, and you synthesize elements. And it's because you get this, in my view, these charge clusters forming, and you get the charge separation, the intense energy localization, the resonant energy localization at the nodes and antinodes, and you then get this aggregation, and you get these intense magnetic vortices and soliton pairs, Faraday-soliton structures. And this is what is going on. If you have an aluminium plate and you're spinning it, and then you have magnets on there, the magnets will do this. They will create vortex pairs. They will create induction effects. And the vortex pairs, because the relic neutrinos have a magnetic component to them, they will condense in these structures. And so you have you've got the sound creating an assistance to the self-organization, and you have the magnets also helping with the self-organization, because in the aluminium, it's forming these eddy currents. The eddy currents have a vortical center, so you have another means of aggregating these around the edge. And this produces a cluster that gets bigger and bigger and bigger. You cannot see it. You cannot see it because it's moving material in the ether. It's moving material in the ether. And so this produces a large torus, probably 2 tori, depending on what you're doing. And this will produce a gravity shielding effect. It's preventing the action of gravity on the structure that's inside this structure. But things that you approach these kind of things with will not work. Things like phones, watches, any kind of electronics, because they use the Josephson effect, they use tunneling for transistors to work. This will not work. So electronics will not work around the technology that drives UFOs, okay? And it also messes with consciousness, because our consciousness works with this technology as well, okay? So you will have difficulty having a normal train of thought, and your perception of time will be completely distorted, because this is what causes time. Every random changing processes, the progression of time is counted in the change in the environment around you. If you don't have a change in the environment around you, time didn't happen. So if you remove the thing that causes time, then you can't perceive time. And if you remove the thing through which consciousness and connection to reality can work, then you will not have the ability to think in the same normal way that you do. Okay, so anyway, that was a little aside, but I'm talking about cymatics. I don't need to go into it. There's many different patterns you get, so it almost does not matter which sounds you put in. But what I will say is, if you have higher frequency sound, you have more nodes and antinodes. Okay, so you can even it out. Okay, so let's go back to here. So makes the charges via cavitation and resonant modes. That's the resonant modes I'm talking about. Aggregates via resonant modes. So I'm talking about the fact that you have these magnetic structures. They are able to move to the area of least movement, which is the antinodes in your cymatics. And it stores aggregate particles. So once you've got them to a certain cluster size, they become attracted to anything paramagnetic. So in terms of a gas, oxygen is incredibly paramagnetic. It's bizarrely paramagnetic compared to all of the elements, all the way up to something like of the paramagnetic element. And so this is why you've got those weird glows above Chernobyl, because it changes the spectral bands, just as Xuan Zhu observed during 3-body alignments, because he has a different density of the relic neutrino condensate. Okay, so stores the aggregates in metals, and we know we can store it in metals because you've seen it in S.V. Eremenko's work right there, and we know that Ken Shoulders says it can stay in metals indefinitely, and this is what was going on in Suhas Raukar's reactor. Okay, so he then had a foil maker, and this was a fast. He only did this to produce a fast way to make nickel foil for part of the electrode, and he pulsed water flow electrical discharge with 19.46 kilohertz sound, and this would have assisted the formation and aggregation of these structures. Plasmoids were found in, and what I've got here is another slide down here, and this is the work of Bogdanovich, and this is a black torus. This black torus here, this is so good at grabbing the light. So the EVOs can be spheres or tori. Okay, this is a tori. So the event horizon on this is real time. This is a plasma flow discharge by Bogdanovich at the Moscow National Nuclear Physics Laboratory. So he has water flowing down here onto a metal plate, and he's discharging high voltage through here, and it's producing this plasmoid, which is you've got a plasma glow behind, but it's not being able to get through the torus. So this is an example of this going on, and actually Suhas did this. And here is the thing that produces his, where are we? Am I doing? It's going to, there we go. So he has a plate in here. and it is got water, and the metal plate collects nickel, and it produces this nickel foil, which he actually uses ultrasonics to delaminate as well. And this goes into the reactor. So let me just find, oh dear. The fuel is processed in this. This is PZT, and these are 1.5 kilowatt horns. So you've got 4.5 kilowatts of sound, and it goes into this. All he was doing is he was trying to mill the powders to make them. So he's taking off-the-shelf powders that are not at 5 microns because they're expensive and they're not easy to get in India. But you can get powders of different scales, and the idea was to just mill them and put them in here with a sealed thing. And then he had a cooling channel, and this outer chamber here was for cooling, because there's a lot of it. You've got 4.5 kilowatts of energy going in here. So he was only trying to make it smaller. And the funny thing was, is when we looked at it under the SEM, in almost every case, there were transmutation of elements. So this is the powder that's not processed, and not fully processed, because he's not graded out the different scales. And we found different elements being synthesized in there, like niobium and zirconium that weren't in the original material, and a lot of lead, 57% lead, 14% lead here, 51% lead. So why lead? Because it's the heaviest stable element in the periodic table. So if you're doing this nuclear collapse and you're building elements, you get to lead, and if you go beyond lead, it doesn't like to create radioactive elements, so it comes back to lead. So you end up building more lead. And if you pushed it harder, you would start to produce things that were unpleasant. You don't want them. That's what Adamenko did, and that's what Leclerc did. Okay. And here we've got, what have we got? Again, more lead, niobium. So those are the sort of things that he was producing. On the foil, we were getting things like gold, 31% in this little band area here. This is where the plasmoid came in and collided with the metal. And so we've got gold here and palladium here. And so we observed gold in the first couple of slides with the work of Adamenko. And here we've got it being produced in a nickel system. And we have these other elements, but also it produced this structure, which is in my view, with lots of other data that we've had since, this is a collapsed coherent traveling matter wave. And you can see the torus here, you can see the colloidal, you've got a toroidal motion here, and you've got a colloidal motion here. So this is one part of the overall structure here. And this was by weight, 94 points of silver in this reactor. So this is one particular coherent matter traveling wave. Okay, so this is synthesizing elements. Now, what was he doing? This is the actual reactor to maybe give you a better idea of what's going on. It's going to do it. So you've got the metal going backwards and forwards. This is vibrated with your. It has a discharge of 200 volts, and it was at 300 kilohertz. Okay, so not only was he doing plasma flow discharge, like the Moscow Nuclear Physics Laboratory, producing those large plasmoids, he was also using ultrasonics. Okay, and then this foil and the powder goes into his reactor tubes here. So the foil gets scrunched up into a ball. It's a very simple construction. Scrunched up into a ball. You have your powder here, and you have an ultrasonic horn, which is actually at 1 megahertz. It's the thoriated electrode here. That's why do you have thorium? Because it lowers the work function. That is the ability for the electrode to emit electrons. And it penetrates, so the tip just comes through the nickel foil. So the nickel foil actually here is just to provide a conductor, a large size conductor, to allow for corona discharge. And is an initiator. Now, if it gets a spark between here and here, then this ceramic tube blows up. Why? Well, I've already discussed this in many presentations, but when you have the material condensed into the electron condensate, all the electrons, let's say there are 10 to the 23 electrons in a particular structure, which is much smaller than they would ordinarily then you blow this with a discharge. The coherent electrons then return to their normal electron charge. So you've got, let's say, 10 trillion electrons, right? But they're all acting with 1 minus charge. Okay, you disrupt it with an electrical discharge, and it blows up. And at the point that it starts to dishevel, all of the individual electrons become a -1 charge, and then you have a coulombic repulsion between all of them, and it's incredibly violent. And Ken Shoulders talked about how sadly this can make unbelievable weapons. He said about a 1 cc of fluidized electrons would do a 10 by 10 by 10 meter volume, and basically everyone would be completely destroyed. So the point about what's going on in here is his metal is completely loaded with these monopole structures. And what do you want to feed it? Well, you've got hydrogen atmosphere. Let's have a look at the overall reactor here. You've got 8 of these cores around a central tube. You've got a helical water around the outside, and it comes through the center, and it comes out at, let's say, 95 degrees C. We wanted to test this. We didn't want any phase change, okay? And so you have these multiple cores, and then this whole thing is in a hydrogen atmosphere. So it doesn't matter that you haven't sealed these things very well. It's not important. Because you want the hydrogen in there as part of the fuel. On here, a little bit more information. So this is the generator working, and it's producing steam there. It's wet steam, so there's a problem with that. Is this where he gives me some fuel? No. You can go have a look at this. This is on cmet.com and MFMP, and I describe in detail, but I have here the ultrasonic horn that connects to the reactor core. So it's a very simple construction. You have a ceramic tube here. You can imagine you've got your, have I got the diagram here? No, I haven't got the diagram here. You've got the nickel foil through this tube. You have the welding electrode, and in there you have that processed powder. Inside that powder, it is completely loaded, chock full of these magnetic monopole structures, these exotic vacuum objects bound in the metal, like you saw at the beginning of the presentation in S.V. Adamenko's work. How do we know this? Well, because he gave us some fuel. He gave us looking at this in various different ways. This was on this polymer that's on the outside. So I had a magnet here. We know these things can be affected by magnets. So I had a magnet here, a little neodymium magnet, a neodymium magnet here. We had some neutron bubble detectors here. And this was left for a number of weeks. And we had these, whatever's coming out of this fuel, this is not graded and not sifted. So he didn't know that this had strange radiation emitting from it. We just discovered it by getting some fuel, and it came out and it was drawn into the direction of this magnet over here, and we've got this structure on here, and when we looked at it under an Olympus scanning laser microscope, we see the telltale signs of the impacts of strange radiation. There's one track here, and these kind of double pits and group pits of the kind of appropriate scale. One of the reasons I thought to use a magnet in that way was the work of Keith Fredericks, who created these spots and observe these tracks. This is from Matsumoto, this star formation, and this is the similar torus that's rolling along the surface, flipping over end to end, same as you got here in Matsumoto's work. And he actually used a nuclear emulsion like Matsumoto, and he, because Ken Shoulders said that these things can be emitted from your fingertips, that's the easiest way to produce EVOs, he put his fingertips, so if you ever think of going producing sound and sitting in the locus position, creating a vortical structure around yourself from the EVOs that are being emitted from your fingers, then people do that. I always used to think these people are utterly bonkers, but now I know they're not. Find a picture on your wall there, Tim. So you're emitting these EVOs from your fingers, and you've got left hand, right hand, which is exactly what you need to produce the vortical structure around you. So you put his fingers on this film and use this neodymium magnet and produced these different traces. So this is interacting with biology all of the time. Okay, so here is this thing here. Now, I have, so I'm just going to step away to talk about the fall off of these structures. And I've shared this slide with you before, but what we've got going on here is we have two brass plates. This is the cathode, this is the anode. This is caused on which leads to coherence of electrons. That leads to coherent matter. Okay? You then have the coherent matter, the macro ball lightning forming here. When it disrupts and explodes, we have the emission of part of the original structure of the coherent matter structure in the form of a coherent matter traveling wave. And here, if I press play, you can see it flying out of there. Maybe you can see it. So it goes boom. Recently, using computer animation software, I've simulated how this works with toroids and so forth. So we've observed all forms of strange radiation track in 3 dimensions using this type of approach. And here is a undiscussed strange radiation track interacting with aluminium in work from 1990s. This is a dual EVO. When I say dual, it's like a condensate of possible, and I'll talk about this in a separate presentation. It's possibly a singlet electron condensate where you have spin up, spin down, but like a massive singlet state, or it's a positron electron structure in a massive coherent iconic cluster structure in the form of a thing that's much larger than a normal positronium. They can spread apart and they come back together just like a phallico-celaton does in the swimming pool. But down in this bottom side part here, you have this type of strange radiation track where the helical structure of the coherent matter traveling wave is traveling through. And because the binding energy of the electrons and the ions in this coherent matter traveling wave structure is far higher than normal ordinary matter. Normal ordinary matter has no way of being able to resist this. And this is why it makes unbelievably unpleasant weapons. This is why the Hutchison effect did really weird stuff, because ordinary matter cannot deal with this. Okay, so this is what I'm talking about. This structure here has a very defined boundary. And when it goes through this aluminium, which is a highly thermally conductive metal, it's literally cutting it exactly the same shape as the coherent matter traveling wave. Okay? It's not spending long in here, but it's completely removing the material. This is what I'm talking about with an event horizon. Outside of it, it's largely unaffected. Inside of it, it's completely changed. Now, in this particular video, which I've analyzed in detail, this is about 5 frames within, and you can see several coherent matter traveling wave structures going around. This one here is beautiful because you've got the positive and negative structure orbiting around each other. But we've got one that comes up here. It orbits around this one before it even gets there, and it comes over here, and this one comes up here, and it's orbiting around here. This one comes around and bends around, and then this orbits in the other direction. But they're not really interested in where the anode and the cathode are. They're only interested if they come within a certain distance of each other. They literally they go in exactly the direction they want to go in until they look ahead or look behind the structure of another one of these coherent matter traveling waves, in which case they move very intensely. And one presentation where this is very clear, maybe not so clear, but you'll have the slides, is this one, which is of frames where we've got a large plasmoid structure in a reactor. This one that comes out, it comes out here, it goes over to the left, it bounces off the cathode, it gets re-energized, comes round to the right now, comes round to the right, comes round to the right, and then another one is blowing out of the birthing zone over here, and it comes in, and it's doing its own trajectory, and then in one frame, 1/60th of a second frame, it starts to come orbiting around the just come round from the side. So it has no influence. It has no influence in the world. And then you see another one here in purple coming out. It's moving in its own direction. And then it starts to interact with the two that are now nearly perfectly in sync. They're self-cohering. They are self-organizing, coherent matter-traveling waves. Okay? And there's no resonant chamber in here. They're just doing it because they're so influential on each other. And this one comes in and it starts to wrap around this one. And it's wrapped around, and then these three come together. But for whatever reason, these two may have performed a decent, stable structure. But by the time it gets to here, this one has disrupted them, and they kind of wobble out, and they go on their own merry way. But another one down here bounces off the bottom, and then it comes up, and it's hilarious. It comes to here, and then it orbits 180 degrees only around this one's path, and then it starts to follow it. So the influence on each other is phenomenal. The ability and desire for them to collect and organize, but they're organizing at a distance. And this is what Ken Shoulders observed. They form bead chains. Matsumoto observed this as well. We have observed this. Many authors have observed this. And in fact, even if you go back to the original work that was a reference for Ken Shoulders, this is the Lafferty book here. There is a book in this, a page in this book where they actually characterized where cathode spots produce these structures. And this is probably way back in the 60s or 70s. And they produce these parameterized groupings. So you have one on its own, and then you have two that are orbiting, three which are equidistant, 120 degrees, and so forth. And so you can imagine that's like a collision of one of these self-organized structures with the surface. But within them, they have their own substructure, which I've discussed in other presentations. Okay, so why am I talking about this? It's about this aggregation process. And just for some fine detail, this is from Zhigalov, Vladislav Zhigalov, and he looked at one of these birdies that he produced in a laser, using a laser, which was suggested by Lowe in 1973 as a way to cohere matter. You actually use coherent light to cohere other matter. This was suggested in 1973. He used laser into water that had been exposed to sunlight with, or being outside, with 0.4 Tesla magnets underneath it for about 10 days. This actually allows the relic neutrinos to, in my view, aggregate into the oxygen that's dissolved in the water. So the oxygen's paramagnetic. The cooler oxygen is, the more paramagnetic it is. That's why if you have liquid oxygen, it stays between the two magnets, okay? So the cooler it is, the much more paramagnetic it is. But let's say it's just paramagnetic in the water. You've got the relic neutrinos coming down, and you've got the magnets underneath. Now, here's the thing. If ancient people took a magnetite bowl and they put water in it and they put it into the sunshine, that water would be very, very materially different after a period of time, because the oxygen dissolved in the water would be replete with clusters of magnetic monopoles. All water is not the same. It's absolutely not the same. Cavitation running down a stream, crashing against a shore, working its way through cracks from underground, whether it's volcanic or pressure related through rainfall and so forth and springs. Any cavitation will synthesize through cavitation, through this process, fresh bioavailable dust. This is why it likes to live near streams, likes to live near the sea. It doesn't like to drink someone else's water, ideally, because biology will absorb this stuff. But water exposed to the sun in a petri dish, in a sealed vial, and then exposed to a laser, produces these structures on film. And when you look at the outside of these structures, and I believe these are also similar to the macro structure. This is an aggregate of aggregates of aggregates of aggregates of aggregates of aggregates of aggregates. Okay, and these things can scale. And the pseudo-north monopoles like to join the pseudo-north monopoles, and the pseudo-south monopoles like to join the pseudo-south monopoles. What do I mean by that? If you can imagine this is a mushroom, okay, this is like a primer fields bowl, or more specifically, like the Boyd-Bushman directional magnetic beam pattern by Lockheed Martin, which when he was working at Lockheed Martin, and it produces a magnetic beam of either south or north energy, depending on the arrangement of the magnets around the other other 5 sides of a cube in the basic configuration. But this is more like a primer fields bowl, where you've got lots of magnetic monopole structures or things that have a magnetic beam pointing into it. This intense magnetic beam here, in my view, is the disruption beam in the Podolsky work, which causes material to blend into other materials in the same fashion as the John Hutchison work. So, like I say, spinning bodies will produce these things. Electrical discharge will produce these things. Cavitation will produce these things. Okay, so lastly, I have my steam. So this is a steam in my city here in BurnEye, and I'm going to use a phrase here as I drink my fake Soviet cola here, because they didn't get Coca-Cola over here, so they invented this thing called Cola. Do you bring Muhammad to the mountain or the mountain to Muhammad? In the case of S.V. Adamenko, he was bringing the Muhammad to the mountain. He was taking the thing that needed to be cohered and transformed to the mountain, which was in the accretion plate in his experiments. Okay, that's not going anywhere. It's stuck there in the landscape of the accretion plate, and he's shooting the ions into it. It's kind of like the realization I had was, what is so important in Suhas Ralkar's technology that he has to have this ultrasonics here, moving these particles around, okay? And then you've got a corona discharge, okay? Well, what is a corona discharge? Well, you've got ions and electrons forming, okay? What did I say these structures need? They need ions and electrons. This is exactly, with all certainty, you can possibly imagine, by the claim of S.V. Adamenko in that accretion disk. They feed on ions and electrons. Okay, Scholder said, what do you do to keep an exotic vacuum object alive? You feed it electrons. Okay, all right. And if you don't feed it enough electrons, they die. But they will reside indefinitely in metals. He has metal powders in here with absolutely replete structures. We saw it shredding polymer, and we caught them on a web camera, the one that I'm looking to you on now. In fact, I can show you that. We're nearly at the end, you'll probably be pleased to know, in a different thing. So this is a side view. So you've got the ultrasonic horns and the reactors here, the water on the outside, the water on the inside. Let's see where I did the strange radiation analysis. Give me just a second. Nearly there, honest. Maybe it's way up. Oh, here. So this is what his fuel did to a plastic container after just a few days. It's just, well, I don't know why, but I put my unprocessed fuel into a container and it shreds them to pieces. And he literally lifted this one that was on the shelf behind him off the shelf, and as he moved it around, the whole thing just fell apart. It wasn't in this state when he started to hand it to me. It was quite funny. So then I decided that I thought, well, okay, maybe that's producing some strange radiation, so maybe we should look at it. And so you can see this macro photography. So these are the stars of Matsumoto, and what these are showing, and you've got the helical, sorry, the toroid running over each other. It produces like these train tracks. And here's a star, and the the structures coming up. This is a blowing up macro cluster that's here, blowing up macro cluster here, and it shreds these two lines side by side. It's literally shredding the polymer. There's some closer, different macro. Here's some nice shots here. There's the train tracks here. So you can go and have a look at this. So this is this little container here. It's so destructive, and the energy in these things. And I don't know. I think SV Adamenko found these were large numbers of giga-electron volts, each one of these structures. So I then used Cosmic Ray Finder, and I put PTFE here. This was because it was just something to cut out the light. And little did I know, and later find out, that fluorine and carbon are good fuel for strange radiation, i.e. exotic vacuum objects in dark mode. And so you had them coming out here. They were excited by this PTFE tape, and they came into the structure, and I think we have a number of traces there, but they're not the best, so we'll go to the next one, which is up here. I changed the orientation so it had a longer run through it, and it shifted over time to here. And this is my favorite trace. And the reason this is my favorite trace, because it exactly lines up with one that was found in the first Lion that we looked at, the first Lion reactor, the actual geometry of the trace. And this shows the structure of where it's moving. And so this was determined from the pixel size on the detector. So this is not three-body interactions. This is not a piece of grit between two things making a trace as it rolls around. This is something that came out of that reactor, out of that fuel, after an exotic vacuum object destabilized and blew up, a macro cluster. And a fragment came out. It went through the polymer, it went through the air, it went through another piece of polymer, it went through the air, it went through many layers of PTFE, it went through the plastic on the front, through the IR filter, and through the lens, and into the CD, leaving this track. It's incredibly energetic, and it must be neutral. And this is it overlaid onto the Lion track here at same scale. And interestingly, I didn't have to rotate the actual track. So you've got the monopole structures here, but you've actually got the excitation of the CCD. Okay, so why am I? So we know 100% that it was emitting strange radiation. In fact, we observed it on X-rays and so forth. But I think observing it using a CCD is probably the most interesting of the findings. So back to our thing here. So why was he using ultrasonics? Or why did it work? Well, it's a case of he needs to feed these things with as much of ions and electrons as possible. And in the reactor, he has absolute buckets of ions and electrons because he has this corona discharge here. Okay? But what we have shown is that there is this incredible event horizon where everything happens when you cross the event horizon. Everything happens when you cross the event horizon. Everything happens when you cross the event horizon. Everything happens when you are crossing an event horizon. And then shooting ions into the center, by having this vibrate, you are moving the particles, which are all over the surface, covered with these, what look like, if you were to be able to see them, they look like solar prominences. You have one pole and another pole, and you have material that's sweeping through in an intense magnetic flux loop. Okay? And that magnetic flux will and produce energy by fusing or fissioning them appropriately to or from heavy elements to light elements, or from light elements to middle of the road elements, somewhere between iron and calcium they tend to end up. And so I was sitting in this steam room about four years ago, and I sat there, and when you're sitting in the steam room, you're getting hot, and you're getting hot over a period of time, and that's called Brownian motion. So that's like our particles sitting at the bottom of an echo reactor, not moving. Okay, they're only getting the electrons and the ions that are getting there by statistical chance of particle interactions through Brownian motion. And going on in the Adam experiment, even less is occurring. But if then vibrate my hand as I did a couple of years ago, like that, what you find is, and you can go and experiment with this yourself to have a very visceral connection with what's going on, your hand gets a lot hotter because all these water molecules in the air that had a lot higher energy than the temperature of your hand collide with your hand and share energy. What that taught me is I am adding more of these molecules to my hand. And this is what's happening. It's like wind chill factor. It is like being on a motorbike with a helmet off and going on an icy road. If you stand on the motorbike, you're pretty okay. You've got hairs on your face and stuff, right? You're not so cold. But if you get on the motorbike and you go at 70 miles an hour, believe me, your face starts to freeze pretty darn quickly, okay? This is what's going on in the reactor. You need to make these structures. And in conclusion, I'm just gonna kill my presentation here. Okay, so can you see my mugshot, my ugly mugshot?
Yeah, and I still have you spotlighted too. So
okay, fine. Okay, so you need to make these structures like on this Hutchison sample here. You will have the structures growing on the grain boundaries as reference last year, and we can observe it on Hutchison sample, and they build up on the all these grain boundaries. In iron, you get them to build up inside the material, they will produce intense magnetic poles because they lock. In aluminium, they can move around and jiggle. So you'll get one mate moving, grow here, and another one going here, but if they're too big enough, and if they're the same pole, they'll come together. So it goes. Right? But iron, okay. So as you get this building and you're building, they stay locked in place, and they're locked so hard to the iron that new ones that are formed jump onto each other. So you get an aggregation of norths and souths, bigger and bigger and bigger and bigger, until if you have two norths that are growing and growing and growing, they will then literally tear the sample apart. It literally goes because you have an intense north and an intense north. So you end up with a sample that has two norths. Okay? Now, when George was talking about all of these different systems producing the same effect, and probably it was John having some interaction with it. There's two things that he's saying which are correct. Yes, if you're electrically static, sensitive, right? Some people can't, right? There's a certain level of field that you can sense. And you will know better when it's going to occur. But he also used an AM radio. And in the previous presentation, I showed you that when you get an electron macrocluster disheveled, and the electrons that were formerly in a condensate state blow up, they then return to the state of normal electrons. They form a colonic repulsion, which is instantaneous, and that produces a scalar wave. That gets picked up on AM waves as broadband AM and gets you the pop. So he used two tricks. He used the fact that he's sensitive to electrostatics, and he used the fact that he's listening for those pops. And it doesn't happen immediately. You have to have patience, because if you haven't got things set up, you will not get the clusters forming very quickly. If you haven't got the parameters right, they will not form quickly. He had a high intensity discharge xenon tube. That is absolutely perfect for producing loads and loads of these loads, and you guide them to the sample area. They aggregate in the sample area. But he also sometimes used traveling waveguides, and he also used sometimes some uranite. As I said, it was always in presence. Uranite by itself will be producing these things, right? And you need to aggregate them and guide them to the active area. Once they are there at a sufficient intensity, they will lock into place. With aluminium, they move around, like I said, on the ground, and they tend to stay in place and grow in situ. Okay. And you could use sound, actually, to improve it. And I talked about how you would use sound, and I talked about this before the Salvatore patents were released, that you would use a technique that was developed in the 1950s to use a piezo material to convert high-frequency magnetron output, say 10 megagigacycles or whatever they call it, 10 gigahertz or whatever it's on, and you convert that into solitons of traveling waves, scalar waves, which are just actual phonons that are of the same distance as the interatomic spacing. And this is specifically said in New Scientist in 1963. This is not patentable, okay? Sorry, Salvatore Pais and the US Navy. This is not patentable. And what this does, it causes these structures, these electron condensates to grow in each other, as we have shown in Vega. They wet together, and that produces superconductivity through the structure. And this is specifically said in the book, which you can download off remoteview.icu by Takaaki Matsumoto. And he said this in 1999. Okay, and he said the structures, and we have demonstrated it in a huge scale using the ball lightning here, and a one ball lightning here, and a one ball lightning here, and they are wetting their electron condensate north-south magnetic monopole structures, pseudo-monopole structures together, and when they are big enough, they wet together, and this is one condensate. This is one electron fluid condensate. Okay, and I will be producing a book of that. That is actually a 5 millimeter by 7 millimeter demonstration of what self-organized plasma can create in other matter by and showing how the magnetic and nuclear transmutations and everything is aligning up. But anyway, my point being is that you can create superconductivity in the metals, and then once you get superconductivity, you have some very, very weird effects going on, like things become transparent. Okay, and I gave an example back in 2017. Maybe I can quickly find the presentation if I.
Yeah, and Bob, if I could jump in really quick. So we have 10 minutes left until David is on. We're going to have to skip the Q&A session for today, and that's totally cool. That's totally cool. I just want to let you know.
I don't mind taking questions. I just want to share this.
Oh yeah, no, I just want to let you know we have a hard stop in 10 minutes. So
okay, great. Okay, so let me just see if I got right one here. What's my friend talking about? No, I've lost my thread.
Yeah, I can't thank you enough for. I mean, you have run through so much material today. You know, this is a lot of food for thought. So, maybe if you're open to it, maybe we could postpone Q&A, because I know it's getting late your time. But
no, it's okay. I know. This is from an old presentation, but it's got some useful slides. So let me just switch back to show you my share. Okay. So I think I gave this presentation. So what are you seeing now? I don't know whether you're seeing. What are you seeing?
Yeah, so it's back on your browser and it's showing schema.
Good. Let's go here then. Right, let's find the slide I want to show you. So this is the bead chains by Shoulders. What I'm talking about is this famous experiment by Thunderfoot, where he mixes sodium and potassium in water. And so you have your silvery metallic thing. It becomes black as it interacts with the water, and then it becomes transparent. Now, I believe that this is because you have an electron condensate, or an intense amount of electrons that are interconnecting their wave functions in here, and it's interacting with light in a very materially different way. And then it explodes, and the explanation for the explosion is a Coulombic explosion, although this is an ionic Coulombic explosion rather than this pure electron Coulombic explosion. But this isn't exactly what I'm saying, but what I'm saying is that if you have this going on in the metals may actually become transparent. Okay, so if you had anti-gravity craft using this technology. A number of things. I talked about the fact that it's likely that they will have plasma, and the plasma will grow through several colors from sort of the ionization of nitrogen in the air and oxygen, and then it will go through to UV, so it'll blue shift. It'll go like purple through to yellow. This is my prediction off the top of my head. It would go to a UV blue type look, and then it will start to look transparent. And there's two reasons for that. One is when it's a coherent condensate, the light from behind will bend around the entire structure, like it does around a black hole. And the other thing is the actual metals in there, if they're depending on their metals, will become partially transparent. So you might even be able to see into the craft partially, because of the way that the technology works. This is the transparency thing. So let me go back to so I hope what I've given you food for thought is that when George Hathaway is saying he doesn't know, he has loads of different systems produced it. Over 9 years, Shishkin et al. in Dubna in Science City, 50 kilometers north of Moscow, found that very many systems produce these cleaner condensates, which can start off as electron condensates carrying ions, but they carry ions definitely, and when they interact with materials, they act as if they have neutrinos in them. Okay, they are neutral because they're coming through the water, they're coming through the aluminium, they're traveling over air, and they're going through the sheath of the radio plate, the emulsion, and they are interacting with the silver compound on the impure emulsion. And so you can imagine how these things are clustering, and they can cluster and be produced by a range of things. The simplest way that you can do this and to do nuclear transmutation is to go and buy yourself an ultrasonic, probably around about 43 kilohertz domestic cleaner. They're about, I don't know, the size of a toaster, and they cost about $35. You can get aluminium kitchen foil and high quality or any water, but it's useful to have deionized water. You put it on the underside of a cake box from an old CD stack, and you sonicate it for about 3 minutes, and you find these yin-yang pairs, and in the center of the yin-yang pairs, where the forces are most intense, you get synthesis of elements, and you will see that you have coherent matter, frozen coherent matter traveling waves on other areas of the aluminium as well. It's the simplest way. There's a long history with people like Roger Stringham of synthesizing elements using ultrasonics. And the higher the frequency, the more resonant nodes you have. So Suhas-Ralka in a reactor was having 1 megahertz. So not only the particles lofted into this ion and electron-rich food for the magnetic monopole flux loops, the organization in the whole system is much more superior as well. Okay, and so forth. So this is you in a strong wind, or this is you on a motorbike driving into the wind, or as I said, vibrations in a steam room.
Wonderful, sir. We have 4 minutes left. We have 4 minutes left. So yeah, I don't think we have time for questions. Actually, you know what? Let me do this, and maybe David Chester is with us, so maybe we can start him a couple of minutes early. But let me remove the spotlight there, and what I want to do is I want to put this on gallery mode, and everyone, please give a tremendous for Bob Greener. Bob, that may be our longest straight-through presentation to date. That was amazing. Thank goodness.
It would have been more organized if I'd have had the other 3 hours I thought I was going to have. But it would have been shorter.
I would always love to have you back. So, you know, if you have more to share, or if you want to come back and do a Q&A section, or any along those lines. As you know, guys, I need to put the hands down though, because David is. So we've got a couple of hands, but I'm going to lower those. We're going to have to skip Q&A session today, and I apologize for that. So Bob, again, that was absolutely tremendous. So
it's a very simple concept. You build them, you grow them to a point of where they become active. You store them in metal, and they use the metal as a substrate, and you feed the metal substrate, and it will eat the metals. It will eat the metals, but you kind of want to feed it stuff in a controlled fashion. So.
Wonderful. Okay, well, let me do this then. So I want to, and again, we're about 4 minutes early, but I think in terms of timing, I want to introduce Dr. David Chester. So, Dr. David Chester recently created an in-depth overview of theories more complicated than general relativity, and today he will be discussing those with a focus on gravity and possible applications for gravity modification and engineering. David's career as a physicist includes work on efficient scattering amplitude methods for Yang-Mills theory. His PhD thesis discussed how to compute gravitational radiation confinement diagrams, and he's had a long-term interest in the application of exceptional mathematics to describe gravity beyond standard model physics. David's before. I mean, he is one of the big guns in terms of gravity, and so I'm absolutely pleased to have him here. David, let me see. Let me ask you to unmute, sir.
Hello, everyone.
And thank you for joining us. I cannot thank you enough.
Thank you for the wonderful introduction. Awesome. So I'll try to share my screen. So let me get rid of this. Today I'm going to talk about, I first titled this The Most General Theory of Relativity, but then I realized it's really about the most general theories of relativity. I will try to talk about metric engineering a little bit. I mostly took these slides from another talk and tried to repurpose them, so apologies if its talk is pretty technical, but I did the best I can. So we're going to talk about subsectors of this larger gravity, and basically every theory of gravity I've ever seen fits within this framework, so that's why it's interesting to me. And so there's going to be a lot of technical things going on, so if you're going to get anything out of this talk, I would just say that the main point is that when you refer to gravity, usually people, at least in Einstein's theory, you think of it as curvature, but there's different geometry, and there's three, and all three of these geometries are types forms of gravity. So maybe you've heard a little bit about torsion, maybe you haven't heard of non-metricity before. So if I would just take away anything from this talk, it would be that gravity is really all three of these things in principle, and general relativity only has curvature. So and then basically there's many different theories that you can study with different geometry. Some of them are equivalent to GR, and some of them have better properties such as global conservation laws or quantum behavior. So the motivation for this group here is obviously we're interested in alternative propulsion, and I'll briefly talk about the Alchemy drive a little bit, and another paper that briefly mentioned prospects for warp drive in the context of these complicated theories. And just as a legal disclaimer, this talk will have a lot of mathematics, so I apologize for the technical details. I would like to simplify a lot of these things for this audience, but I give this talk elsewhere and then just repurpose a lot of things. So yeah, once again, the main message is gravity is more than just curvature. And so basically what has been realized fairly recently in the past 3 years is that there's this quote unquote geometrical trinity of gravity. And basically you can have curvature, torsion, and non-metricity. And it turns out there are 3 different theories that have these different geometries. So general relativity has curvature, but it has no torsion and no non-metricity. And obviously the first thing to think is, well, if I use a different geometry, then I would obviously get a different theory, right? Well, it turns out that you can get these different theories that have different geometry yet have the same vacuum dynamics. So metric parallelism is one example. This theory has torsion, but it has no non-metricity, and it has no curvature. And there's also parallelism that has non-metricity. So it's often said that teleparallelism was kind of Einstein's failed theory of gravity, but in present day, there are now two formulations of teleparallelism that are equivalent to GR, which is quite interesting. So metric affine gravity basically is combining curvature, torsion, and non-metricity. And as such, it can contain all three of these equivalents. So if we had this triangle before, you can think about it as the triangle as being inside a cube, where at the corner of the cube, you could have all three. So this was something I was working on about 2018. I was constructing this cube of gravity, and then I was mapping all these different theories. So if you had no curvature, no torsion, and no non-metricity, at least in this cube of, let's call them Einsteinian theories of gravity, you can imagine like there's no gravitation, so that's just special relativity, and that would be at one corner of the cube. And then the cube is in 3 dimensions, and this isn't space or anything. This is just an abstract space of theories. So you can have an axis with curvature, an axis for torsion, and an axis for non-metricity. And basically, since general relativity only has curvature, you could put that at a vertex at one corner of the cube, let's say 1, 0, 0, and the zero metricity. The theory of gravity is basically a triangle corresponding to the different axes of this cube. So the metric teleparallel theory has torsion, and the symmetric teleparallel theory has non-metricity. There's also been this general teleparallel theory that combines both of those. That's been discussed. It's also common to discuss, actually the more common one is the Einstein-Cartan geometry and the Poincare gauge gravity that involves curvature and torsion. That's pretty common, commonly studied. There's also this Riemann-Weyl geometry that combines Riemannian curvature with non-metricity, which was initially introduced by Weyl. And then metric affine gravity is kind of at the other end of special relativity, where it has all three. And so basically, these are theories, but technically I'm referring to the geometries themselves. But then obviously theories exhibit certain geometry. So the scope of all possible theories is actually much more complicated than this. This is just like a first approximation for diving into it. So this cube kind of brings that trinity together and shows more complicated theories as well. So I'll just briefly go through what curvature and torsion is, since there's a nice geometric picture. So the general relativity, you're worrying about transport of objects on some curved manifold. So it becomes difficult to think about how to move vectors around. So if you had different fields, maybe it's a vector field like an electromagnetic field, that's some vector field, and you can imagine maybe you have some electron that's emitting some radiation, and then the electron is moving around on some curved space-time, and you want to figure out how you can transport everything properly. And so one thing that's commonly done is to look at transporting in loops. And so the idea is when you go in a loop, you kind of come back to where you started. So if you kind of go in a loop and something changes, then that you came back to where you started. So that change is something non-trivial. So another way to go around a loop is just to think about first starting at P. You have some vector, and you can represent a vector as a partial derivative. So you have some d sigma, that's just some vector. And then, so if I start at P, I could transport to Q, and then I could transport to R. And I can compare, so I'll end up at some, that d rho will end up somewhere, that vector will end up somewhere, right? But then I could also go from P to S to R and compare where I end up, right? If I go from P to Q to R versus P to S to R, you want to compare the difference of those vectors, right? And so if there's curvature in your space-time, basically when you transport those two vectors and come back to the same spot, if the two vectors are rotated between each other, and you would say that this curvature is associated to the area of that loop. So that helps to give some intuition for how the Riemann curvature tensor is formed. Basically, you have this area, you have the vector you're transporting, and then you have the difference of the vectors after transport. And that helps describe why the Riemann tensor is a 4 tensor, basically because you have 2 indices for the area, 1 index for the initial vector, and 1 index for the difference between the final vectors. So you see that curvature is intimately related to rotation. For torsion, on the other hand, you don't actually need to even think about transporting a vector, but it's a little simpler than that. But what if you went from P to Q, and then you went to Q to R, and let's say you just went in the X direction and the Y direction, right? But then you started at P and you went in the Y direction and then the X direction. If you turned out that you took the same translation vectors and you end up at two different points, which is kind of weird to think about, right? Like if you go left, or if you go right and then up, and then you go up and right, you should end up at the same spot. But if you don't, then that is a characterization of torsion. So you can measure the difference between the 2 points, and basically if that difference is 0, then there's no torsion. And once again, the area is associated with the torsion. So the torsion would be ascribed to this area that you transported around, and basically the change in the final positions gives you another index. So you get this torsion 3 tensor, and we see that it's intimately related to translations because basically you went and transported one way and you ended up in a different spot than you thought. So you'd have to translate to end up where you were aiming for. So this is another type of geometry that you can have. And then there's also non-metricity, which this is the weirdest one. Basically, you don't even need to consider transport on a loop. You just go on an open line. So if you go from P to Q, you can imagine taking 2 arbitrary vectors, A and B, and you can see how their dot product changes as you are transported over an open line interval. So basically, if the dot product changes, then that is a characterization of non-metricity. And that also ends up being a 3 tensor for a slightly different reason than torsion, basically because you have to consider 2 vectors and you're transporting on this open line, which infinitesimally you could go along in the direction of a vector. So that describes non-metricity, and basically it leads to variation in length and angles. So it's pretty bizarre because usually you like to calibrate rulers and say you have this invariant notion of length. So this is probably why you might not have heard of this before, because it's pretty tough, but it can lead to scaling and shearing effects in your geometry. So I figured, since we're going to talk about some concept of energy and warp drive and stuff like that, I figured worth mentioning energy conservation or conservation laws in general, thanks to Emmy Noether. And basically there's this notion that for every symmetry, you get a conserved quantity. So if you want your laws of physics to be invariant over time, if we wake up today or we go to the next day, the theory that we're using shouldn't have to be changed. We want this universal theory that works every day of the week. So that actually defines what energy should be. It's the conserved quantity associated with the laws of physics being invariant over time. Similarly, momentum is conserved because physical laws are constant over space. And you could do a similar thing to talk about angular momentum and rotation. These are local conservation, right? In thermodynamics, you look at heat coming out of a process or something like that, right? You're looking at the local events of what are going on, and you're tracing apart like where the energy goes from here to here in a local sense. And general relativity has some bizarre properties in the fact that you do have local conservation, but the global energy basically is not conserved. One simple way to see this, especially for an expanding universe, is that we assume that there's this constant dark energy density, and then the volume is increasing. So if you have a constant energy density, the total energy is the volume times the density, and if the volume is increasing and the density is constant, the total energy is increasing. And I think there's probably other ways to see this in general relativity without expanding the universe as well, just from looking at the gravitational interactions. But basically, general relativity has a lot of conceptual difficulties associated with it because of this notion of global. It's at a point where maybe 50, 100 years ago, people were more concerned with this, but after a theory becomes popular and is used for a while, people start to get more comfortable with the problems. But it leads to a lot of confusion because people like to think of global energy conservation as being conserved. So I think a lot of the controversies coming out of general relativity, a lot of times they're related to this. They'll think about observers and get confused about if they've been observers look close to something around. There's a lot of different apparent paradoxes that can come out from a misunderstanding of this, but it's not necessarily a problem. But I think it motivates that there could be better formulations that might have a more sensible global energy conservation as well. So I figured to also briefly mention the symmetries because I'm going to mention a bunch of different gauge theories of gravity, and those involve different symmetry groups. So Newtonian dynamics had Galilean symmetry of space, whereas Einstein's relativity introduced time, so it unified space and time, and that generalized the symmetry group to a space-time symmetry, which has Lorentzian symmetry. And so this is just the notation used for the special orthogonal group, which describes rotations. And so basically you can also add the space-time translations themselves, and that leads to Poincare symmetry. So Poincare symmetry is the Lorentz symmetry plus the space-time translations. And just to get a simple idea for what I'm talking about, you can imagine rotating all of space at every location as a global transformation. You rotate everything everywhere, and basically the dynamics shouldn't change. If I change a different frame and I rotate from one frame to another, that shouldn't change. And similarly, these symmetry groups relate to the symmetries of a sphere, right? So if I have SO3, that describes three-dimensional rotations. I have a sphere embedded in 3 dimensions. If I rotate that sphere about any axis, as long as the axis goes through the origin of the sphere, the sphere is going to be invariant. It's going to stay the same. If you rotate a sphere, you can't tell if it changed. So that's this notion of invariance of symmetry. When you change something and then you apply some transformation and no change occurs, then you have a symmetry. But then there's also these local or gauge symmetries. Some examples of these are these unitary groups, which are basically orthogonal groups except with complex numbers instead of real numbers, and this gets used in electrodynamics. So the standard model has some more complicated local gauge symmetry. And so you could also consider, well, what about gauge gravity? Can I gauge the Lorentz group? Can I gauge the Poincare group? So those are studied in various fields, supergravity and string theory, loop quantum gravity, pure gravity community. There's all these different subfields that are looking at various different gauge gravity theories, but a lot of people just theories exist and that they're being explored. And so a local symmetry you could consider, instead of applying a transformation such as a rotation everywhere in space, you could just apply it locally, just at a single point. So if you're at a certain position, you can apply that transformation where you are, rotate. It's not like you're rotating yourself, you're actually changing your coordinates. It's a hard way to visualize, but imagine changing the coordinates such that the coordinates of things only change in some local region instead of everywhere. And that's the basic idea. And invariance, which is basically this idea that you can choose any frame of reference. It doesn't have to be some global transformation between these frames. So you could argue that Einstein really was going for some gauge theory of gravity, but just never quite got there. Maybe he did just some agree with some of his later formulations. So basically, generally has this global Lorentz symmetry, and you can consider gauge theories of gravity, which create this local symmetry. And the idea to think about it is if you can apply a local symmetry, then you can apply a global symmetry, because you can apply that symmetry locally, and you could apply the same local symmetry everywhere in space, which would then lead to some global symmetry. Whereas the global symmetries are, there's more freedom in the local gauge transformations than in the global transformations. So the gauge theories of gravity kind of go beyond, and these are very useful for quantum gravity and also have different properties about the global conservation. So it seems, at least to how well I understand it this far. So I figured I would kind of go through some of the fundamentals of general relativity. Basically, we have this principle of relativity, which is the principle of general covariance, which is saying that the physical laws should be invariant with respect to change of coordinates, as I was saying. So basically, you start considering changes in these inertial frames, basically boosting to constant velocities that led to special relativity, and eventually you could consider accelerated frames, and then it was realized that you had this equivalence principle where basically in this accelerated frame, if you're in free fall, you won't even feel your own weight, so it's basically gravity is indistinguishable from acceleration. information and GR also has this this global symmetry that is associated. Sometimes this is stated as being related to the diffeomorphism invariance. That it's this general linear group. Basically, it's just arbitrary 4x4 matrices that can act on space-time. And so the Lorentz transformations are sub in this GL4R. And this metric affine gravity takes as a gauge group this general linear group and then adds translations to that. And it's a local gauge. Gauge gravity formalism contains curvature, torsion, and non-metricity, and it uses this fairly large gauge group. So, let's stick to general relativity. Basically, okay, so we have this principle, and so you could ask yourself, what is general relativity? Is it the theory or is it the principle? So I think it makes sense to try to bring as much as possible. Sorry for that. And because he did find the first theory that led to the perihelion of Mercury, so that's a good result. And basically, you can argue that the most general theory of maybe Einstein chose a bad name for calling it general relativity. Maybe he had this nice principle, he had a theory, and there's really this more general theory of relativity that could come in the future. And maybe it should contain this local diffeomorphism invariance to truly get that notion of arbitrary frames associated with his principle of general covariance. So at a minimum, you can say that this metric affine gravity formalism has linearized local diffeomorphism transformations. So what I'm talking about today, it's going to seem pretty complicated, and it's just first order. Imagine you could have a linear function, you have a quadratic, cubic, quartic. You could keep going to infinity. I'm just going to talk about linear gauge transformations, and then we're going to see there's a wide range of theories, but really we probably want to go beyond the linear gauge transformations one day, but we got to take it one step at a time. So basically, if quantizing GR fails, then we can still preserve Einstein's legacy and pursue the most general theory of relativity that is still following up on Einstein's philosophy and his principle in some way. And I figured I'd at least throw a shout out to Heaviside because he introduced the first theory of gravity that predicted gravitational waves using Maxwell's equations. But as far as I can tell, if anyone finds a computation that actually gets the perihelion of Mercury correct, I'd like to see it. Hefemenko claimed that it worked, but no, he didn't get it. He didn't calculate it. Maybe there more calculations could be done, but I haven't seen anything. There are a lot of people that claim it can be made to work. I haven't seen it. General relativity at certain position, and basically we can keep on going to these more complicated theories. And another interesting point is that this metric affine gravity theory is actually an elastic theory of gauge gravity. So we're actually imagining this this frame of space-time as this elastic medium. And an elastic medium is basically a fluid, except you have small displacements. So that might relate to the linearity of the gauge group. We're just going to allow for very small deformations and keep things very small in some sense. And so if you want to get all ethereal about it, you could say that this fictitious medium is the ether. And because gauge theory, it's usually stated that the symmetry itself associated with the gauge symmetry is a gauge redundancy, implying that the gauge symmetry is unphysical or not real in some sense. So it's kind of funny to look back on history and think of Einstein removing the ether, but then basically failing to realize that there's all this freedom that you could get from keeping it in, but still pretending that it's not a real thing, but using the mathematics associated with it. And in my opinion, I don't even subscribe to the idea that gauge theory is implying that it's unphysical, but that's kind of the mainstream consensus. So I think it makes sense to at least put this perspective out there, because then you can say you have this ether theory where the ether isn't 50 years later, someone can say, hey, well, there's actually something here. Maybe the ether does exist. Maybe it is physical, but one step at a time. So for this talk, I'll say ether does sort of exist mathematically, but not physically per se. And so we can continue with a little crash course with general relativity, and we can unify space and time into this space-time forward vector. It leads to what's called hyperbolic geometry. It's non-Euclidean because basically this signature associated with time. Even in flat space-time and special relativity, when you start measuring lengths, the time comes in, and the fact that you get a minus sign here and a plus sign here denotes that you have hyperbolic geometry. But in general relativity, it's even more complicated. You get this curved space-time, you get this metric tensor G mu nu. And so this is a generalization of the flat space-time. And yeah, this is a helpful picture for thinking of space-like separated foliation. So you can imagine taking like discrete time slices and then kind of breaking this up in here and then separating space and time again within the framework of general relativity. That's something that's commonly done, especially for quantum gravity and also the Alchemy air drive. So the next thing to look at is after you have this, you have a connection, and this leads to a covariant derivative. So you have derivatives in calculus, right? That tells you about rates of change. You're on this derivative that transforms properly because everything is curved, and you get this connection. It's a pseudo tensor. It's called. It doesn't transform like a tensor. For instance, a tensor has transformation properties associated with the Lorentz transformations, right? So if I have some vector, I can transform it with a Lorentz transformation and bring it from one frame to another. And the values of the vectors will be different in the different frames of reference, but the Lorentz transformations tell it to convert the information from one frame to the other such that we can figure out how to calibrate everything so everyone agrees on what is actually happening. And so when you have curved space-time, you want to make sure you have these vectors and tensors that transform properly. And so basically, anytime you have a derivative, you're going to need this covariant derivative in order to get tensors that transform properly, and that involves this connection. And basically, you can then look at the acceleration of different particles in some curved space-time manifold, and this connection ends up, basically, it's kind of like a force equation. And this is kind of like F equals ma, except in G force. So we're seeing gravity, basically, if the connection vanished, then there would be no gravity. And so the fact that the connection is here, if that was finite, you would get this gravitational fictitious force that would be encapsulated in this term. And then for compatible, which means that it has vanishing non-metricity, you get this non-metricity tensor. That's this 3 tensor that I talked about before that has to do with the variable length of rulers. And in general relativity, in arbitrary theories, the non-metricity tensor is the covariant derivative of the metric tensor, but this vanishes in general relativity. So there's also this notion of torsion, this torsion 3 tensor. You could take this connection here and then generalize the connection of this affine connection. It's the same thing. Just pretend these two are the same thing. And if you just basically subtract 2 of these affine connections and switch 2 of the indices, take this anti-symmetric piece here, you'll find that in general relativity, this torsion tensor will vanish. And what's kind of actually remarkable is the fact that although this affine connection here is not a tensor, this torsion tensor actually is a valid tensor that transforms properly, which is kind of interesting. So yeah, GR basically has curvature, but it doesn't have non-metricity and it doesn't have torsion. So from here, once we have our metric, we have our connection, we can then talk about a curvature tensor. And there's different types. Basically, you can take a combination of derivatives of the affine connection to get the Riemann curvature tensor as a 4 tensor because it has 4 different indices of space-time. But then you can contract 2 of those indices. It's kind of like taking a trace of a matrix. Like if you have a matrix, let's say an n by n matrix, you take a trace, you add up all the elements on the diagonal, and then you just get this single number, this scalar. And so you can generalize that concept to arbitrarily higher tensors. So if you have a 4 tensor, you can contract 2 indices and get this 2 tensor. This is called the Ricci curvature 2 tensor. That's found in Einstein's field equations. And then you can also take another contraction here, and then you get the Ricci curvature scalar, which also appears in Einstein's field equations. And then, so we have this field equation where we're getting curvature, but something has to source that curvature. And so we get this energy momentum stress tensor that is the source. And basically all of matter is formulated in terms of its energy and its momentum and its stress. And from there, that leads to the sourcing of curvature of space-time. So matter is what curves space-time, and then space-time, as it's curved, moves matter. And because this ends up being a differential equation that is nonlinear, you get this it's pretty complicated to work with Einstein's field equations because of the nonlinearity. So sometimes it helps to make approximations where you start where everything is small and you kind of pretend everything's flat, and then you just source a little bit of stuff and you kind of go back and forth. So you see how matter curves space-time, you see how that affects matter, and you can kind of push things to both sides of the equation and get more accurate predictions by doing things in a more simpler way. So in general relativity, there is this Levi-Civita connection. There's all these different types of connections. There's Cartan connections, affine connections, blah, 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 right? Okay, so in general relativity, there is this Levi-Civita connection, which is also called Christoffel-Symbols. They're the same thing. And this is uniquely determined by the metric. So you just take partial derivatives of the metric and contract indices in this way, and you get this Levi-Civita connection. And this is what goes into the covariant derivatives. So this helps describe transport, I was saying, and this is just reiterating the geodesic equation where you get this acceleration term in the fictitious force. And this is just showing the mathematics for the Riemann curvature tensor. Basically take derivatives of the connection, let's say the affine connection. Basically the idea is the affine connection is more general. In general relativity, the affine connection gets reduced to Levi-Civita in some sense, especially in general relativity. So then these terms also appear. This actually, if you have looked at Yang-Mills theory, which is related to all the other forces of nature, this looks very much like Yang-Mills theory. So, everyone talks about how Einstein failed at actually unifying stuff, but, we didn't understand that there were these other forces of nature related to Yang-Mills theory until really right around the year that Einstein died. That was being discovered. So I think if Einstein stayed alive for another couple decades, he would have really figured all of this out. And okay, so we have this Ricci tensor and Ricci scalar as I described. And you get in physics, especially classical physics, well, quantum physics, well, you get this action, which is in terms of the Lagrangian, and this derives all of the dynamics. So you have this action principle that is this principle of least action, which is an optimization procedure where you're considering different paths. You consider a classical solution as a particular path, right? Like we want to predict the future, we specify some initial conditions, and we want to see how the particle evolves through space-time, let's say, right? So we want to consider all possible paths, and then basically you can do these calculus of variations to look at this, and you can get this simple term here. It just involves the Ricci scalar, and this is just some volume of space-time, but since space-time is curved, you have to include this determinant of the metric just to get aspects of that. And then you could add terms for matter, and the Newton's gravitational constant G is encoded in this coupling constant kappa here. And for the most part, you just have this integral over R. So that's pretty much the simplest action you could consider out of curvature. And you can derive that from that action there. And so it turns out that the curvature is two derivatives of the metric tensor. So you get the second order differential wave equation. Basically, second order differential equations are wave equations. So you can get waves coming out of here. And it's worth talking a little bit more about the energy momentum tensor. Blah, blah, blah. You have this action for matter, and you use like metric that describes how matter is encoded. Sorry for the mathematical details, but it's worth pointing out historically, basically, this is called a stress tensor. And it's kind of curious because why are we calling it a stress tensor? Where did this come from in physics? And so as a little quiz question I could ask, well, what was the first theory of physics with a stress tensor? Or what theory discusses the relationship of stress and strain? 5 seconds, while you think about it. Basically, elasticity theory was that theory. And so it's kind of curious looking into it. You hear about the ether maybe as being some elastic medium, but then Einstein banished that, yet we have this stress energy momentum tensor. So mathematically, it does seem like something came along for the ride. So, you could then ask, well, what the heck does elasticity have to do with gravity, right? We have the stress tensor. Where's the strain, right? And basically, that one answer you could ask, you can reply with, is that the symmetric affine gravity theory is relativistic elasticity theory, and then you can actually interpret the metric tensor as being strain, the strain associated with the medium. Strain is basically like the displacements that you apply, so it relates to the physical changes in length that occur from deforming a medium, and then the stress related to the forces required to cause those. That kind of makes a lot of sense now. We have this stress tensor, and that's related to the forces required to cause that strain or the change in the metric or the curvature. So yeah, we got some more math from the theory of elasticity. The basic idea is that you have this position vector x, and then you can deform it with a small displacement. So this and you can do it locally. So at every, you could just imagine a rigid body that can oscillate a little, right? As it's oscillating, you're getting these local displacements of any physical material that you're thinking of. And you could measure the length. You can imagine atoms in a lattice, right? The atoms are oscillating, and you could measure how the length between those atoms are changing over time. And so you could say that basically you get this change in length, which is kind of weird. This is where it starts to look different than general relativity, because general relativity is simpler than the elasticity theory. But this theory is simpler than relativity because it only has space, it has no time. But when you look at the mathematics of the strain tensor, it turns out that basically the idea is this: you have this local displacement as some vector field, and then you have some partial derivative. And another way to write this partial derivative is just instead of d dx you could just write it as del j, that little partial symbol right there. And so here we have mu, which is a 4-dimensional index. This I was meant to be a 3-dimensional index. So general relativity has this gauge-like transformation. It's very funny when you'll read these books, and sometimes everyone knows that GR is not a gauge theory, and then they'll sometimes refer to this as a gauge transformation. And it's like no one really knows what they're talking. Like they just kind of say it. A lot of the experts really do know what they're talking about. There's a lot of really smart people that don't know what's going on here, and it's because you can consider diffeomorphism transformations, and it really is a gauge symmetry, implying that general relativity should be replaced by some gauge gravity theory. But even in general relativity textbooks, you'll see stuff like this sometimes, which looks very similar to the partial derivatives here. You just have a symmetric component indices, and in fact, you won't see this term right here. So in a sense, GR is simpler than the elasticity theory because there's an additional term here. And basically more mathematics. All of the gauge theories use these linear terms, and so this is a second order term. And so we need really complicated mathematics that I'm not going to get into in this talk to actually nail the gauge gravity. I should have put this slide earlier, sorry for this, but this is just a quick sketch of the derivation of Einstein field equations from the Einstein-Hilbert action. Basically, you vary the metric, and then you vary the action with respect to variations of the metric, and you can cleverly get it to pop out. But I'm not going to focus on this in too much detail, but it's actually a fun exercise to go through. And I just wanted to also mention this frame field formulation because this is needed for matter. When you have spin, when you have fermions, like electrons are fermions, and Dirac in 1928 introduced this Dirac equation that used this Dirac spinner. And it's really remarkable. I mean, most people don't even realize that Einstein did this right away in 1928. Most people attribute this frame field formulation to other people, maybe Weil. But it turns out it took until 2011 until it was actually translated. Einstein's paper was translated to English. So, I mean, this is just more evidence to me that Einstein is, he is a genius in the sense that as soon as someone comes out with this new equation for the electron, he immediately figures out the right geometry needed for dealing with that. And this frame field formulation is studied. It's very common in theories beyond general relativity, and the basic idea is that the spin 1/2 Dirac particle is like the action is the differential operator is kind of like a square root of a spin 0 particle. So So Einstein had this idea, well, let me take a square root of the metric tensor, and you get this frame field. So it's called a vierbein or a tetrad in 4 dimensions. Frame field is more universal in arbitrary dimensions. But basically, you can kind of factorize this metric tensor into this frame field times another frame field with different indices, and then you can contract it with this other metric in some other space. So it's common to basically consider curved space-time here, and then imagine this eta AB as some different space-time where everything is flat. You don't have to do that, but you can. Most of the time, people consider this one to be flat. So you can have Minkowski space, and then you can see how this is really like a deformation, right? Like you have flat space-time, and then you're deforming it into this curved space-time, and you can go back and forth. So you have these kind of local indices here and these global indices here. And it can sometimes be convenient to use these indices for the gauge theory. And basically, you have this metric tensor, and you have this affine connection. I'll just point out that in metric affine gravity, it's called that because the metric tensor and the affine connection are independent. So the affine connection also splits apart into this spin connection, this omega here in this frame field. So yeah, you can use these different formulations even within the same theory. So you can have general relativity, and you can either apply the frame field formulation or not. But it seems that you basically need this formulation to deal with spinors in curved spacetime, which we have. So that's helpful. And basically, another formulation you can do, commonly studied with frame fields, is what's called a first order formulation. So in general relativity, you have this action in terms of the curvature tensor, and that depends on the metric, which is 2 derivatives. When you take a first derivative of the metric, you can combine that in different ways to get the connection, and then you can take another round of derivatives. You have some spin connection here. You can take another derivative here to get this curvature tensor. So typically, GR is called a second order formulation because they have those 2 derivatives. But you can kind of replace the metric as being the dynamical field with this affine connection or the spin connection. So you have the spin connection be the dynamical field, and now it's quote unquote first order because you have this Lagrangian. It's the same exact thing. I mean, this is just a metric tensor essentially that's contracting indices. You still have this curvature tensor. It's the same theory, but within the different formulation, you then treat it first order, and then you vary with respect to the connection rather than the metric. And that makes it more like other theories in certain ways, such as Yang-Mills theory. And so, okay, you can have different connections. And the next thing, we're going to transition away from general relativity for a bit. So another common theory is this Einstein-Cartan theory. In that theory, it's the same exact Lagrangian, except now when you go to the first order formulation, we allow for this affine connection. And when you study that, you realize that the affine connection can contain torsion in general. So now I have this Levi-Civita connection plus this contortion tensor, which contains the torsional contributions to the affine connection. And so then you can say, well, I have this larger theory. And if you keep this basically with the affine connection here, you'll get Einstein's field equations. And then you'll get this additional equation where the spin density sources torsion. And what you find there is that the torsion is only inside matter. And it's not even this, you don't even get like a wave equation for the torsion. It's just like, there's no calculus. It's just A equals B. And so whatever the spin density is, that immediately determines the torsion. So in Einstein-Cartan theory, which is ignore the fact that they're actually studying it. They'll pretend it's general relativity when they're actually studying Einstein-Cartan theory. And in this theory, when you have their Dirac fermions coupled with it, wherever there's a spin density, that creates torsion around it. And this is kind of mind-blowing because it's sort of anti-gravitic in a way. I don't know if I would literally say that, but it sort of is anti-gravitic in some sense. And so when you study rotating black holes, if you go into literature and you really dig into the details, you're never going to see them talking about torsion, but there's actually torsion hidden behind the scenes in a lot of these studies. So it's one of those things where it seems like it's heretical. I think one of the main problems with Russians studied it during the Cold War. So there became this polarization around, oh, torsion physics like isn't a good idea. But it's used ubiquitously in string theory. It's used in loop quantum gravity. Well, loop quantum gravity doesn't include matter, but there's a paper that showed you need torsion in Einstein Cartan theory if you want to add matter to loop quantum gravity. So like anyone who's attempting anything in quantum gravity, basically they're struggling because they're forgetting about the torsion. This is just more mathematics about the Lorentz group transformations. Basically, you have the Lorentz group. There's this Poincare group that adds the translations, and the translations, space-time translations, are related to momentum. Momentum is called P sometimes, so that's why they call it P. And then don't worry about this too much. And just to briefly motivate gauge gravity, furthermore, just because you might not hear about it a lot, but basically, supergravity is a gauge theory. That's in string theory. So string theory is a gauge theory. Loop quantum gravity is a gauge theory. Poincare gauge gravity is studied. That's gauge theory. Metric affine gravity is a gauge theory. Geometric algebra, that's this other community. They have their own mathematical way of looking at things, and then they study gravity, and then they get a gauge theory of gravity. General relativity is technically not a gauge theory, but you can break the gauge symmetry and recover general relativity. And so basically, like any in my opinion, any interesting theory of gravity that I've seen in academia that people are studying, a lot of them are gauge theories of gravity. And so you can have all these different gauge groups, different symmetry groups, right? So that SO31 was the special orthogonal group for rotations of space and time, because you have 3 space dimensions and 1 time dimension. And there's this mathematical detail where you use this double cover for spinners. The spinners are spin 1/2, so it's kind of like you have this spin up and spin down that motivates this double cover. They actually have the same algebra, but are technically a different group. And so whenever you see spin P comma Q, it's basically the same thing as SO. And then there's all these different isomorphisms, like these equalities that you can find. So you can consider like special linear transformations over complex numbers for 2x2 matrices. It turns out, coincidentally, that just mathematically is the same thing as this. So then there's all these theories revolving around SL2C. That's very close to the spinners, right? Like the Dirac spinners have 4-component spinners, and those 4-component spinners break into 2-component spinners, where this SL2C will act on that. And then there's also these, maybe you've heard of Asticker variables, that's kind of studied in loop quantum gravity, that uses this complexification of SU2, which also is the same thing, Lorentz group. So 3 different ways to represent the Lorentz group. And then there's also this Poincare gauge gravity that adds the translations. It's kind of cool. You can actually fit the translations into this 5-dimensional rotation group. You can do it with 3,2 or 4,1. And then, some super groups. Who cares about that for the moment? There's conformal gravity. You can take the conformal group, which it turns out that's basically any area preserving situations that increase the scale, but the angles would be preserved, and those are conformal transformations. Those are beyond the Lorentz group, and it turns out you can add like a light cone, like 1 space dimension and 1 time dimension. So, the conformal group of 3 + 1 dimensions is this spin 4,2 group. So you can gauge that symmetry as well, and get conformal gauge gravity, and then it turns out that spin 4,2 is the same thing as SU22. And so, that's it's to complex matrices, and we have this 2-2. I was talking about that 4-component spinner, that Dirac spinner. Basically, Penrose's twisters, maybe you've heard of Penrose's twisters, those are spinners of the conformal group, which now makes a little bit more sense, because the conformal group is basically, it's 4x4 complex matrices acting on this 4-component spinner, or a twister, which is basically the same thing as a massless Dirac spinner. So if you imagine at high energies, if you have a lot of kinetic energy, you can just kind of ignore the mass, and then it makes everything easier when everything's massless, and then you can look at twisters as basically massless Dirac spinners. And then there are these other groups, GL4R and Yang. Of Yang, those theories, a famous physicist studied this theory of gravity that gauged GL4R back in 1974. There was a lot of confusion about it. Most people thought the theory didn't work, but maybe it actually does. And then there's also this affine linear group that adds the translations to the general linear group, as I was saying. So, okay, basically, there's all this amazing work on metric affine gravity. If you add torsion, you can get nice properties for how that relates to spin density, as I was mentioning. and that relates to torsion. And then there's also this interesting work by Poplawski where he found that the photon, when you have it in curved spacetime, it leads to non-metricity. So now we have our curvature for energy, our spin, and our charge for non-metricity, kind of at a high level. Like if you look at a black hole can only have mass, spin, and charge. Maybe that motivates these three different geometries. And there's also this thesis that is quite fun and complicated that presents this unification of the standard model with kind of loop quantum gravity. And they describe how the Higgs mass, the gravitational constant, and the constant, which is absolutely mind-blowing to me. So this is very suggestive for unification. That's why I like this geometry. And you could also look at quantum parallel transport and get into membranes and motivate it from that angle. So I like to think of metric affine gravity as kind of like driving a Ferrari. You know, it's really nice when you got it working nicely, but it's kind of a bitch to get all the maintenance working properly. Who really knows what's going on under the hood? One way to think about it roughly, this might be a slight oversimplification. In general relativity, you typically have this base manifold, and then you consider these tangent vectors, and you consider this tangent bundle, which is a collection of all the tangent planes on the manifold. So you have, and the tangent planes are nice to work with because everything is flat. The collection of separate tangent planes, or you could think of sliding a single tangent plane to different places and describing how maybe the sliding changes the properties there. Or you could look at these affine spaces, and a lot of cases there you'll find that they'll think of something like a sphere as a tangent manifold that's rolling on top of the base manifold. So you have this tangent space as its own manifold that's rolling around the base manifold time. And that's a different construction, different way to visualize what's going on. And finally, this metric affine space combines both of them. And so you can imagine you could have like slipping and rolling. Like if you study classical mechanics, when you study a ball rolling down a hill, it's much easier to just assume there's no slipping, right? And then it makes everything easier. Or you could just say, what if it only slips but doesn't roll? That's a lot simpler. But if you allow for slipping and it's kind of at first glance ambiguous about, well, how much is it going to slip? How much is it going to roll, right? And then if this entire framework is this fictitious medium that doesn't even matter, right? Like it's just this mathematical tool that we're using, we can allow for arbitrary slipping and rolling however we like and maybe find different desirable, maybe it helps mathematically, who knows, right? So maybe these metric affine theories are kind of like the Ferrari of gravitational theories. So this is the best picture I could find of Friedrich Hell. You could see maybe why is he so angry? Well, it's because he did a lot of the pioneering work on metric affine gravity. And basically, you have to ask all these deep questions when you're studying this, like how do we even define length and angle? Like which covariant derivative? Because like you could have the Levi-Civita connection, you have all these connections. So like which connection should I use? Like should I just restrict what Einstein had? Should I add the non-metricity? Should I use both? Should I consider the one Einstein had and then use the total affine connection and use both of those and reconcile something different, right? You have to think about all these things. And then it gets even more complicated. Not only do we have this curvature tensor, this torsion tensor, and this non-metricity tensor, we get different curvature tensors because we can decide, well, like how much of the affine connection do I want to go into the curvature? And so when you start going in the literature, it's very difficult to make any sense of it because everyone is just simple, no one's going to the top of the mountain and seeing what the most general thing is. They're all just trying one thing at a time, and everyone's using different notations. It takes forever to disentangle all this, and this is why it's taking 100 years for us to figure this out. And I'm not even going to mention this final point. There's a million things you could, it really opens the door on a lot of different possibilities for questions you have to ask. So just to kind of break down this format to some other space-time vector, and maybe let's say you multiply by some matrix. Some matrix is something with two components. It's a two tensor, and so you can have these generators of the general linear group as matrix transformations. And then you could imagine translations as just adding something, right? Like if I have space and I just shift everything over by some constant value, then that's just adding something, right? That's what this v mu prime is doing here. And what's kind of remarkable about all in the 5 dimensions, and just think of, oh, sorry, I'm missing a vector here. I should have put, I keep presenting this and keep noticing this and forgetting to fix it. There should be like an X and a 1 here. So this, if this is a 4x4 matrix, this is just like a 4 vector. You can embed the 4x4 matrix and the 4 vector into this 5x5 matrix and then have it act on this 5-dimensional vector that I forgot to write here. And 1, and that would give us our X prime and 1. And then you just throw away the 1. And then you got your 4 dimensions again. See, so now you see like people talking about extra dimensions. Here's a utilization of 5 dimensions. It's just some math trick, right? And so you have this affine linear group. You can break that down to the Poincare group, and that would isolate spin 3,1 and leave the translations. Or you could just remove the translations and get this general linear group, and then both of those contain the Lorentz group. I'm just showing the commutation relations. I'm not going to focus on that too much, but you can work through mathematics for how these you get matrix representations for the generators, and they satisfy certain relations. But yeah, this is basically decomposing. I'll mention this. You have this L as your matrix, your generators for your matrix transformations of the general linear group. You can decompose it into symmetric matrices and anti-symmetric matrices. And it turns out that the anti-symmetric generators are associated with the Lorentz group. Those are what I'm using for the generators of the Lorentz group. And those are used for space-time. And so there's other ways you can break down AL4R as well. I'm not going to go into it in too much detail, but you can also get 3 time dimensions hidden in here in this clever thing that I like to study. So then you can kind of look at the subsectors of metric affine gravity with this affine linear group and start to break it down. And basically you can pull out this Lorentz group and associate it with curvature. And it's understood that the translations naturally relate to torsion. And so basically whatever is left has to be for non-metricity, which is this coset. It's not even a group. It's not even closed. So yeah, if you go in the literature and you look, I'll mention this theory of non-metricity. They don't say what the gauge group is. It'd be nice if someone talked about the gauge transformations of this theory of non-metricity, but they're struggling because they don't even know what group to choose, purely because it's not even a group. It's this coset. You got to take this group and then remove generators out of it, and it doesn't even close. So that's just a little technical detail. And so if you have this affine connection A right here, you could decompose it into the Levi-Civita connection and this contortion tensor and this disformation tensor. More buzzwords. But I tried to show this slide because it does outline a simplicity that I haven't seen anyone write. They're all the same. The structure is the same. Like you have these terms, just one term plus minus, plus minus. The structure of the Levi-Civita connection, the contortion, and the disformation is all the same. It's just that what goes into them is a little bit different. Here, we just have the partial derivatives of the metric that leads to this Levi-Civita connection. This is the torsion tensor. If we combine the torsion with the tensor, non-metricity can cause scaling and shearing, so it can maybe disform things perhaps, and so this is called the disformation tensor. So this kind of at least gives you a little bit of, there are all these tensors, it's a little complicated, but there's at least a little bit of hope in seeing the simplicity that these 3 things all sort of are the same mathematically in some sense. They have similar structure. This affine connection here, and if you study Yang-Mills theory, there's going to be a covariant derivative there, and they'll often write it like this. And this is the matrix formulation of the Yang-Mills theory. So if you had QCD, you'd have 8 gluons and 3 quarks. It turns out you could represent the operators for those gluons as 3x3 matrices, and that I and J would be components of those 3x3 matrices. So this would be like a collection of 3 quarks, a vector of color space, right? And you have this, it's just a vector in space-time with these extra components for the charge. And it turns out that gravity, it looks pretty much like the same thing. The only difference is this is a vector of space-time and this is a vector of, say, color space, right? But so that further motivates, why we might want to go to extra dimensions, because then we could combine space-time with the gauge symmetry associated with the other first and charge, let's say. And it's also remarkable, there's a lot of work in the literature where they're finding ways to compute solutions of gravity, classical gravity, quantum gravity from Yang-Mills theory. But they're still trying to figure out the precise reason for all this, why all this works. And the basic point is we're all trying to figure out, how do we make gravity look like Yang-Mills theory, so we can unify it with this other formulation of gravity that uses differential forms. It kind of removes some of the indices. So if you don't like tensors, it's more math to learn, but the good news is you see less indices here, so that's a little bit simpler, right? And when I was talking about the transport, I mentioned that for curvature, you can transport around a loop and see how the vector space rotates, and that loop is associated with this dx mu wedge dx nu. This is like an area element associated with the loop where the curvature is located. So then this here depends on these local indices, and it completely removes these global indices. So now we have this formulation that's completely independent of the base manifold. It's independent of the actual structure of what's going on, and it's purely gauge theoretic. And then you get this, so it's a 2 form because we're hiding 2 indices, and the torsion 2 form leaves 1 gauge index here. And the non-metricity tensor is a 1 form, as I was saying, because you just consider transport on an open line rather than around a closed loop that forms an area like you do for curvature and torsion. So that makes it a 1 form. And so you have 2 indices left over here associated with those 2 vectors that you're transporting. And then you can think of these as field strengths. So an electric field and a magnetic field are examples of field strengths in Maxwell's theory. And then there was this electromagnetic potential. We had the scalar potential and the vector potential, maybe like phi. Well, the scalar potential is kind of like a voltage, right? And then you had A as a vector field. Those got unified into this 4 vector, A mu. And that was the potential. So you have in Maxwell's theory, in the relativistic formulation, you have this electromagnetic potential as a potential. And then you take derivatives of that, and that leads to the field strength that encodes the electric and magnetic fields. So now here we have 3 different potentials. We have the spin connection that leads to this curvature. We have the frame field that leads to this torsion tensor, and we have the metric tensor itself that leads to non-metricity. And let's be honest, probably 99%, even like a lot of gravitational researchers don't know this. This is pretty obscure. But this is a very nice picture because it really what goes to what. Like most people just assume the metric immediately goes to curvature, and what they're failing to recognize is that, well, technically what's happening is you're reducing the theory to some simplicity where you get this like cascading of coincidences where it turns out that the metric is related to the frame field, which is related to the spin connection, which then relates to the curvature tensor. And so when people don't go to this full framework, they often get confused. So yeah, basically there's different types of transport, as I was alluding to. There's this geodesic equation that we'll call geodesic transport, and that uses the Levi-Civita connection. But there's also this notion of autoparallel transport, which uses the most general affine connection that could include the contortion and the disformation coming from the torsion and the non-metricity. And so you can get in these philosophical debates about, well, what is the valid transport? If I'm transporting a vector from A to B, what equation do I use? There's not really even a good consensus yet on what the best way to do this. Everyone has different opinions. As far as I've seen, one good opinion seems to be, like, if you have torsion, you can imagine kind of taking a string and like twisting it, and then it'll cause you to like spiral in a helix. And so if you had a vector field and there was torsion and you ignored the torsion, then you would be on the geodesic transport, right? So imagine, let's say you have torsion, it's going to cause some spiraling leading to a helix, let's say, and you forgot about the torsion. So you did the transport one way, you go from A to B and you get this vector and it ends up where it ends up. It turns out the autoparallel transport allows you to take another path from A to B, but it's a different path, and you wouldn't twist the vector as you're transporting it, but when you end up at B, the path is chosen such that you land on something that it twists it in the way that the vector would have rotated as if you transported along the geodesic but accounted for the torsion. I wish I made a better picture to demonstrate that, but basically it seems like there is some nice notion of this geodesic transport. We want to latch onto it and keep that as what's going on, but that's maybe the path that's going to be followed, but it also is helpful to consider the autoparallel transport to make something. That's one interpretation that seems sophisticated and interesting. That seemed sensible, at least. So I'm not even going to mention that last comment. So yeah, basically you can have this Lagrangian that goes in your action principle, and then now you can have, typically you have this stress tensor that I was talking about that's a derivative with respect to the metric, but now you get these other sources that you can consider because you have the frame field. Sorry, that's the same thing as that EA. This E right here, we have this spin connection, this frame field, and this metric. It's a similar thing here. We have this connection here, this frame field, and this metric. Those lead to different sources, and just something to keep in mind if you happen to go into these theories. And so basically, as I was mentioning before, you have this geometrical trinity of gravity where within metric affine gravity, you can simplify again, and you can go just back to curvature, look at general relativity, or you could just focus on torsion. Turns out there's this metric teleparallel equivalent to general relativity theory. And basically this it has a gauge group of the translations alone, which is interesting. And then this non-metricity theory is called symmetric teleparallel equivalent to general relativity. We got these beautiful names, these awesome acronyms. And actually people refer to these as different. This is also called coincident gravity. And if you teleparallels them, they're usually talking about this one now because this one came later. So more people know about this theory. This is the most common one. Some people know about this theory and few people know about this theory. And this one is actually my favorite. But fair enough. So this is the metric teleparallel theory. It's a bit of a mouthful. And basically it's flat, which means it has no total compatible, which means it has no non-metricity. So that's why they call it. There's actually a reason for it. The name is because, so they name the theory not based on what it has, but based on what it doesn't have, which I guess doesn't make that much sense, but fair enough. So that paper, they didn't even cite the original theory where it came from. So this is, it was found in 1976. You get this Lagrangian for it. It's in terms of the torsion tensor. And basically the translations are the gauge group. And actually Feynman said that, the translations are like the gauge group for gravity, but I don't think he understood how it was related to torsion. So, I mean, we have these, big figures in physics who providing us clues that some of these formulations are nice. And so, as far as I'm aware, this is the first formulation of teleparallelism that is equivalent to GR at low energies. And basically what you can do is take the Einstein-Hilbert action in terms of the total curvature, and that total curvature is going to contain curvature from torsion, actually, and then it's going to contain the other curvature that you're more familiar with. And then when you set that to 0, you subtract all the torsion stuff to the other side, and then you'll see this pop out. In case anyone is interested in deriving this, that's how you do it. And basically, you can do the same equivalent to GR theory. It's once again flat. So any teleparallel theory has no total curvature. And it's torsionless, which means that the affine connection is symmetric because the torsion tensor was this anti-symmetric piece of the affine connection. So if the affine connection is symmetric, then there is no anti-symmetric part. So once again, we're naming this theory based on what it doesn't have. And it's symmetric and teleparallel, which means it could have non-metricity. And you do the same trick again, and you can find that you get this Lagrangian, and you can It's actually, don't worry about trying to derive the field equations. If you're interested, I'd love to talk to you more. It's a fun calculation to try to do. And basically, this theory was found in 1998, but then it was rediscovered maybe 3 years ago. And it has this covariant energy momentum tensor instead of a pseudo tensor, which helps for a lot of considerations with energy conservation. So it's actually remarkable looking back in the history, because there were a lot of people complaining about various properties about the pseudo tensor. There was this Eddington pseudo tensor, and it worked nice for calculations, but it like physically didn't make sense in some regards. So this seems to fix some of those things. But people were arguing about this so long ago, people don't care as much anymore. But it's good. It's good to see that problem get fixed, and it allows for this coincident gauge, which is why it's I think some coincident general relativity. And basically, the disk formation becomes equal to the Levi-Civita connection, which means that you can set the affine connection to vanish, and then you get the Levi-Civita connection, and you subtract the disk formation to the other side, and now you have those two terms equal. And that's just a very nice, convenient thing to look at, because it allows you to connect back to old theories more readily, but then get these nice covariant properties. And so this is another way to write Einstein's the Einstein-Hilbert action ends at the field. You can get Einstein's field equations from this Lagrangian. This Lagrangian has been known for probably almost 100 years, but this can be recovered from this theory in a way. So that's kind of nice to see. And so then you could ask, well, okay, we have these different equivalent theories, but can we classify all of the theories that are equivalent to GR? That was the question I was interested in around 2018 before that paper came out. And I was looking into this paper as well, which found that, okay, how I mentioned this first order versus second order formulation? The first order formulation treats the connection as dynamical, whereas the second order formulation treats the metric as dynamical. So there's this history of final gravity going back to, let's see, 1918. And at first, everyone treated it as a second order formulation just because that's the only thing they knew how to do. And so and people argued about that, and most people decided it wasn't the greatest theory. But this theory from 2013 is claiming that basically if you treat final gravity as a first order formulation, then it leads to Einstein's field equations if the torsion vanishes. And so basically this could be another way to get an equivalent. And so the Lagrangian is an R squared Lagrangian. So the Einstein-Hilbert action just had the R term. And once again, I was talking about Yang-Mills theory, which has it's a quadratic Lagrangian. And you notice this is quadratic. It has Q times Q. This is T times T, right? So if we have the R term, we have the T squared terms, we have the Q squared terms. It makes you wonder, well, what about R squared terms? Can I get that to work? If you go in the literature, you start looking, people be like, you can't do it because it doesn't work, right? But that's all of those people are doing a second order formulation. So if we do first order formulation, according to this author, I haven't fully vetted it, but it seems promising. And in fact, there's actually, you can take any Lagrangian, and there's this trick you can do called gauge fixing, and then you can add stuff to the Lagrangian and reparameterize things. So there's actually like an infinite number of ways to look at the same theory in a different way, which is like even a different point from all of these theories. So, and some of these techniques have also been used to find equivalents to GR that look very different, and the methods for computing solutions are completely different, but then you get the same results. So this is really mind-blowing to me, because if there are certain issues with certain aspects of the philosophy of GR, then we can start to explore the different philosophical standpoints for all these other equivalents. And okay, so then we can look at something maybe a little more interesting for everyone in the audience here, is trying to get to interesting propulsion, right? So you could look at the Alchemy drive in general relativity, and you could claim that you can get faster than light travel in a global sense, and you do this trick where you're basically applying metric engineering such that you can have your local speed be less than c, but you're warping space-time in this exotic manner such that you can actually get faster than light travel. And it basically involves metric engineering, which involves, this is the difficulty. Einstein's field equations are so difficult. You can imagine trying to find a solution and you could find some solution, plug it in the equations, confirm that's consistent, but then you have to figure out, well, what matter is needed to source this solution. And basically, the metric tensor is what defines length. So if you specify the equations here of how length is kind of defined in that region, then that's specifying the solution to g mu nu, which is the metric tensor. And so now there's problems with this. People say that you need negative energy density in order to source this. And also maybe in order to accelerate, it seems like it might violate energy conservation or some weak energy condition. And so basically, there was this paper that came out like a week ago or 2 weeks ago that I saw on Jack Sarfati's email list, where they used this metric tail parallel theory that I just showed you with the torsion. And there they say that a static observer measures positive energy of the source, while a Eulerian observer measures a negative one. So you can get into all these philosophical debates now about what is energy, right? And there's all these different perspectives, especially in general relativity. There's like Bondi energy, there's this ADM energy, that energy. There's all these different energies because, we've been trying to figure out what's going on with this global energy issue with general relativity. Theories that came along later seem to fix some of those problems. So when you start looking at solutions of general relativity in these new theories, it provides you a new perspective that might help you figure out, well, like what is the good energy? And so this paper claimed to fix a lot of the problems with the Alchemy drive and had a lot of hype claiming that this would be a good way to look at it. And then I was just searching around the internet like 10 minutes ago before I started presenting, and once again in conformal gravity, they found similar things where basically they don't violate the weak energy condition when you look at it from the conformal gravity perspective. You're not required to use exotic matter. And I'm just pulling this from their abstract. I didn't even look into the paper that in much detail, but they're saying basically if conformal gravity is a correct extension of general relativity, then superluminal motion via an Alchemy drive might be a realistic solution, thus allowing faster than light interstellar travel. And also there's this paper that came out last year that was looking into some different geometric structures, and they found this positive energy warp drive. And there was also some people talking about solitons or sound waves and different things potentially being anti-gravitic. I saw on the news like a few months ago, and this is a completely independent work, but it's similar. They're talking about solitons, where basically they're stationary solitary waves that exhibit particle-like behavior. And I guess they found that you can get these superluminal solitons, and they actually have positive energy, even though it kind of looks like they have negative energy. So when you hear people claiming that they found some negative energy thing, maybe just keep in mind, maybe it's not as controversial as they're claiming. Maybe. And so this geometrical interpretation opens new doors to generating realistic warp fields for laboratory study and potential future manned interstellar travel. And so at this point, I don't even know what time it is exactly right now, but I figured this would be a good spot to at least pause, see how I'm doing. This could be a potential spot to conclude. Let me just see how we're doing on time. Yeah. So I'll just stop and see if we have any questions right now, or I just kind of mini conclusion would be, even though Einstein's GR might not stay in its current formulation forever in the future, I do believe that we can still embrace Einstein's legacy and find a lot of fruitful value from it. And basically these gauge theories of gravity have better behaviors for various different reasons, whether it be quantum field theory or getting into these different energy considerations, which seem promising for warp drive and LQBR drives. So I'll just stop there for a moment and see if there's any questions. I do have like another, 30, 50 slides that I could go on. It's going into different formulations of gravity more, less about warp drive. I figured.
Oh well, David. Yeah, it's Tim. Do you want to go through those then? I think we're kind of. and it's up to you. Do you want to go to Q&A session, or do you want to keep going?
Oh boy, I'm open to either. Whatever. I mean, if the questions are good, no, I'm just kidding. It's it doesn't matter too much to me.
Well, if you're up to it, I mean, if you're up for it, why don't we go to Q&A session now? Do you think you might be open to coming back in the future, and you can kind of conclude from there?
Yeah, and I mean, this stuff, I mean, it's just a bunch of math and stuff, like, I could keep going. I could show you this Lagrange, but is that going to mean anything they want? Probably not.
Yeah. Okay. Well, let me do this then, man. Yeah. And I cannot thank you enough. Let me stop your screen share right now.
Sure.
Let me see. Okay. Stop your screen share, and then I'm going to put this on gallery view. And everyone, please give an enormous applause to Dr. David Chester. And David, I literally, I cannot thank you enough for the thing that always amazes me about your work is it's not just that you know the theories, it's that you can compare the theories, right? And they're like, there's like so few people in the world who are able to do that. Say, look, here's what this one is doing, here's what that one is doing. So that's why it's so exciting, for me.
Thank you. I really appreciate that feedback. Yeah, and I had the same perspective. I mean, I saw so many different gravitational theories, and it just became obvious that this needs to go in class, and everyone's just kind of going in one direction and then just arguing, this is the best theory because of this. And then you start looking at all the different theories, they're all finding the same results in these different formulations. So there's some bigger picture behind the scenes.
Yeah. Well, let me go to questions. Let me see, and I'm going to allow people to unmute themselves, but let me take an order. So Falcon Labs, I think that's Mark Sokol. But I'll go there first. There he is. Go for it, Mark.
Yeah, let me just share a screen for a second so I can show you this. Show you the right screen.
Oh, okay.
Yeah. So this is a video I found on YouTube about general relativity, talking about Mercury's perihelion precession.
Sure. His general equation for the planets reduced down to exactly Newton's equations, just plus one extra term, and that extra term was 2gm over c squared r cubed. So g is how strong gravity generally is in the universe, m is the mass of the sun, c being the speed of light, and r being the distance of the planet.
Yeah, so I think that's enough context. So basically, obviously, solving general relativity exactly is very difficult, and it wasn't done, in order to confirm the orbit of Mercury, the perihelion, I mean, they didn't solve. It's kind of complicated history because some people argue that even the experiment that confirmed GR may have been fabricated in order to make it look like GR was right. But then over time, as we did more measurements, it does seem like the prediction held up. And so what you happen is when you study GR, you can linearize GR. So then there's linearized gravity. And that was Mercury. And so then you can, I mean, it depends how deep you want to go in the literature and talk about.
I mean, basically what they were insinuating was that most of his math basically equaled Newtonian mathematics, except for this one equation, which was only derived knowing the perihelion precession of Mercury, having past couple of years.
Yeah, I mean, obviously Einstein was motivated to try to solve this problem, so I think that was the main thing he was looking for. So, he was looking at the data and trying to figure out a theory that matched the data, and that's what people do. And it turned out he was able to do it. And, you could argue, I get it, like, I'm interested in linear approaches to gravity. Like, and there's a lot of theory. I mean, that's why I mentioned side gravity. So you could say, well, maybe linearized gravity is all we need, right? Like, why do we need to go to all this nonlinear stuff? But I mean, it gets to a point where we got to look at all the experimental data. And so, honestly, with the perihelion Mercury, the story gets very complicated because there's all these different approximation schemes for general relativity. then, different things, and it depends, like, I've tried going into the weeds on looking at, like, okay, well, like, how accurate do we measure, how accurate do people compute it, and there's varying layers, like, of people who argue at different generations, like, oh, I calculated more. And another
important part of Mercury's perihelion precession is actually the planet Venus and Earth. Our planet tugs on Mercury as well, and that's changing. And this equation, for most part, for Earth, the radius, we're so far away from the sun that it almost equals to zero. But for Mercury, which is a lot closer, it does make a small change. And then there's Venus tugging on it, and then there's Earth tugging on it, and to a lesser extent, Mars and Jupiter. So there's a lot more components playing into this, which makes the mathematics so much more complicated to figure out.
That's the problem with life. It's too complicated to actually nail everything. And so, depending on your application, you might. Everyone's got to make approximations. I don't even look at, I'm interested in unified field theories, but I don't look at it as being the final theory. Like, I just see it like we need some theory that describes all phenomena universally, and it's going to be approximately accurate, let's say. And, different people do the same thing, and depending on your application, you can ask, how accurate is this theory for the phenomena I'm interested in, and evaluate that.
Yeah. Well, so let me, Mark, so thank you to Mark. Let me go to Michael next. That way we can start moving along to questions. Michael, go for it.
Hey, thanks. First off, thanks, David. Awesome presentation. This is really determined undergraduate to really dig into this. And this is just going to be a huge, great resource to have. And Mark, very impressed with your progress in learning these topics. I think Remy's correct in the comments in the chat. It's, the gravitational field is going to gravitate because it contains energy. Right? It's very small and for most applications. What it was, I had a few questions somewhere. Let's see. Have we got you in touch with Ken? I can ask that later. What else? So, what would graviton that's equivalent to the squeezed vacuum state? Are you familiar with squeezed vacuum states?
Let's see. I've studied squeezed states in quantum mechanics. Let's see. My squeezed vacuum state, what are you referring to exactly? So
you apply the Bogoliubov transform to vacuum noise, or the matrix that would be flat space-time, or equivalently like isotropic vats.
Are you thinking of like the quantum electrodynamic vacuum?
Yes, so basically my understanding comes from the quantum electrodynamics side, where I'm looking at it from a perspective where you've got space-time refractive index instead of curvature because they're equivalent.
Right.
The quantum electrodynamic virtual particles define that refractive index. And that's
from my perspective, I'm just fascinated with the standard model, and I'm fascinated with the mathematical similarities between Yang-Mills theory and general relativity. So I would prefer to think of all, just generalize electromagnetism to all other forces, right? And you can, you have the strong force, you have the weak force. And so I think a lot of these are interesting and worthwhile pursuing. In my opinion, I would just try to go to Yang-Mills theory, but that's just because of my interest. And so I would, in my head, I would just immediately say everything you're saying and kind of convert it into being maybe it's not just squeezed photons, virtual photons, but also gluons. Why not?
Well, it's squeezed anything ultimately.
Exactly.
But if you're unifying electromagnetism with the weak and the strong force, squeezed anything within that.
Yeah, sure. Yeah. I mean, that's probably stuff you get out of that.
Yeah, I think so. I think it's worth discussing further. Then the other thing I wanted to mention is, because I'm more looking at it from the experimental results, because squeezed vacuum states, they've been observed, but for some reason they haven't been attributed. They're considered an excitation, I guess, but they haven't been given a name as their own particle or anything, which is weird. I don't know why. But the other thing I wanted to mention is, are you familiar with spatiotemporal optical vortices?
Not precisely.
That would be they're photons with orbital angular momentum.
Orbital angular momentum. Huh. Okay. Oh, okay. You got how?
Some people call them Majorana photons, or.
Okay. Yeah, I've heard about some of those.
Yeah.
Yeah, and condensed matter
in free space. So that's the interesting thing. They've been.
That is interesting.
Yeah. So a lot of the EVO stuff, I wonder if that's a component in that, because now you've got a Maxwell's equation solution where your fields are still orthogonal, but you've got this toroidal geometry.
Okay, yeah. I would be interested in looking at that more. As I was mentioning in the chat before, I'm interested in this toroidal.
Sorry, I interrupted.
No, that's fine. I'm interested in this toroidal solution that relates to torsion for fundamental particles. So at one point, I could see that happening. I mean, any particle with the same should have this torsion field, and it probably would connect to what you're saying in some way. And also, it seems that in order to do the path orbital for hydrogen, you need torsion as well. I'm interested in some of that.
There's a lot of other terms. It's been discovered independently at least 4 times now, to my knowledge. So people use all those different terms to describe the same thing. But we'll definitely discuss it further. And then the last, I did one more thing. What was it? Oh, I just had it. I'll just get in the comments afterwards.
Yeah, sure. I just shared my email.
Michael, thank you. And so let me go to Mark Fiorentino next. Mark, sir? Oh, and Mark.
There we go.
There we go. Okay.
There we go. Hey, call out to Mark Sokol for bringing up that point about the Newtonian math. In that solution that I sent you, David, that was a Newtonian math solution. Remember?
Let's see.
Gravity and inertia solution that I came up with on ResearchGate. It was a
send me another email. I remember us talking. I remember us chatting. I just don't remember exactly where we left off.
We had some disagreement about the strong force in the gluon, which is a side thing. It's a side thing. The solution is just the moment of inertia used in a way that described the particle motion. Is accelerated fundamental particles, unbalanced charges, cause their gravity via accelerated motion. Bending the ether. Now, the question I have for you, the first question, I got really 2. The first question is, you use the term curvature a lot here for gravity. I would like you to define what curve are you talking about?
I was talking about curvature of a space-time manifold as typically studied in, I'm imagining this mathematical thing of a manifold coming from some topological space that is, you have this topological space, you got all these points, and then you get this geometry, and the points are connected. There's differential structure, it's continuous. You can, the manifold's differentiable.
Continuous, very good. I like that. Could you think of it perhaps as maybe a simple contraction? The curvature is moving inward toward the origin of the gravitational field. So have you ever considered that to be a contraction of space? And that's the curvature.
Well, yeah, so, I guess depending on precisely how we mathematically do electricity. Example of deforming length, which you could look at as a type of contraction. But
now you're getting
different than length contraction. So that's the problem with speaking in languages such as English. It becomes very difficult to precisely get on the same page.
So
but there's possibilities I could think of.
So you're talking about the Ehrenfest paradox as the method for the contraction then. No, that's exact. That comes from special relativity.
Yeah, so I mean, non-electricity is not in special relativity. I think what I was referring to is something different, right? And I don't know.
Mark, and if I could jump in really quick, and this is a complete tangent. I'm just looking at the door in your closet. You, sir, like hats.
Yeah, I do have a lot of hats back here.
You do have a lot of hats. I'm looking at there's a Yahoo and there's a boonie cap and
that's a Yale cap.
Oh, okay.
Tommy John and Tommy Bahama. I got them all.
Yeah, you do. You have quite a collection there. Quite a collection.
Yeah. Anyway, let me get back to this other thing. The last question. I'm really curious of mental life. Could that possibly be interpreted as also a metric tensor for density?
Density of what?
Of that continuous space that you just referred to. If space were really real, an ether, it would then have to have a density, correct? If it were real.
Refractive index, I think. Sorry.
So you could have some stuff, and it could have some energy density or something, or it could have a density of some quantity.
Assuming, if you're going to calculate a length, the length is going to be dependent upon the density of the material. If you believe that there is a material there, you're calculating a length or density for.
Yeah, I mean, density is like 1 over volume. So if you're messing with length, that'll affect the volume.
Aaron's Planck's constant for that, and the Schwarzschild proton for that density. Sorry.
Bernie, let Mark finish. Because we're neck deep in
I'm almost
complex stuff
here. Just the volume, though. Can you have a volume for a continuous object? I know volume is usually used when you're calculating for particles. A particle field or something like that. Yeah, that's particles again. I mean, a continuous solid. Can you have a volume for that?
Yeah, I mean, my phone. I mean, when I zoom out, it looks continuous to me, and it has some volume associated with it.
Okay, so is there anything like that, a calculation like that, in any of Einstein's work or your work?
It's Weyl curvature. You got to think of it as derived from the amount of particles in the ether. They're virtual particles, so it doesn't have its own reference frame, but that's the idea, I think.
Put your email on the thing, please, sir. I want to get more explanation for that.
That might be helpful, because I think you guys have pretty much completely lost me. And
because aren't you referring to the vacuum catastrophe?
I appreciate your work. You're very nice.
Thank you.
Well, Mark, thank you, sir.
I also remember the question that I had.
Let me see. Do you want to go really quick?
So, David, are you familiar with the results from Gravity Probe B?
I've heard tangentially about it. I didn't look into the details.
Well, they seem shown that. Yeah. So, would that be? Is that equivalent to the torsion concept, or is it generated by the torsion?
No, I actually think that this. Yeah. So this is where I would argue that the analogy between electromagnetism and the mode general of gravity breaks down, because torsion is a type of, it's like a gravitomagnetism, but it's a different type. And the way I would articulate that is to recall that it's one, whereas electromagnetism is spin one. So it's almost like when you combine, you get the polarization of the graviton. You can get it from multiplying two spin one tensors, polarization tensors together. And so you you should really actually think of, typical curvature that you're thinking of or gravity as being like electric, and then one of them being electric magnetic. Maybe the electric magnetic. So there could be generalized gravitomagnetic effects that are difficult to understand from just electromagnetism alone. So I think there's multiple types of gravitomagnetic effects, and some of them are only in some theories and some have more. So if you had a theory without torsion, you could still have the lens throwing effect, and then the torsion is completely independent as a different thing. Confusing.
It is a property of the particle itself, then.
I mean, it really depends. I mean, you can just look at it as a property of space-time, like the manifold itself can have torsion. I prefer theory. I prefer theories of torsion that restrict it to the spin density, that are sourced by spin density. But the metric teleparallel theory doesn't set it up that way. That's more the Einstein-Cartan theory. So
we're talking about a very broad theory space here, then.
You can consider it.
Well, in that case, I definitely recommend reading up on those spatiotemporal optical vortices and other things as well.
Yeah, that sounds interesting.
That'll narrow it down for you, hopefully.
Cool, thanks.
Awesome. Okay, well, let me go to Michael Boyd next, and we've got about 20 minutes left. And again, David, thank you so much for presenting today. Michael, go for it, sir.
Hi, David. Thank you. I'm curious, you used the term negative energy. Could you explain what you mean by that phrase, negative energy?
Yeah, so I mean, this is coming from the kind of standard approach to the Alchemy drive. They found this solution to Einstein's field equation, so they got this metric tensor, and then they had to figure out, well, what energy do I need to source that curvature associated with that metric? That's whatever, you got kinetic energy, you got mass equals mc squared, everything's positive energy. Typically gravity is always an attractive force. There's no gravitational repulsion that's kind of related to the fact that all energy is positive. So they realized that it seemed like you needed negative energy, almost like negative mass or something, like the first solution of this Alchemy drive, they found that they needed this negative energy, which seems like it doesn't exist. So
dark energy? It's like dark energy? Like it's
actually not. Well, no, not really. So that's the thing, that they were like, it's just a math thing. They said, in order to get this warp drive, we need some type of negative energy that we don't even know if it exists. It probably doesn't exist. So it was kind of left open for further research. Well, maybe we'll either discover some negative energy, or maybe we'll find some different solution that maybe can get around this problem without requiring negative energy. And so some of the recent papers that have come out, when they're looking at these theories that are slightly different than GR, they're actually finding that there's different ways you can look at energy, and it gets a little complicated, but basically with negative energy, from a different perspective, it turns out it's actually not negative energy at all. So now it seems like there might be ways to use normal matter, not exotic negative energy that probably doesn't exist, and use normal matter in some way to create it. Now, I haven't looked into the details of these enough to really comment too much more than that, but that seems to be
let's think about it differently. To have gravity, you need to have matter or mass.
Typically, you need something to source the gravity, which is any type of energy, which could include mass or momentum or stress, which is kind of like it's basically like when you have a material and you shear it, you're putting stress on the material. Like you have a stress ball that's going to like form the space-time manifold, which is usually energy or momentum. But so it doesn't just have to be mass. So if you had massless particles, those massless particles will have energy, kinetic energy, and that kinetic energy will actually warp space-time.
So like photons are a massless particle, supposedly. Is that?
Yeah, that's a perfect example.
The speed is irrespective of the frame of reference, whether it's in space or on the surface of the sun. The speed is always the same.
Yeah.
So wouldn't that mean that the photons are independent from the force of gravity, or wouldn't that?
It turns out that you can still. Yeah, it gets pretty complicated, but it turns out when you solve the equations, it turns out that you can still have photons participating in a gravitational force, yet they'll still always move at the speed of light. It's it actually can work that way. So yeah, you can just you just write down the stress energy momentum tensor associated with the photons, and then you figure out how that sources that, and it'll have some back reaction. Now, I mean, I would say that we still might not have a consensus on what the best way to unify those two forces. There's definitely a lot of good candidates out there, but so you could maybe argue that there's new physics we haven't understood yet for the interplay of electromagnetism and gravity. But at low energies, the story seems pretty clear that I mean, because another big result of general relativity was the fact that photons got this like ring of light that goes around the sun, and so a big part of the confirmation of general relativity was looking at how light bends.
That would be gravitational lensing you're talking about, wouldn't it?
Yeah. So that's all I'm referring to.
So I got your email. It's just to verify, it's David C. at quantumgravityresearch.org. Is that correct?
That's correct.
I would like to send you some data. I have some inventions using gravitomagnetism that uses nanobumps and nanopits.
Yeah, we'll send Michael, send that over, and let's take it offline then.
Yeah, so I'm going to take that offline. But I have one final question. Is about how do you deal with what's called offset accelerate. Say you accelerate towards Alpha Centauri at half the speed of light, and then you come back to Earth. That the people they're all going to be dead and gone, and you're going to be like so many thousand years in the future. This offset spatial divergence. How do you deal with that when we're talking about?
Well, I mean, you could consider transport and calculate, like, you got to get to another location. Yeah, I mean, I mean, obviously, yeah, the theories are going to deal with that. I mean, you could consider how long it takes to get from A to B. Maybe you make some warp drive device and figure out how to get to B really fast and come back. But you got to look at time, how it works in everyone's different perspectives. So, the theories might deal with that and, make it back without having all your friends dead. That might be quite a challenge. But, the theories at least
Thank you very much for your answers. Appreciate it.
Awesome. And Michael, thank you as well, sir. So let me go to John Quinn, and then I will come back to BurnEye after that. I'm kind of squeezing things around. John, go ahead, sir.
That's Tim Ventura and our presenter, David Chester. Great talk and amazing overview of so many brands or variations, modifications of general relativity theory. Just really quickly, this kind of cabooses to Mark Fiorentino's point about contraction the importance of contraction. In a different field of geometry, we don't have well-defined tangents and metric tensors all the time in fractal geometry. But what we do have are families of contraction mappings that can define generic compact sets that have different kinds of ways of measuring things. Sometimes a metric might converge, sometimes it might not. And this allows us to kind of evaluate singularities because necessarily integer value. And so the notion of diffeomorphism and variance, I think, can play into this if we just normalize diffeomorphisms to be contraction maps in some greater space. Then we could maybe take a subfamily of those diffeomorphisms, the diffeomorphism group in general relativity. Loosely speaking, I think you were saying it does in conticity, or at least the torsion, if I'm not mistaken, right, to get the full diffeomorphism group. But anyway, if you normalize that, so they all have some kind of norm less than 1, then you have this family of contraction mappings. And it's not really well known in fractal geometry, but we can deal with what are called compact families. So uncountable families of contraction mappings even have, and they turn out to be the crystal groups and the quasi-crystals in the work of Baca and Moody. Is this being used in the context of gravity?
It's funny that you said that because actually where I work at this place called Quantum Gravity Research, we're looking into quasi-crystals, and it seems like, as far as I understand, if you look at the Fourier transformation of the quasi-crystals, then you find fractals a lot of times. So I'm currently slowly working on basically a quasi-crystal projected from E8, and so there is some work by Notal, who did some scale relativity that seemed very interesting. I'd like to look more into that one day. And it seems like El Nashi kind of got too excited and destroyed all the hype because he kept citing himself, and he got more citations than anyone has back then. He ruined the credibility in the field. So ever since then, no one has really taken it seriously, but I think there's something important there. So I would love to see if, feel free to email me like any references on the mappings you're talking about for the fractal geometry.
You know what? So far, I haven't found too much in the literature that echoes these thoughts in just a very kind of clear way. I feel like this is the way Mandelbrot would have approached general relativity. And it gives you is an inroad to quantum gravity, if I am correct, because in the fractal worldview we iterate, and the natural way to iterate, it seems like here, would be some type of multiplication, like a tensor product. The tensor product is in the quantum side is a is a complex system, a multi-body system. So it looks like that would lead to talking about the elastic condition on space-time. It's a rather crude analogy, but the box counting dimension is a perfect analogy of the economic elasticity, which is a crude analogy of physical elasticity. So I think there's some things that are very happy congruences between the smooth and rough geometries that you see in general relativity contrasted to fractal geometry. I need to straighten my thoughts out and review my general relativity in better order so I can send you a more intelligent kind of bunch of thoughts on this. But as they relate from our research with my research group at UC Riverside from fractal geometry. So I'll make a point to do that. I also was going to try to present representations in quantum theory and how this plays out because of this obvious relationship to fractal geometry, how this plays out to some other applications. I think I see it in what you call the Drake equation, which is so accessible to everyone here. I think we're all wondering, like, where are the aliens, right? Fermi's paradox, and I was, I don't want to take up too much. I was going to kind of bring that perspective to an equation we can all kind of sink our hands on, or grab onto, and try to do stuff with and apply to mind. This might be a little controversial, but maybe mind is kind of at the center of it. You don't see it as much on the GR side, but definitely on the quantum side, there were hints. It looks like we don't need conscious observers now, but maybe it'll come back.
Yeah, wonderful. And John, thank you as well, sir. So let me loop back around to Bernie really quick. We've got about 10 more minutes. And David, thank you again for your time, sir.
Thank you.
Let me see, Bernie.
David, great work. It's always quite the time trying to understand hyperdimensional physics and systems being described, but you did a pretty good job of it. If you don't recommend trying to enter some of your rotational based systems into that, if you haven't looked into his simulations and programs now.
Sorry, did you mention, I saw you had the Wolfram book, you just broke up for a bit. Are you referring to Stephen Wolfram?
Yes, sir.
Yeah, so I actually did the Wolfram summer school like a year ago.
Nice.
And I was just a TA for the winter school, currently working with Xerxes there, who's under Wolfram. Yeah, so he has this hypergraph model of graphs and this and that. So I did a project looking at curvature, torsion, and non-metricity on discrete graphs for discrete models in the Wolfram summer school. So yeah, I've been following what they're doing, and it's very exciting.
Nice. I could see how it would relate to your work for sure. Last comment.
You're cutting out again.
If you can hear me, Nassim Haramein's Schwarzschild proton thesis on holographic universe and the vacuum catastrophe theorem. It's a really good read and has great relativity to your work. Thank you.
Yeah, he has origin. He likes Einstein-Cartan theory. Maybe he put some like background torsion field through everything. He has some cool once, and basically he's hiding the mass of the proton in this whole thing. There's one big thing he hasn't figured out: mass renormalization, and he makes everything like he gets all these things at different scales, brings it all together, and it all relates to the proton. There's just one problem: he doesn't actually use the proton mass. He like makes up this holographic proton mass that isn't the proton mass, and he doesn't understand what that means. So. Yeah, he's that's the thing. You can make all these models at varying degrees, and so yeah, in some ways he's on the right track. In other ways, he's probably stuck on some things.
Awesome. Well, Bernie, thank you again, sir. Let me jump back over to Phil. Mr. Bouchard.
Hi. Yeah, thanks, David. That was an awesome presentation. I had questions, but I'll just skip to the one first. I'm doing an experiment on the gravitational shielding. I wanted to predict it before doing the experiment, but now I didn't have time to do the maths. And I was wondering, the energy of a graviton, is it similar to the energy? I read that it's slightly different than the energy of a photon, like the Planck multiplied by the frequency, but the graviton considers the mass. Why would the mass be considered in the equation if it has no mass?
Yeah, I didn't follow that equation. Yeah, I would think it would just be the same. I mean, you could just look at any quantum as have energy related to h bar times the frequency. And the graviton doesn't typically have mass. I mean, you can get into some exotic theories that have very, very small mass for the photon and graviton, but let's ignore that. I didn't follow it exactly, so I would think it would be basically the same as the photon.
Oh, okay. All right, cool. Thanks. I appreciate it.
Okay, and Phil, thank you, sir. Let me go to Will next, and then we'll go to William Alec after that, and we'll just keep going until we hit the top of the hour. Mr. Riken? you're muted.
Is that okay?
Yeah, perfect.
Okay. Really, two questions. It was interesting that you were connecting your the equations into the Maxwell equations. Is it? And I haven't actually heard that take on this, or is that already completed as far as your work?
I mean, I looked into this a while ago, so I mean, this goes back over 100 years ago. Heaviside, before general relativity was created, just used Maxwell's equations for gravity, but no one really. It was probably no one really read it. Probably, and for a lot of people who use similar formulations, I think Hefemenko is probably the most famous, simply because he did a lot of good work in electrodynamics itself. And he actually has equations that are in Jackson's classical electrodynamics that's taught in grad school. So for the most part, any academic would not take that approach seriously anymore, because the graviton is spin 2, and we already detected gravitational waves by now. So most people would not look at it that way. But when you look at middle school, I mean, it's a spin 1 theory, and you look at the spin connection, you look at the connections. If you try to get away from the metric formulations towards the affine formulations, then it starts to look a little bit more like Maxwell. I mean, you could linearize gravity, you could linearize GR and get something that's sort of similar to Maxwell's equations there. And, you know, so I don't think there's anyone like in academia who's studying that, but some people look into it for approximations.
Well, one of the reasons why I was concerned about that is that if we take the current state of mathematics, which is really in tensors, then it seems that most engineers to build equipment over new technologies based upon this concept, whereas Maxwell equations have been simplified enough to allow engineers to build the world we have today. So where do you see that going?
Yeah, well, I mean, I guess large collaborations would help. And also, I mean, even in some of the more exotic theories, they'll often treat space and time separately, especially in a lot of the quantum theories. So what they're sometimes go back to these natural three-dimensional formulations to make the math easier. So maybe if that story continues, you could use similar vector calculus ideas to make contact with that at some point. You know, it might take time for someone to break it down that simply for the engineering level. But yeah, I mean, it's an interesting question. Like, is it challenge? Right? Like, if the universe is so complicated, like, how do we get engineers able to work on this? So, yeah, I mean, I think that's why it would make sense to have people try to pursue simple theories. If you can get some complicated theory that everyone is convinced is good, and then you can find some simple theory that is shown to be some approximation, then you know, that might make sense.
Okay, sorry, just one more question, please. You mentioned non-existent. So does that, in today, the way we build circuits, so do you think really we're just looking at ground potentials and the way electricity works today in order to get, so rather than invest on negative energy?
Potential states here. I mean, I'm just not aware of any way to find negative energy personally, but I don't know, maybe it's possible. But yeah, I mean, then you could look at voltage in a circuit, but I mean, that's a type of electrical potential that is sort of related to energy potential, but the dimensional analysis is a little different. So you can have negative potential, but that doesn't mean it's necessarily negative energy in this context.
trying to keep this up there. Mr. Alec, sir.
Okay, can you hear me okay?
Yeah.
Okay. David, I've been looking into this Einstein's gravitational constant, okay? And when you go and run the numbers, you see that you have c to the 4th power divided by 8 pi g. And that evaluates times 10 to the 42nd newtons. So you have a force. Einstein's gravitational constant is describing a force that, to overcome that force, it's just enormous, an enormous force.
Right.
Okay? And it requires an enormous amount of mass to be able to define time. That space-time is an extremely rigid medium. I mean, just trying to compress space-time, you'd have to overcome this 10 to the 42nd newtons. Okay.
Right.
Now, when you compare the electric force with the gravitational force, you run those numbers. Get a number 10 to the 42nd power times the force of gravity, okay, gives you the force, gives you the electric force. So when you look at these two numbers here, 4.1 times 10 to the 42nd, and this force equation of Einstein's constant, 8 times 10 to the 42nd, it seems to me that they're almost interchangeable. That to overcome gravity, you just use electromagnetism.
Yeah, I think you would find that one of those numbers was probably a dimensionless number, looking at the ratio of the electromagnetic strength to the gravitational strength.
Yeah.
So that one would have that would be dimensionless. But I don't know, maybe you're onto some point. We should find some unified theory that has a single coupling constant that would unify them in some way.
All that we're really trying to do is either compress, space, or decompress, that's your negative energy, decompress space. Okay, that's what we're trying to do. And that you can use electromagnetism to accomplish it, because it's really the only number that's big enough.
Yeah, I mean, I think I would say that as far as I've seen, Jacques Sarfati is at least the closest to someone who's articulated how electrodynamics might help get over that difficulty barrier. I'm not even sure if he's right though, but he's thinking at least in the right direction. I think more people should explore that more in like condensed matter theory. It just gets very but yeah, I mean, energy electromagnetic systems to power these devices, it seems.
Exactly.
So,
right. Yeah. Right.
It gets difficult. It's a serious problem to actually make such some nice propulsion device.
Yeah. Okay. Well, Will, thank you. If it's okay, let me go to Michael really quick, and then we'll wrap things up after that. We're a little bit over time. Michael, sir.
Thanks. I just thought of one other, trying to understand the symmetries and asymmetries between these models and electromagnetism. So if you're familiar with Dirac's quantization argument with the magnetic monopole that's stretched dipole, if you look at that in terms of Maxwell's original equations in quaternions, it looks a lot like complex analysis in terms of how that ends up. Do you think there's any similar potentials with 1 over r that can be mapped to gravity that would allow a residue theorem for the mass?
Let's see. I'm not exactly sure. I'd have to review more detail to see precisely what you're referring to. But yeah, I mean, there's deep topology there with the magnetic monopoles and accidentally discovered cosmology. So I think that's a big clue that there's something there. I mean, there's all these topological studies of gravity as well. So Hopf vibrations. So that would be another example. So yeah, I mean, you have like, space-time, like when you get in the exotic gauge gravity stuff, you have these like fiber bundles and you can have Hopf vibrations. So I've been looking into like these Hopf vibrations from Eve, for instance, and trying to find like Hopf vibrations. Maybe that would eventually let me connect to the Dirac monopole story. I'm not exactly sure yet, but I guess that's the closest I can quickly mention.
And one last, where does Strominger's research fit in terms of the infrared triangle and all that stuff?
Strominger?
Andrew Strominger?
Yeah. I mean, I've followed some of his Sitter holography stuff. I don't know exactly what triangle you're referring to.
There were some.
Well, Michael, we are pushing up against our time. Yeah.
We'll chat in the email then.
Yeah. Send me an email.
Well, thank you so much. Yeah, so let me do this. Again, David, I genuinely cannot thank you enough for presenting today. Everyone, please give Dr. David Chester a giant applause.
Thanks.
I have never, why it's just so incredibly impressive, and it's such an honor to have you here, sir.
Really appreciate it.
Okay, so next, let me introduce, and I believe he is with us. We have several mics here, so I'm gonna, let me see. Retired mechanical engineer Mike Melia will present an approach to inertial propulsion and discuss a video that he's put together showing a proof of concept delivering perpendicular rotation in his device, and in normal circumstances only peripheral force should manifest itself and as part of this rotation. But contrary to this, the drive that he's going to demonstrate is creating a linear thrust at a 90-degree angle to the direction of rotation. So again, Mike Melia will be discussing this, and now I have to find out which of our mics he is. Sir? If he is here. He's joining us from the UK. And he may not be here. We'll give him another moment. Okay, so I think that our guest is not here. He's having communication issues. It could be one or the other. Guys, do you want to do open discussion then? Oh wait, there he is. He's having problems with this microphone. Okay. I see him. There we go. There we go. Mike? Yeah, sir, you're still muted. Or actually, you were not muted. Your microphone is just off. You can try switching the microphone volume. Is there a separate volume button for the mic? The other thing you may look at is on your computer, you may have a volume control for the microphone. That may be all the way down.
You could try telling him too, if you can hear me, have him disable the microphone in the software and then re-enable it, and that might reset it so it comes on. I have that issue all the time.
Okay. And Mike, I'm not sure if you heard Thomas, but he suggested disabling and then re-enabling the Try that. And we do have a couple of other suggestions. John suggested turning the auto adjust volume off, adjusting it manually. You may be able to turn that up. And Billy suggested that it's possible that it's muted in the Zoom window. And it does look like in Zoom it's muted right now. So it looks like you have mute on. That may have turned on automatically if you disable driver. Well, why don't we do this, Mike? While you work on this, why don't we go to open discussion, if that's okay?
Every Mike and Michael, I've come across their microphone is still showing the red down.
Yeah, so I'm pretty sure. In fact, I'm going to rename him here. Mike Melia. There we go. Mike Melia. I'm just renaming him. Yep. I'm just renaming him now. It looks like it looks like his microphone is off, but it was on a few moments ago, and it was also dead then. So. And I apologize issues. And then for Mr. Melia, when you do have it there, no worries, we can pop back in. Or if you'd like, we can also postpone. And I could do a test session with you another time. We could get the mic set up.
I'll say in that open portion, it'd be nice if some of these people are working with the math to this, like the formulas for basically finding how much energy at what frequency a photon is necessary for bonding versus ablation on various materials. And that would basically expedite manufacturer capabilities so that we could try their theories out. Just, drop of the hat, next to no money, not having to, get a giant grant or anything else like that. So, will be, 100 years from now, kids will be like, oh yeah, they thought this was hard while they're like in school learning about it.
Yeah. Well, and again, let me say to
Tim, isn't there a call-in number that they can just call in with a cell phone for audio?
There is. Mike, would you like to try a call-in number? But that would be an alternative. Let me paste that into chat just in case. And
Yeah, I was gonna say the only other option I can think is for him to completely shut his system off and reboot it, and then rejoin the call, because that might be something that the computer's just having an issue with because it's been on for a while or something. So, or he was running something before he joined that is conflicting with like Zoom. Skype does that. It hold your mic and not let go of it to go to the Zoom call. I've had that issue too. So if you have anything else that's using your microphone, make sure all those programs are turned off and then do a disable and then re-enable so you can try to get Zoom to pick it up and then go into your Zoom settings then and force it to the microphone you're trying to use.
Yeah.
So that should help.
Which one is this? Oh, that's Vulcan Labs. Oh, I see. Okay, that's rebroadcasting. Well, yeah, I would say, guys, let's just do open discussion for now, if that's okay. Or if you'd like, Mark, would you like to do lab updates now? That's something else that we could do.
We're still working on some stuff. I'd rather show you in a little bit. It's an hour, so
yeah.
We're on good time. Do you have that phone number you can call into? I'm trying to find it.
Actually, I just pasted it in there. I just pasted in the local access numbers. He's in the UK, so he needs to find it.
Or you can Google Voice to call in, which can run into all of its own problems. That is really disturbing, by the way, Mark, seeing his face through your filter. When he moves,
what you're looking at is a microscope that's looking through a fiberscope that's pointed back at my screen. So this is the fiberscope we're going to be using for the high energy experiments. And
we're not looking at a digital filter. We're looking at a literal real world filter of the.
You're looking at a digital analog filter or digital analog device. It's a whole bunch of fiber optic wires that are going through tube. Basically to protect to keep the camera away from the experiment.
Yeah, flashback to the 1980s. Flashback to the 1980s. I remember that. Remember the fiber optics came out? That was one of those, back in the day.
And
look at Tim's face now. Tim, I don't see the phone number in the chat.
So again, I pasted in the page, the web page he would have to go to for local numbers, because he's in the UK, right? So he's gonna want. And here, I'll paste that in directly as a chat to him. Oh, I did it as a direct message to him. That's. Yeah, and Mike, if you'd like, you could try rebooting and entering the call again. Do you want to try and reboot your machine and enter back in? Well, so Mark, to ask about this fiber scope, it looks like the visual quality on this is it's not as high as I would have guessed. I guess so.
Well, here it is.
Do you anticipate any issues using it? I mean,
I've been and it's kind of limiting, but you're able to look at anything. You're able to stick this end inside of a microwave oven and still get a clear image out of it without frying your camera. And I couldn't think of any other way to do that. So here we've got batteries, and there's a light at the end of it. So we're going to be able to see inside the waveguide as the experiments are going on. I also got the end over is a microscope that I attached on to give us the visuals that you were saying before.
Yeah, so you've got it looks like there's a metal probe end on that. Is that that'll have issues in the microwave too, right? Is there a way to isolate that?
I can remove the metal sheathing. It's not actually an integral part of it. It's just
it's just over that. Oh, okay.
It's just over it.
If you make sure the metal's not grounded to your camera and to the frame, everything that hits it right back into the microwave where it belongs anyway.
Exactly.
So
I was just wondering.
I was going to say, have you tried using Lexan with a sheet of glass over that, like the glass on the other side of the?
Guys, I'll be right back.
Like that, That way, if the glass breaks from something smacking it, the Lexan will still protect it, but the glass will protect the Lexan from being scratched.
I haven't gotten it. We may give that a shot. It's a pretty small tip over here.
Right.
I'm gonna try
being able to get into tight places, that would be excellent. You basically got like.
It's not just about tight places. We do have a little USB camera that's at the end of, with the wires that go at the end of a, sort of like a boroscope that you'd use, like a mechanic would use. But try putting that near any RF interference and the thing just goes haywire. This is thinner than a human hair bundled together. And
right. Put the camera far enough away that the RF is suffering from square inverse loss, so that it doesn't have enough energy to damage whatever camera you're using.
Right, and all you're getting is the optical.
Yeah. I'll have to build one of those. I like that idea.
No, you don't have to build them. They sell them on. They used to be using by mechanics, but there's much cheaper ways to do it today.
Right. Well, I've got access to single fibers though for fiber optic.
So. You need a bundle. You need I think this has 10,000 fiber bundled together in this tiny little bundle.
Right. So, and that's what I'm saying is take a bunch of that coiled up and then cut the ends flat. Break the ends flat. After wrapping it to make it single. I like that idea. Even if I use it for an experiment, I'm sure I can find something at least for artistic use.
Todd's asking, do we know where that scope has been? I don't know. Well, I know where it's going to be.
Just clean it with the strongest cleaners you've got. Can't get any cleaner than that. Everything has been in a bad place back far along material timeline. You sure that water that you're drinking hasn't been inside the intestines of a dinosaur at one point?
Here's a close-up of the end. It's not really focusing very well. Also, when I turn on the light here, you can get an idea. There.
Okay, and let's see. It looks like it's logged off. Okay, so maybe he'll come back. But again, we can just do open discussion for a while. So, Mark, you're still working on lab updates? You're still putting stuff together?
Yeah, actually, Tom was in the other room. We have a big update on the gyroscope project, and we also got some more sensors that are pretty much ready to go for this Alzifon experiment. I just have to take the waveguide apart now to install. I got the cam figured out. We got to drill some holes in it to get temperature sensing and visual sensing inside the Faraday, inside the waveguide as the experiments are going on. So we'll get a lot more data, and we'll know what we're doing. Pretty much.
There you go. Oh, okay, and it looks like Mike is back, and he doesn't have. There we go. Okay, it looks like his video is still off.
How about we go to Q&A for David Chester in the meantime, because there was lots of questions for him.
If David is open to it.
Yeah, that's fine. That's fine.
Oh, okay. I just didn't want to. It's so technically complex. It felt like an interrogation. That's the thing that scares me.
Oh, that's fine.
Okay. Well, yeah, we can do that then. So yeah, I guess anybody.
He's a scientist. That's what peer review is interrogation. So that when he passes the interrogation, they go, okay, put that one on the board. That's legitimate. We're going to start following that.
I know, but it's so intense. That's the part that scares me, right? It's like so. Yeah. Well. Okay. So yeah. Anybody with questions for David Chester then? And David, thank you again, sir. And I should let me do the let me see. So option. Sorry, let me get this out. Option Y on Mac or Alt Y on Windows, or the button in your Zoom menu. But Option Y on Mac are all wine windows for questions. And
are you free for a question, David?
Yeah,
I know I asked a long one before. Sorry about that, but it looks like we have another minute. What about stuff like entropic gravity and some of the stuff coming out of that, modified Newtonian dynamics? Just, do you have any thoughts on that, or are you kind of
not necessarily. As far as I understand, a lot of the modified Newtonian dynamics is difficult to make a theory that doesn't have too many parameters, as far as I can tell, for the most part. But that's just a very high level observation. I haven't studied too much extensively there in great detail, but a lot of that's trying to figure out how to get expanding universe type stuff worked out. And then the entropic gravity is certainly interesting. I mean, there's the Bekenstein stuff, and then so I mean, a lot of the Berlin gravity stuff. So that's good work. I mean, they have a description of just even Newtonian gravity. You can get this entropic formulation of it, so that's kind of interesting. You can do the same thing for general relativity, and then I guess Berlin has his own ideas on dark energy and dark gravity that are inspired by his views on entropic gravity, but it's not clear to me if that's the only way to do it, just because he was the guy who pioneered some of the entropic gravity stuff. That's kind of the direction he went into, but I mean, it seems like there's a lot of stuff that could be done with that. It depends on, some people have different perspectives on gravity, like should it be quantized, like should it just be this emergent classical field? Some of the pure gravity people look at it that way. So there's a lot of different ways to potentially look at what gravity actually is. Trying to quantize gravity just to make it like the other forces, but that's just me.
Thank you. And also, real quick, you're talking about in kind of gaugifying gravity, if I can say it that way. Does ADS CFT fit into that scheme?
Yeah, to some degree, it seems. It looks like I forget. I've been trying to figure that out. On one side, you have this correspondence. It seems that global symmetries on one place turn into gauge symmetries on the other. So it looks like gauging the conformal group on the boundary was mentioned by Andrew Strominger at one point. Because the isometry group of the anti-de Sitter space is the conformal group. So I don't know if that implies that there's the same conformal group gauged on the boundary. That's the current perspective I think it seems people looking to, but Strominger was stuck about something I don't fully understand yet about that whole story. But I mean, you could study ADS CFT. I mean, a lot of the ADS stuff, a lot of the supergravity stuff is secretly, well, they know they're doing gauge gravity, but then a lot of it is they'll have the torsion related to the gauge theories that I talked about, but they kind of try to ignore that fact. So just limiting down to Einstein-Cartan theory, which is gauging the Lorentz group. Maybe they, depending on the formulation, they might write it in different ways, but that's all related to that.
Cool, man. Cool. Great answer. Thank you.
Now, David, with some of the comparative analysis stuff that you're talking about, is there a way to use like computer programs? Is there a way to use like algorithms to do comparisons on that? Or is it too tied to kind of like the experimental models and the concepts, I guess?
You could. It would just be a lot of work to set that up. I mean, I got close to figuring out how to get like metric affine tensors in Mathematica, but I didn't perfect the covariant derivative stuff. So yeah, I mean, there's definitely stuff you could do in principle, and there's some code that helps work with some of the tensors because it can get pretty complicated. So do anything, right? But yeah, it'd be challenging to set stuff up, and I don't know. I haven't seen anything too proprietary out there that would really be great. I mean, there's some of the tensor stuff, like I was saying, that is out there that you can help with the tensor calculus, but you'd have to do a lot more built on top of that to get into some comparison like that.
Yeah. I was just curious because I mean, I heard of, looking at this versus that versus the other model. And there was like, I was just thinking, if there was a way to automate some of that, and then you could see kind of what dumps out the other end,
Yeah, and I mean, because there's even varying layers that you can compare the theories. I mean, you get the equations of motion, but then those are just the classical equations. Then there's the quantum behavior. So, yeah, it's pretty daunting to think about. Like, it's like, where am I going with this rabbit hole right now?
Yeah. Does it feel like there will be a big breakthrough, I guess?
Yeah, I mean, honestly, the amount of breakthroughs that are happening right now are pretty surprising. I mean, even just the fact that we're getting papers talking about like Alchemy drives, like talking in these like mainstream theories and finding like, it's like you don't need any exotic matter. To me, that's like pretty awesome. And then, I mean, just even this metric alpha and gravity stuff, like just in the past 2 to 3 years, there's been a lot more papers coming out towards it. And then even like I've been skeptical of string theory forever, but I mean, I'm now more open-minded to it. And even there, like there's a lot of progress that's being made really in all directions right now. There's just so much going on. It's hard to keep up because there's just so many papers being published. There's so much work. And yeah, hopefully one day computers will really just help with organizing all the papers, like connecting, like how we can look through trees of who cited who, but I wish there was like a better tool to like really aggregate all the papers based on the topics, like more clearly. That would be helpful for figuring out, because I mean, all the time people are discovering the same thing in different formulations, or even in the same formulation, they're just not aware that someone else already wrote about it. So there's a lot of work.
Okay, so let me see, Mike, I'm looking at your screen share. Looks like you're on microphone 2. You might want to check your audio settings.
Click that drop down and make sure that there's not another microphone, and maybe that's one that basically isn't connected or something.
Oh, okay, it looks like there's only... Yeah, there's only one mic there. Okay. And so, Mike, you might try test your microphone. I don't see a button for it either. You might try clicking. Maybe try clicking.
The troubleshoot. Yeah, I think that's where the button is supposed to be, and it's already seeing there's a problem. So drop down to over where it says troubleshoot and click it. Yeah, there you go. Any operating system to really save itself, 99% of the time, it just basically makes things worse.
So, back in 2015, I went Mac, and I have not regretted it at all. And Macs cost more, right? But I still haven't regretted it at all. It was worth the money.
Mac, you don't go back.
Yeah, I was on Windows, and I went Mac, and the thing that changed for me, because I've met lots of people in that 25 years who had done that, what changed for me was the majority of software is web-based, and the important stuff that I use, you can either run like VMware, right, or you can do it in a virtual Windows system, or all of my stuff now has native Mac, right? So I weighted devices, so you can do pretty much anything you can do on a PC on a Mac, and that being said, they're moving Mac over to the ARM architecture, so I don't know, that may change things the next couple of years.
So they're not going to move over to that supercomputer technology that's got like the multiple cores. That each core has like 32 gigabytes. That's ARM too. That's ARM too. It's like a souped up cluster of ARM processors. So it's like having a Cray supercomputer.
Yeah, Thomas, and I think that's what you're talking about with the Apple Silicon. They have what was I was just reading about the other day. It's something like 8 to 12 cores. And what makes it different is the RAM is right on the chip, right? It highly integrated, and so you don't have the delays. So even though
you can't change it though. That's the thing, is there's no upgradability without it getting slower. If you add RAM after that, it's got to go through another bus. The ones that I was looking at weren't 8 cores. We're looking at like there were 16 cores per cluster, and there were 4 clusters.
Okay, you're talking about something that's a lot. Yeah.
Yeah, they're just releasing them now for like, because they used to use those for silicon graphics and whatnot to build their super clusters instead of a big computer in a box, and then another one, and another one, and another one. Instead, they just cluster a bunch of these video cards together and use them. So this is just going to burn that into the ground. They're not going to be worthless. They're going to be completely worthless compared to them now, because it'll do one card.
So can I just cut in a moment?
Yeah, go for it.
Mike, sure. Yeah. Have a look at this. If you go down to the bottom right-hand corner and what looks like a mic, a speaker icon, if you right-click on that and bring up sounds, you'll get this pop up. Go to recording. Right-click on there. Okay, I'll stop showing up. Try that. So just to recap, go down to the bottom right corner, follow my mouse pointer. Bottom right corner, right-click on that. Sounds. You should bring up this. Go to the recording tab. Then right-click on it, see if it's disabled. It'll show if it's disabled because it won't have green. Okay.
Thanks. Well, also, if it's green, if he right-clicks it, disables it, and then re-enables it, anything that it was connected to, it'll disconnect. And then when it comes back on, because he has Zoom front and center, it'll reconnect and connect to Zoom instead of whatever it was.
Yeah. Well, guys, let me again apologize for the delay. And in a few minutes here, probably in about 20 minutes, I think Mark will be ready for lab. We can just do open discussion after that. So I am pleased as punch that, I mean, Bob did a knockout presentation, and then David did an amazing presentation. So I'm pleased as punch today, you know. And then I know Mark has a ton of stuff he's working on.
I'll say hopefully by the time I can actually do any kind of discussion about the manufacturing I'm working on, I'll be able to basically at the end take addresses to start sending copies out to people.
So I had something, this is maybe a little tangential, but you guys might be interested in this. I've been doing as kind of a hobby, I got back into doing photography, just landscape photography. And so I have a Nikon, and what I found was, in the past, I was not shooting in RAW mode. I was shooting in JPEG mode because those RAW files are just painfully large, right? And so my brother said, well, look, you've got to switch it because, you know, it's high color. It's, you know, it's going to capture the darks a lot better. And that way, when you put them in Lightroom, even if it's too dark, you can basically boost them up to make it look good. And that's true. So I put it into RAW mode. But the other thing that I noticed was I had issues with shooting in RAW mode in the Nikon. I was able to get some pretty good photos. In fact, if you guys want, I can run you through some of them while we're waiting here.
You know, if you could get that hooked up to a telescope and use it for getting some deep space photos. Man, to share.
Here,
I'll headset, because he could bypass the internal microphone if he had like an external microphone to plug in the jack.
Yeah. And Mike, if you're listening, let me see. Okay, yeah, and he's working to enable. And here, let me share screen really quick. There we go. these are not the highest quality, but what is this one? These are night shots. I don't know if you guys can see that okay or not. Oh, and you know what? It's going over zooms. The quality's not going to be there anyways. But
it still looks really good. So
yeah, this is raw mode. Now, in the past, these would have been. I would throw one out probably 9 out of 10 photos.
So that is the night mode. You mean it's in the sunset mode, like just after the sun's gone down?
Oh, sorry. No, well, actually, the camera was just in. It was set in auto mode, but it's. I have a Nikon Z. I bought it for conferences for work, and the reason was a lot of those conference halls are poorly lit, and so I wanted something that would work in really poor lighting. You can see this is deep sunset.
Yeah, that is a very sensitive optic that you're picking up on that to get that much light and not have any kind of issues with it, especially with the water. You can tell with the water it's not blurry because it's not taking forever to get an extended exposure. It still looks crystal, like the waves look separate. They're not blurred together. That's nice.
Yeah, I was really surprised, and for me the difference was putting it into the calm mode, and I'm has the same thing. But and
you don't have a cheap one. I have one of the cheap ones. The only way to get to the raw mode or to control the compression is there's a thing like it checks something or other that you can load onto the little SSD card you load your pictures on, and it will kind of like hack your camera temporarily until you pull that disk out and reboot your camera, and then it'll go back to normal.
Oh,
they're probably using similar technology that Sony's using, and I think Canon, unless you buy a really expensive one, you're not going to get that mirrorless technology that Sony has developed. So that's what yours looks like it's using, because it's really cool.
Yeah, this one is mirrorless, and I spent the money on this a couple of years ago, and I haven't used it that much. Because I have the issues of blurring, and
that's actually an old secret to get your camera to stop blurring. If you want a dark-looking scene, you overexpose the scene, but then when you're done, you then pull down the brightness and the contrast to make it look darker, and it'll come out crystal clear without looking like a bright daytime shot. So. If you don't have what the technology you have now, I mean, we're talking like old school, whenever you really couldn't deal with that in that way,
Yeah. No, it's and let me see. I had a couple others, and then it also it seems like it handles motion a little bit better. Oh yeah, you can see this my other project I've been cooking. Seems like it handles motion pretty well too. This was I got stuck in the railroad crossing. I said, I think it was probably only going about 20 miles an hour, but still, I was standing right next to it when I got these. So,
can you do video with it too?
Yeah, you can. I haven't used it for video.
I'm just wondering what the fastest frame rate you can set it to when you lower the resolution. Since sometimes you can basically get those cameras to basically give you a slow motion effect. You can capture it because it's just going so fast, slowing it down for you afterwards.
I had some trouble with the water in these. The issue was, well, I don't know. There's a lot of different shades of white, I guess, or shades of light, and
the droplets look separate though.
Yeah.
No, zoom in to really see for sure, but it does look like it's still got it pretty clean on that shot.
Yeah, I have issues with the what would you call it, the resolution. I had more issues with the color, and I think part of it was the green, right? It's like if I was able to get the green, I wasn't able to get the white, or vice versa.
Right, that's the same problem with like either everything is blown out on the moon and you can see the stars, or everything is pitch black in the sky and then you can clearly see the terrain of the moon. So couldn't adjust for both. There was no way to take a picture of both at the same time. The day was too bright, and people
and you can see,
oh, they faked it. It's like
in the Seattle area, you can see that. I mean, it's the middle of winter, right? So I'm not getting any flowers this time of year.
Yeah. That's still a whole lot better than a lot of places in dead of winter. Most places you'd have to adjust it down because everything would be white.
I did,
and the water would be stopped. Still,
I did get seagulls. That kind of surprised me. Right after sunset, I don't know. Maybe they decided to feed or something. Right, there really weren't that many flying until the sun finally went down, and then they just started to. You should
try catching some evening shots of the bats near a city. With like the video, especially because of the way they kind of move like black smoke through the air.
Yeah, you know where they have bats down in Austin. When I went to visit there, they got this.
Yeah,
and then
that seems to be an issue. That Tulsa has that issue too. They have a bunch of subterranean areas that the creeks and waterways had to be completely encapsulated, and they just the openings that lead out of those tunnels will just be covered in little brown bodies during the day from them sleeping in there.
Oh yeah. So yeah, that's been my project last little while. So when summer rolls around, in fact, you know what? I'll put my Facebook up here. Oops, sorry.
It's time for you to go up to Falcon Labs and do some video work for them then.
Yeah, actually, we were talking about that. Yeah, and let me see. I guess we're still kind of an open discussion, guys.
I think this is something we probably need to work on within this group of people together for, like, assistance with computer hardware and stuff like that locally to where they're at. Even if they're not directly interested in this, if you know that they're into computer equipment and they're a friend of yours that's living, say, where he's at, that could help him out with that, I think that would go, miles toward solving a lot of like the problems once we have better communication, because they have better tools, whatnot, or have better working tools due to the help.
Okay, so let me see. Harold has had his hand up patiently, sir. And it's open discussion, Harold. You don't actually have to put your hand up.
Yes, I wanted to ask a question about David Chesson. And what interested me is, since they have been so many studies, and I know there's not a paper on studying planetary gravitomagnetism, etc. If anybody has theorized that there might be a particle related to gravitomagnetism in the same as gravity has a graviton, a particle. Has anyone made that up, investigated that? Any theory, any papers on that?
Yeah, so I guess you would say it's basically a piece of the graviton in the sense that an electromagnetic wave is like photons. I mean, everything's just fields. So you can talk about electromagnetic wave, you can talk about light, you can talk about photons, but they're all just kind of different facets of the same thing. So when you look at that perspective, you could say the gravitomagnetic effects that most people are talking about. There is also a Calabrumond axion. There's gravitational axions, and one might argue that is a different type of gravitomagnetic type of effect, and it seems that's related to torsion. So if you have propagating current, curvature that's like a graviton. If you had propagating torsion, a type of gravitomagnetism, but not the one that most people are talking about. But yeah, I think the one, I mean, anything coming out of general relativity, you can get that from a graviton.
But Heaviside, when he wrote the theory, when he theorized gravitomagnetism, he did not say, there's a particle. I guess back then there was no idea about particle relationship. But the graviton have been made, but it seems to me like since the gravitomagnetism is related to magnetism, and graviton is just plain gravity. What I'm questioning is there a distinction, is there a separation in there? Because it seems to be graviton, no relation to magnetism, but gravitomagnetism does not have a particle. And that is mainly curiosity. What's your thoughts on that?
Yeah, so I guess when someone says gravitomagnetism, it doesn't really have to do with magnetism. It's an analog from electromagnetism, the analog of how magnetism works in electromagnetism to how something similar works in a theory of gravity. And so you could look at the polarization structure of a graviton and maybe break it into a gravito-electric and gravito-magnetic component. But yeah, those are just words. So yeah, they really are separate. Like when you say gravitomagnetism, I mean, it's just all gravity. It's just a focusing on an aspect of the gravity that might relate to something rotational in mind. Yeah, so I think that's probably something a lot of people get confused about when you're like reading all these theories all over the place. When you see the same words used in different theories, it can kind of be a challenge to disentangle them. And I would also just point out that there is the Heaviside gravity theory. That theory is contained in some of the supergravity theories, but it's not like they're associating all of gravity to that. They'll add it as a separate particle. So there was this one paper by Joel Shirk around 1974 where he had a paper talking about an anti-graviton that was associated to something that it looked basically the same as the theory in Heaviside's gravity, but that was adding it to general relativity. So they had this like theory with gravitons and anti-gravitons. And once again, you could go through the same story and say a magnetic thing, but that isn't, it's the same math, as Heaviside, but it's a different theory now because now we're adding that to the ordinary graviton and associating most of gravity to that graviton. So yeah, it gets a little complicated to sort out how all the math and all the words relate to each other, but hopefully that helped clarify a bit.
Well, yeah, a little bit. Thank you very much.
Thank you.
A lot of detail, a lot of good information. It was great. Thank you.
Appreciate it.
So I take a question there. Tim and David, can I take a question?
Go for it.
Yes. Yeah. Okay. I'll just turn on the web camera.
Oh yeah, thanks, Remy. Yeah.
Yeah, I'll just start with you.
Yeah, we're pretty mellow today. Again, I'm not even sure what I'm gonna do when we edit here.
You're mellow, are you?
I think we're mellow. We're mellow.
I was distracted by the news. Sorry, David, I missed your presentation. I came in at the end, but I will catch it online. I was distracted by the news about the NATO Ukraine thing, and apparently Russia are now tit for tat up in the ante and talking about putting missiles in Cuba and Venezuela, and that kind of ups. Anyway, to get back to what you were saying, so I've got the camera at the right angle here. If I understand field theories correctly, they're all a little bit of it's a bit like when you study simple harmonic motion, as a kid, and they say, oh, the sign you approximate as X these field theories, but they're only the linear case, right? Happens to be so works fine for QED. It's a highly linear theory, yes, apart from that very high field strengths. But gravity is inherently non-linear, and also, as you probably went through your talk, because I saw in the comments, you got this. What do you think a proper quantum theory of gravity will look like that includes non-linearities? I mean, are we talking a bit like when you have non-linearities with light in materials, how you can say have photon conversion, you get spontaneous conversion. So you won't necessarily have one graviton, you'll have a sort of non-linear effect where it splits in two. And that's basically the question. And string theory is based on it as well as string theory. Not a lot of people know it is a linear theory. So I'll hand over to you now, David.
Sure. Yeah, that's a good question. So when you say something is linear versus non-linear, it depends on the context somewhat. So I think there's two main things to focus on. First, let's just take classical field theory. You have the field equations for those classical linear, and general relativity is non-linear. And so that's one notion. And then, so you could take a linear theory or a non-linear theory at the classical level, and then you can quantize it. And so the quantization of quantum field theory, this is related to harmonic oscillators. Exactly as you were describing, you get a linear potential that leads or force for a spring, just an ideal spring, a mass on a spring. And all of quantum field theory is kind of based on this idea of simple harmonic oscillators all connected up. And because it was realized that you can have the quantum harmonic oscillator gives you like different energy levels where you can associate a particle with a different energy level, and the energy levels have the same gap between it. So you could say I have one part to quantization of the field in that sense, and so you get that you get these these quanta, these particles in that sense. So obviously there are issues perhaps with quantizing gravity that everyone talks about. Okay, but let's see. With quantum electrodynamics, there's still problems when we don't actually know how to compute quantum electrodynamics exactly. Or non-added. This was a paper by Pawlowski that came out a couple of years ago where he actually added space-time torsion to electrodynamics and found that he got a finite Bayer charge. So it removed the infinity problems. It's more philosophical problems with quantum electrodynamics. Like we can do the calculations in QED, but it seemed like it required an infinite amount of energy just to create a single. Turns out if you add gravitational torsion specifically to QED, you get a finite self-energy. And so no one has tried this with gravity yet because it's so difficult. This result came out 2 years ago, but to me that's encouraging because if we apply torsion to gravitational theories, that might help clean up some of the infinity problems in gravity. So that's been a conjecture of mine for a decade. I just have found the time to actually calculate because that would take about a year to do.
It's not just fair as well because they reckon that a theory of quantum gravity will solve a host of other problems like wave function collapse. Some are looking for non-linear Schrodinger equations and so forth. Yeah. So you could just to wrap it up. There's one final thing you could do is to consider non-linear procedure that is using, instead of ideal springs for our quantization of these fields, you could imagine some nonlinear spring, and you could try to construct some quantization procedure from that. And people have looked into this and initially tried to argue that those theories are problematic, but it turns out, and this relates to non-locality, it seems, in some instances, and
people are starting to slowly get better at realizing that maybe it doesn't work out nicely. So that'll probably take a few decades to really know. So there's different notions of linearity and nonlinearity. First at the classical field equations, and then when you quantize your theory, let's say you're building off these simple harmonic oscillators that are linear springs. And so in one sense, there's not necessarily a problem with applying the quantization to nonlinear theory. GR is finite. You can do graviton scattering at the first order correction and get a finite result. And actually, they just figured out how to get the second order correction for 2 loops in just pure GR as well in the past, that was like 2018, so like 4 years ago. So yeah, I mean, you can make sense of quantizing nonlinear theories, and then you could also very, very sophisticated.
Yeah, it's a tricky one. I mean, the maths is horrendous. It might not even be humanly possible without the assistance of computers, a bit like computer-aided design. Yeah? Okay.
Yeah. And guys, if I could jump in really quick, Mike just IM'd me. He said they've tried everything they can. They can't get them again. And then Mark Sokol, actually, he's on another call. So we can just continue with open discussion as long as you guys would like. You don't have to raise your hand. David, if you'd like to answer more questions, that's totally fine. But
yeah, I'll stick around.
Okay, yeah, and other than that, I think we're just mellow. Again, guys, let me apologize for the technical issues.
Jumping in at random, guys, back on Bob Greene, the first speaker's talk. It looks like transmutation is kind of in our interest set here, even if some of us take a real hardline view as far as it being very likely, but you could maybe kind of spitball Einstein-Rosen bridges to facilitate photons in acid compounds and transferring them directly into the nucleus to upgrade elements or stuff like this as an application of gravity theory.
Yeah, Bob has so much material. So the interview that he was referencing, that was Stanislav Adamenko from Proton 1. That was me back in 2006. And I mean, Bob took it so far beyond what my interview was. One of the things that I remember from that, and this was the electron eating. So they were using a what was it, like an ion probe, right? And one of the things that he mentioned was they created what he called a black spot. And that was all they described it as. And they said they just kept pumping ions into it, and whatever they dumped into it, it ate. And so I think that was that he mentioned that in the slide. When I get the replay up for this, you can go back and look at his slideshow. But that was one of the takeaways for me was, they almost described it. I guess it's probably a bad term, but almost like a mini black hole, right? Like whatever they threw at it from the probe just went right in and disappeared. They had no idea what it was, visualize it. And they were able to visualize around it, and it was just this black spot. He was like, well, I don't know, but we just kept pumping energy into it, and it just disappeared. So,
yeah, he had a lot of interesting things. I'll have to look more into a lot of the stuff he was talking about.
Yeah, he's got a lot. I mean, Ken Shoulders had tons and tons of stuff. And then Jack corresponded all the time.
Yeah, I keep hearing that name, Ken Shoulders. I haven't looked into it. So what did he do? What's like the main?
Ken was the EBO guy. He was he was the one who started that, and he worked on that for years. And then he like him and Jack were, well, Jack's list, right? So, I mean, they corresponded on Jack's list for years. I used to get CC, really good friends with John Hutchison. They used to correspond all the time on those lists. And then when Ken passed away, I guess Bob kind of took over his work. But Bob has extended things so much. I mean, it's in a way, it's almost unrecognizable, I guess.
Yeah.
Well, I'd say that's one of those things you mentioned. This guy, if you can get a hold of Ken LeBrun, he apparently like reworked a bunch of the math for radar technology because he didn't like the idea that there were fudge numbers. You had to basically take tests and then, use those test results to plug in a number, and you didn't know what number you were going to get until you did the test. And he was able to basically work something out so that when you change frequency and whatnot, you could use the formula, know what it was going to do. And I don't think he has the, I guess the schooling to build his own theories, but he seems like he's pretty good at basically taking a theory that you can't quite figure out how to get rid of that fudge number and figure out how to do that, as long as you can get some tests to give him a chance to take a whack at it. Like he was basically, taking care of all of the radar technology for fear of going to prison, so.
You say LeBrun, Lebrun, or?
Yeah. He, if you want to look for, his history on that, like finding him on LinkedIn, just look for revolution-green.com. Because as far as I know, he still holds that address, but he hasn't been able to basically, but he started that up because of all the nonsense that was going on with PezWiki and a couple other sites like that, with the people who were running it having some really bad stuff about them coming to the surface and finding out that they were running a bunch of scams and whatnot. So, they tried to start something to bust free of that and have their own forum where there were no scams and nonsense involved in it, just raw facts. So they were testing things out to find out for sure, and then giving an honest result answer on that, what they were testing, instead of having to, just go by somebody who developed something that wanted to basically make it valuable, whether it was or not. So they were, getting bad results sometimes. So he worked with Mark Darth Danzy for quite a while. That's the guy that got him to actually go ahead and set the site up. In fact, that's what they call him in the alternative energy community, because he shows up with test equipment and whatnot. Suddenly nobody wants to talk, or when he tests things, they end up finding that, what's this wire here that nearly shocked me to death that you guys had hidden under here, He basically just exposed scams like crazy, but he wasn't trying to expose scams. He wanted to find an answer. He wanted a real answer, and he always showed up hoping this would be the one, but it was never, So he ended up getting that black mark on his name of Darth the Danzy. He's going to come in, like the Sith, and cut you down.
Well, guys, so Mark Sokol just said that he is ready.
Yeah, we're ready here.
Okay. So let's go to lab updates now. Let's do that. And again, my apologies for the technical bumps, but I appreciate everyone's patience. So go for it, Mark.
I'm going to be doing this on my cell phone just for ease, because there's lots of different components in different rooms. Where we left off last was, I mentioned already the fiber scope over here. We tried hooking up a regular camera to it, didn't get very good resolution, and the image was too small. So I got these USB microscopes off of Amazon and found a way to hold it in place. Each, you guys can all see that in the Falcon Labs computer. It's giving you a live image from that. And here it's pointing toward the screen, toward my phone right now. So this is going to be going inside of the waveguide chamber through this hole in the corner over here, and it's going to be pointed toward the sample, which is going to be housed right about in the middle. And
Another thing we're going to do as to what's going on inside the sample chamber. Another thing we wanted to do is get thermal readings, because in the first initial test at 200 watts, we started melting our test holder. Things were heating up pretty fast. So thanks to Jeremiah's friend Patrick, he gave me this idea to work with Germanium lenses to basically put a thermal imaging device inside the chamber. This is to make sure that it works. I got these from a guy in Albuquerque. It's made out of germanium. It's a little window. There's no optical change over there. There's no lensing effect on that, but I did manage to crack it when we were installing it in the many prototypes. That's what these are. These are prototype cam tests until we finally got it perfect. And try to keep it as thin as possible. And the readout comes out on this scanner over here. And you can see paper underneath is at 24 degrees centigrade. So that's like room temperature. So that's going to be installed on the side of the chamber, probably somewhere around over here. We're going to have to take this chamber apart now because I have to CNC it from the inside. So that's a milli saucer project, 42 millimeters saucers, and we're using this die system over here made of 6061 aluminum, and we're pressing out little sheets of aluminum out of it. And Tom, my assistant, managed to make a whole bunch of these little miniature flying saucer disc shapes. One of them is an ounce, 31 grams, whereas these weigh around 1.5 grams. Another interesting thing about thermal imaging is on highly reflective metals like aluminum or brass, we are going to need something to actually look at to get the thermal image. So we're just going over it with a Sharpie, and that's going to be our thermal imaging target. That's working pretty well. Now, moving forward, in the back of the shop, we have a gyroscope system that is very near completion. Tom Butler over here is working on the code.
Yep. I was using the old servers, so when I was putting the code in, and then we wanted to take at a brick install on.
Is it basically we want it fast one way and then slow back the other way as the brass is spinning.
And those are the servos that are going on these devices. They have motors inside the flywheels or the gyroscopes. This is for the Cambell-inspired gyroscope inertial propulsion device. I think that's similar to what Mike was about to talk about, with his technical problems with the microphone, but this is a similar device that we're very close to completion. We should have 3 complete units here. I saw you were also
the motors.
You're also contacting Pololo for technical support.
Yeah, yeah, they're great. They're great. Talking to a guy, Brandon, through email, and they're very helpful. Absolutely, highly recommend.
Okay, this is the micro server that we're working off of.
12 channel.
It's 12 channel, but we're only going to need 6 of them. 2. The servos, 2 servos running in opposition on either end. So if one servo here, one servo here, here's a more complete unit. But we're first going to test it without hooking everything together, so we don't hear that wonderful gear churning sound. That
don't want too much crunching going on.
Yeah, we don't want to have too much crunching going on. So now we're just, I guess, just hours away from complete.
Yeah, it's thinking this needs a little more we can should be ready to go.
Okay, going on here at the lab. Inside the Faraday cage, not much has actually changed. We do have some more shielding materials coming in to help shield the infrared sensor. I'm kind of concerned about how this is going to work out with 200 watts inside the chamber. Germanium should shield it pretty nicely, but it's only so we'll see what happens with that. But that's pretty much where we're holding over here at the lab.
Awesome. So that's your update.
No, pretty much for now. Yeah. Any questions? Any comments?
I think we're good. Well, should we go back to open discussion then? Let's go back to open. We'll go back to open discussion. I will the door evening.
Hey, I got this article I wanted to share, if that's okay.
Yeah. So I guess the only thing that I should probably mention is, and I would caution everybody about when you're playing videos, every now and then we run into issues with copyright stuff, videos with sound especially. So just be aware.
Yeah, this isn't
Jeremy Reese was playing BBC. He was using some examples from the BBC, which is okay because it's on YouTube. He's just playing YouTube, but then Google blocked it as a re-upload. So
what I have here is an article in physics, and it's titled "Using Time Dilation to Measure Curvature of Space-Time." Has used time dilation in an atomic fountain to measure the curvature of space-time. In their study reported in the Journal of Science, the group used the fountain as an interferometer to measure atomic wave packet changes that corresponded to phase shift. The atomic fountain created by the team consisted of a 10-meter tall tube. There was a ring securing a piece of tungsten. To use the fountain, they fired lasers beneath single atoms, pushing them upward, and other lasers fired down from the top to stop them. A third laser pulse captured the atom as it reached the bottom. In their experiment, researchers pushed the pairs of atoms up the fountain and measured results phase shifts as they traveled up and down the fountain. Phase shifts were initiated by stopping atoms at different distances from the tungsten at the top of the fountain. The setup demonstrated phase shifts due to time dilation, in which is described in Einstein's theory of relativity. Time passes more slowly closer to massive objects. In the fountain, the atoms that rose higher moved closer to tungsten mass and therefore experienced more acceleration, which led to a time shift between those and the atoms that did not rise as high. The experiment also showed that the Aronov-Bob effect also applies to gravity, as a magnetic field inside of a cylindrical container can impact particles that never make their way inside the container. In their atomic fountain, electrons take unique paths up and down the fountain, which were forced into superposition. And despite the magnetic field in the chamber, no magnetic force was exerted on them. But there's still evidence of a magnetic field shifts. So I thought that was interesting because it shows that gravity actually slows time to the massive object. And that was my share. Thanks.
Jeremy, how are you handling the snowstorm? You're right there in the epicenter of it.
is a nightmare here right now. I was out shoveling for 5 hours and I barely got like a mile down the road, and my van just does not do good in the snow. It just kept getting stuck.
Yeah, that's why you started the stream a little late today. Got stuck out there.
Wow, I was not even aware. It's 64 degrees here, and it's going to be warm the next 4 days before we get another dip down to sub-zero range.
So one other thing too is I wanted to mention for you guys. There's this that material that Hal put off was showing off, the Linda Moulton Howe material that was like the terahertz wave guide that was bismuth and magnesium. I contacted a couple metallurgy contractors that make like specialized metals, like specialized in metal thin films and stuff. And I'm going to see if we can try to get a sample made to those exact dimensions, like the 3 microns bismuth to 150 microns magnesium or whatever it is. So we're trying to, I'll see what they have to say about that, because there's a lot of claims going around out there that that material would be hard or impossible for humans to make or whatever. So yeah, we're gonna try and see if we can hire a company to build some of that stuff for us. And then,
What did you say? Jeremy, if you can make it fit inside this square, we can stick it inside inside the experiment and see what happens with dynamic nuclear orientation.
Yeah, that would be cool. I'd like to actually. Does a ping pong ball fit through that square? Because I'd like to spray or some of these other depositing, techniques. I'd like to see if they could do it on the surface of like a ping pong ball, so we can make like a sphere that was, coated with this material.
Smaller than a ping pong ball. Like, I don't know the width.
A ping pong ball is a good standard size though, and Keshi is also used those in theirs. So I would suggest going with that, Jeremy, as a good size reference.
To run it in that experiment, it would need to fit.
How big is it? How big was their sample, Jeremy?
I have no idea how big their sample is, but we're just going to try to. There's specifics in a video I have. Let me see. And find the video.
Was it real thin or was it pretty thick?
Hey guys. Can I ask a question? It's just a bit of a strange one in the news. I just dropped a picture in the chat window. Does anyone believe in exopolitics? Exopolitics, i.e. those up there watching down on us. Do you think they'll intervene this time and put us in a place with our technology? Again, isn't it? Yeah. We're talking about the standoff. I'm just throwing in the wild card. We're talking about the standoff between the West and the East, the West and Russia. Russia apparently are going to up the ante, and they're going to put missiles in Cuba or Venezuela. So it's just it's building up, isn't it? Because it might be it. Apparently, those upstairs, they had the technology to convert it all to iron 56, convert the plutonium to. They apparently did that at Rendlesham Forest, which is about 100 plus miles away from where I am. And just a few other places around the world, they fly over bases. And make the technology save us. That's just a question I'm asking.
You posted a picture of something, right? Yeah.
Article that they plan on military hardware into Cuba and Venezuela. I asked that we not talk about politics here unless it relates to UFOs. So Remy, flying to this technology to alternative propulsion.
Oh yeah. Yeah, because politics is especially when we started, right? The golden Trump administration. Yeah. Politics is a hot button issue.
I'm thinking more about technology. I mean, do you think they'll save us? Do you think they'll save us this time from ourselves?
I think we're.
I don't think so.
I think we're going to save ourselves.
You can't do anything about it. Just keep working on what you're working on, because
exactly.
If we keep busting to get to where we're going.
Exactly, it's law of attraction.
That might be the solution too. Instead of developing work drive, they may not be willing to contact us until we literally
stop killing ourselves.
They're
exactly.
waiting for
that. Wait till we're no longer fighting with each other.
We have to stop killing ourselves before we're allowed off, and it's all about the law of attraction. And the more you focus on the negative, the more the negative.
The law of attraction is very real. The more you think of negativity or bad stuff, the more you're going to attract it to yourself.
I think you should probably look deeper into the parasites that they think are linked to schizophrenia, which comes with hearing voices that you can't stop for some reason. It's like that's kind of what a nanobot that connects you to other people have nanobots, so you can hear their thoughts would do,
Yeah, it's karmic delusions.
Well, as I say, Toxoplasma gondii, when you look at the archaeological history on it, dead ends, where there was basically a meteor that hit South America, and there's a parasite that has a dead end somewhere near a meteorite impact in Africa that is the only other organism on the planet that shares similar DNA. They don't seem to be connected to any other pathway, anything. And that the parasite in South America, when it hit, that's when everybody went from doing brain surgery and building those magnificent structures and whatnot to, killing each other and sacrificing children and drinking blood. And that would, if you suddenly introduce the capability of something like that without letting somebody know what it is, that would terrify somebody. I mean, if you knew it was another person thinking, then it wouldn't be anywhere near as terrifying. Is worrying that it might be a demon trying to talk to you,
Yeah. Oh, now we're getting into religion.
yeah, I know.
Well, this is based on biology, though. I mean, we know these parasites exist. We know they have the ability to manipulate behavioral patterns, because rats who are infected with it will no longer have a fear of cats, and they're attracted to their urine, so they'll hang out places where cats are basically living. And get eaten than anything other than a feline. Once it reintroduces into a feline, its life cycle is reset, so that basically the whole colony won't just die. Every generation is just a baby, Whereas in a rat, they
sounds a bit like Stargate.
Mark, let me ask. Mark, is it okay if I make dinner for the dogs and all that stuff? So okay.
Ooh, yeah, dogs are.
Yeah, well, it's that time of the night, right?
I've been steak.
Okay, so let me do that then.
My dogs only get dog food. I get them the premium stuff, but Jeremy's kids came down this last weekend and they were feeding it for crap, and that's what came out.
And it got it from the cat food, because the cat food it's all full of carbohydrates.
Yeah.
And meat stuff. So now I have to give my cat 2 insulin shots. I got to give it a shot twice a day. And what I feed it is I buy mackerel, canned mackerel. And then, so it's like pure meat. And then there's a food supplement called Alchemy. I add a teaspoon of this in the can of cat food, and it's lowered the cat's blood sugar, and it's also better for the cat.
And the same, Michael. The same is true for dogs. I think. I mean, I don't know if they lie. I know they don't have the same quality standards. Another thing I know is the meat that they put in dog food. Basically, they take it up to a high enough temperature for a long enough period of time that the protein breaks down. It's no longer identifiable as an animal, to be honest. And I've read that before. And so what I do with my dogs is I boil chicken every day. But I had the same problem. I've had 2 rescue dogs in the past that were on dog food, and they both ended up with diabetes because it's so loaded with carbs.
Yeah.
It's cornmeal. It's like 99% like grease flavoring to make it taste like meat or fish.
Yeah.
And with a dog, it's a little easier to do that with because dogs they're not even omnivores like us. We used to be scavengers, which is a next step of beyond being an omnivore that can not only eat anything, plant or animal, but it can eat rotten plant and animal without being harmed by it, right? But with a cat, it's all smooth intestines. It's only built for eating meat. It's not made for eating all these plant matter that basically end up rotting in their intestines, and they can't, it just ends up binding them up.
Bad. It's really bad.
Right, and like I said, think about the vegetable problem. Well, now imagine a grain problem that requires even more. I mean, the cows eat grain. They also have multiple stomachs.
Yeah, and I think a lot of it with dogs, I think a lot of it comes down to I think manufacturers are disingenuous about how much carbs, because when you read it, it's like meat, but
should have a warning label.
Right. They don't need the nutrition label because it's not for humans. The FDA hasn't gotten involved.
Not fit for human consumption,
Well, and they say that on dog food.
So
they say that. Yeah.
It's really criminal what they're doing. If you think about it, because they're killing our pets and we're poisoning our pets and we're thinking we're helping them. The other thing that I think is interesting about this pet food thing is there are a lot of places there are shortages of pet food because a lot of it's shipped from China. And so, like in California, there's a lot of
that's an issue because they found a lot of the Chinese food that was coming in, both formula and for animals, had a lot of plastic that on testing looks like.
Guys, can we get back to
yeah. Let me go and do that.
We're here talking about dog food.
Okay. Yeah, the editing on this one will
My
be interesting.
dog is a demon. Swear to God, my dog is a demon.
Oh, you missed the boat. We're not talking about dog food anymore.
Hey, man, sometimes you have to decompress to have a good
trouble with my
conversation.
pet. Like,
I'm still counting for the toilers.
Okay.
I'm still going to do it. I'm looking through. I have the Uline catalog. I want to flip to see if there's something close, and then I could refer to them to and just I still have to do a lot of cross comparison, but I haven't forgotten it. I promise.
Okay.
So I'm telling you, it's one of the coolest things. You're like creating a system that's real, medical, law plans, like real. Yeah. So good job.
Thank you. Yeah, the idea was great. It's the implementation. Willow was, when she was here at the lab, was planning on putting in a shelf system to allow us to access the boxes that are behind the other boxes. But it's a little bit more complicated to implement than just the idea alone.
I mean, the more I know, the more I understand science, the products do I want to use for this stuff, like they were, it's a magnetic field, and these things, I was there, these things flip, like stuff, just moves. I don't, cool, I'm telling you. So you have to know, what you want to use as the container, I don't know, maybe I'm thinking too much of it, but, we're talking about quantum stuff, so a quantum level, that it still matters, you know? Like,
Maz said online, Maz said on the YouTube link that we need to Lulu in every team.
Listen, I had so much fun. I had so much fun. I learned so much. You know, I heard of this stuff, but I never like saw an action. Like, how do you get a team? Like, how do you have energy flow through a team? And everybody, like, you know, it has like on the dot, but it has to be a homogeneous team in order for the energy to flow. I was constantly like trying to any interference, anything like that drops on the floor or anything that's out of place, it's not aligned right, it's gonna somehow like interfere with the energy flow, you know, of the space. And so it affects us, you know, as humans. And, you know, we're all, if you want to call it engines, to be productive and to work together and all of the stuff. There has to be a frequency. But if we have a lot of peripherals and a lot of little things where the energy is bouncing negatively, then, you know, one of us will like flake out. So, you know, I was trying to get that flow. You guys, I picked them up. Those were causing like interference in the frequency of propagation, energy flow. You know, for us all to be connected all at once from different ports, different, you know, cameras, different computers. You know, even in our physical efforts, we you know, we give energy to each other. We like, you know, when everybody's excited about something, we back and forth, and that's a good thing. And, you know, that's how you build things. That's how you grow things. That's how you make a team. That's how, you know, when everybody understands each other just at a whim. Like, you know, not you don't have to give specification. And you know, like, I mean, I didn't know a lot of these things, but I learned. You know, the more I'm here, I learned like more, and I'm like, my gosh, the possibilities. Like, my gosh. Yeah.
So we got some new people here. Abraham, are you new? Oh, we can't hear you. There was some other new people as well that signed off already.
I'll say, where's Jeremiah?
Jeremiah, pretty much. You haven't heard from him. Has anyone heard from Jeremiah?
I hope he's okay.
Yeah.
Join the technicians. We need you to join.
Smart people, like everyone's smart. What do you think is the common denominator between all of us? I mean, I was thinking in terms of mathematics and things like that. We have to have some common denominator.
The common denominator between people who are interested in alternative propulsion is that they're also interested in psychedelics and exploring the the psychospace.
Consciousness.
Yeah. The study of consciousness and the study of alternative propulsion had this weird, parallel.
I have a lot of theories, but I don't know how to prove it exactly because I don't have like the machines to do it. But according to the fundamentals, if space holds memory, then wouldn't like when Earth rotates, like somehow when somebody thinks of something, when the next person in that order of rotation will think of it too, because if it's something that sparks a higher
I don't know if it is where somebody on one side of the world is discovering something independently from somebody on the other side of the world, and they happen simultaneously.
Light bending. Light bending.
The synchronicity that happens is more than just coincidence. We found that with many discoveries, and the co-discoverers didn't know of each other at the time. It's not like they were working together.
Did they have
critical mass.
Common denominator, other than at the same time they do the same thing.
Critical mass consciousness and like the 12th monkey sort of, I think, is what
I
it
was
kind of is.
thinking, let's say, more of the nucleic acid on a DNA level. Or I was thinking of the synchronicity of, let's call time, like birthdays, or major events that happen, like that caused a lot of energy outbursts, from the planet. Made a huge impact on the evolution of humans, like, scientists, like, the Einstein, Tesla. Yeah, and we can go back further, like,
something you might try.
And so on. Yeah.
Something you might try is to look at it from a completely alien aspect of how would you go about developing the technology that we have that we find absolutely necessary if you lived in a completely different environment that you evolved from, like on an aquatic world. They wouldn't be able to just develop fire. So there'd have to be a different chain and path for them to do all the things that they do. And by looking at the differences, I think you begin seeing more of the similarities between humans and why we are arriving to the same conclusions so often, even when we're so completely disconnected. Because as a world, we're advancing at about the same speed. So we're working with the same building blocks. And therefore, when you have, billions of people, obviously two people doing the same thing is not really going to be that big of a stretch. Right. So.
Would there be a middle line, though?
Well, here's a way to look at it. How would we have developed if we had 6 fingers? Meaning that when you count your 2 hands together, you get 12, not 10. So therefore, all of your math would be based either on 6 or 12.
Babylonian.
Instead of us being to decimal.
To account for 2 invisible ones, because everything works, all mathematics works on, time works on the idea of 12,
well, that may be why pi doesn't divide properly into an even number, where if we were using a different numeric scale, we may be able to get a definitive number that's only like, say, 3 decimals.
Okay, how do we divide pi?
Circumference.
We divide
or
it by
it's just one geometry fractal.
24 time zones. But is it really 24? Are we maybe maybe it's less, but we're adding those 2 just because those 2 with the curvature, we have to, to account for space.
Well, and here's a question. When we're drifting away from the sun, so that means that our path around the sun is getting further. So are we slowing down the rate that we're rotating or accelerating the rate that we're going around the sun in order to make sure that numeric value has remained the same too? And how would that change if something were altered on that so that our rotation were different? I mean, look at Venus. Venus spins backwards.
We evolve.
Right, Venus spins backwards. So what would that change?
It doesn't matter. We're the conscious beings. We create a ripple effect, and everybody aligns to that new, energy field.
Right, and what I'm saying is, how would that affect their progression as a species living in a different event like that? And
they're only detectable through infrareds and the things that the human eye cannot perceive. Or we're talking about things that are detectable with machines, not human eyes. If that's so, then we send signals of agreement or not. If we get a signal back, it's agreement. So we know
Right. What if they see bees are able to see ultraviolet spectrum we can't see? How does that affect their evolution if they decided to be, if they were given time to evolve to where they could start developing technology? What would
aren't
they do
they already evolved more than us? Well, you're just saying that, how would that they're already evolved more than us? What if that actually is the starting point where, everybody evolved at, with the wind, and that's the they're gonna probably acquire a new ability with the motion that we start from here. I mean, think about it. I mean, it makes sense. We're the green planet, or the pale blue dot. But no, really, we're the planet that has life, and visible life, and reflective life. Our
Stephen actually has been raising his hand for a while. one of which can chime in. We just ask that you turn on your camera if you're talking, so everyone can see who we're talking to. Hey, Steve.
Hi, I'm Steven. Bob invited me here. I'm a donor and guess a thinker, but not really a experimenter. But one of the things I was interested to find out from you is who is a maker in the key areas, like using the needle cathode, sonocavitation, and collecting energy that way, who's spinning magnets and collecting energy that way. And apart from those three, what have I missed? And
I'm working on those
if
exact
you're in those areas,
experiments.
tell me what you need to advance.
We all are.
No, we're not all. There's a couple people working on sonic cavitation. Titus Yano's on science. We have a high-speed camera to try to get scanning waves in space. Over here at the Falcon Space Labs, we're working on quite a few experiments with dynamic orientation. Basically, we're trying to get the subatomic particles in the core of the atom to spin in alignment, and that theoretically should provide some sort of gravity shielding or inertial mass shielding effect, which could explain how point saucers operate. We're also working on gyroscopic systems a few times. Titus Yano's also tried that. Jeremiah Pop has also tried that. Seen some interesting results. Nothing more than 5% thrust to weight ratio so far. But really engineers in the lab. They're kind of hard to come by, and as you can see, this is a very diverse group over here. A lot more theoreticians than there are engineers. And generally, for every 100 theories, there's one engineer that's actually trying something, and that engineer has his own theory. So, Michael Coyne.
I'm working on a nano gravity, basically using a disk. I have like 4 patents and a 5th one pending on this. What it does is it takes nano bumps and nano pits on the surface of a hard disk drive, and it produces a different kind of magnetism. It's called graviton magnetism. The absence of matter on a spinning object, essentially. And it's something I measure using a thing called a giant magnetoresistor head. It's a little tiny resistor, nanoresistor, but it's made with a special material that's sensitive to changing magnetic fields. And then I also measure it with a little force sensor. It's a slider, and essentially I've already got patents on that. What I'm working on is taking the little nano bumps that are in the center of your hard drive and mapping them out and using them to create private keys for private key public key pairs for basically for making a mutable cryptographical data exchanges, essentially cryptography. So that's what I'm working on. Thanks for your interest. It's appreciated.
I have a question for whoever is capable of answering it quickly on top of their head. I did a little test, gravitational shielding today. In which I think that graviton, when they're traveling through the Earth, they're going to lose energy because they're going to transmit their energy. They're going to lose energy because the atoms of the Earth are going to gain energy, so that there needs to be a balance there. Gain kinetic energy by moving in the opposite direction. activity of the sun would attenuate during the night as compared to during the morning, and did the measurement of the.
Say that again about the thing, the difference. What the gravity is different in the night and the day? Is that what you're saying?
Yeah, the gravitational acceleration, the assumption that would be different because the sun is.
Is it the lunar tide? Is it because of the lunar tide? Like water shifts to one side of the Earth versus the other side of the Earth, and so that makes it.
No, I get what you're saying. You're physically closer to the sun on one side than the other, so the gravitational pull should be different because it's. That makes sense. Your question.
Yeah, this effect that they found with coronal mass ejections. That is a coronal mass. So basically, there's two phenomena that occur on the sun. The first is called a solar flare, and a solar flare basically pushes photons out into space at the speed of light. And a solar flare takes approximately 7 minutes to reach the Earth. On the other hand, there's this other phenomenon called a coronal mass ejection, and what that is there's a basically part of the sun's surface is thrown out into space. It's what's called a proton flux. And it actually produces a gravitational wave of protons. It's a 1 million mile wide wave, and it comes towards the Earth, and because it's traveling at the speed of 3 days to hit the Earth. And when it hits the Earth, it actually causes the magnetic field to go whipping around, and it can actually cause blackouts because the power lines will get charged up and actually can cause it to overload. So, and that's happened before a lot of times, most recently in Canada. The really Earth, when there's certain radioactive materials that when a day or a day and a half before the coronal mass ejection, the radioactive decay rate slows down for these radioactive elements. Okay, and so actually the gravity of what it does is this proton flux hitting the Earth. This affects the rate of radioactive decay.
Yeah.
And so, and they can measure it, and they can measure it over time, and then they'll get the time will slow down. But what's cool about it is it happens. It's like projecting into the future that. A day and a half. And if you guys are interested in this, if you go back to the April 14th APEC, when I did my presentation, I have a video about that in my presentation that you can check out.
Okay. Interesting, I'll check it out. But your name is Michael Floyd?
Michael Floyd, yeah.
But just to what I was saying, at 8:30, I measured it again tonight at 8:30 p.m. And I was expecting a change, obviously, because the sun would be kind of aligned with the Earth. You would add the gravitational acceleration of the sun and the Earth. But it's kind of funny because I get this morning, I had a standard deviation of 3.7 times 10 to the minus 6 G. And I think 30 tonight, I had a standard deviation of 3.3 times 10 to the minus 6 G. So I had a week. gravitational.
Okay, and where are you located physically?
In Montreal.
In Montreal, so you're at what, 25 degrees?
Yeah.
So yeah, you gotta take into consideration your relationship to the equator, right?
Oh yeah, that's right.
And also the planet precesses. Remember that it's not going in a circle like this. It's up on the present of the Earth, couldn't it?
Okay. So I'm not properly aligned with the sun and get this.
Well, yeah, you're at an angle.
Yeah.
You know, if you're in the northern hemisphere, where I am in California, I'm at 15 degrees north of the equator.
Yeah. Whereas in Los Angeles or San Diego,
it's 13. 13 is basically Riverside County is 13 degrees.
Okay.
We have a new speaker here, whimsically ambitious. What's her name?
Sorry, it's Jared.
Hey, Jared.
Hey, how you doing? Hey, can I have a little show and tell for a minute here? I've been building a gravel flyer, and I think I've got some good principles on how it's working.
Cool.
All right, so far what I've got going on, it's pretty much built, but I was in the process of finishing the whole circuit. Turns out I don't have a 47 k ohm power resistor. Shucks, gotta wait 2 days now. Anyways, I was gonna say, I think I've got some good ideas on some of this working principles. Jeremy has talked a lot in the past about shape memory alloys, like nitinol. These are things that basically work like springs when they're in one phase, one crystal structure. It's like a cube, and then it gets stretched to the second phase of a rectangle, right? And then when it snaps back through a temperature or a voltage change, it's like a spring. Boing.
Torsion.
So, say again?
Torsion.
Torsion, yeah. Well, yeah, I don't know about the torsion stuff. I haven't read up too much on it, but for the Graviflyer, I was testing because y'all were doing his magnet paper on there. I was like, oh, I should start testing with that. And so I did. The strongest part of the magnetic field is very narrow. It's only like 1/8 of an inch wide, but it's right around the circumference of the magnetic spinning plate, which comes out to a surface area of about 3.5 square inches. So aluminum, it so happens, I found this one good research paper on it, aluminum can display these exact same Martensite, rectangular, austenite, square properties when it is subjected to electrical, magnetic, and acoustic oscillations at just the right everything, right? And this is probably why Alexei had so much trouble getting everything tuned just right. It's because he's trying to get all these different forces to be stretching this thing and then letting it snap back and dampening that snapback at just the proper moment to get acceleration. Similar to Woodward's Mega Drive that has the piezoelectric, is like tiny amounts of thrust through nonlinear damping. So that's basically what I got so far. Is I think the Graviflyer is changing the phase of a very narrow region under the strongest magnetic field, strongest electric field. And that was the other really beautiful part I found was the ultrasonic welding techniques that are out there. Basically, you take a piece of metal and you vibrate it about 20 kHz, and you can weld it together with another piece of metal. Well, the paper that I was reading about changing aluminum's austenite martensite Bain transformation there was that it has to operate right at about 20 kHz, which go figure, that's what Alexei's ultrasonic piezoelectric was operating at.
Jared, where are you located?
I'm over in the Northwest.
Northwest.
Oregon, okay. Yeah.
Oregon. Can you drop? We have a private WhatsApp group for people who are actually building Graviflyers.
Oh, sweet.
Yeah, it's sort of like a show and tell, daily, nightly, whenever you're working on stuff. We actually have a CNC machine over here, and I'm about to cut out some discs for people, get them perfectly balanced. So yeah, if you need anything, any help from us, we'll be glad. to help out. There's quite a few. There's actually a kid who's working.
Charles.
Yes, Charlie Crawford.
Yeah, I've been talking. The third. I've talked to him a few times about different questions that I had about it, but he's really busy, so I try not to bother him as much as possible. Although it's almost daily that I want to.
He has to take care of Charles Crawford the Fourth too.
Yeah.
Stephen, getting back to spinning magnets. One thing I noticed about them, and Jared, you might notice this as well, is that for some reason they become very attracted to magnetic north. It's like you have it off, it's as attracted as a regular compass would be. But as soon as you start spinning those magnets, the attractive force to magnetic north goes up. I don't know if it's tenfold or it goes up quite a bit. That's something interesting.
So it amplifies its sensitivity to the North Pole, is what you're saying?
Yeah. If you watch the videos that I posted on YouTube, you gotta watch them carefully. You'll notice it swings there. When it's off, it's still. It's not facing north, even though the magnetic field strength didn't change. But when you turn it on, it's suddenly lines up with. It'll overswing a little bit and back and forth. But now I've seen this on several experiments.
How much is it? Does it oscillate around true north, or I mean, does it oscillate around magnetic north, or does it sit? Is it sit? It'll reach up.
It sits there as if it's just like a compass needle is attracted to magnetic north. It becomes a lot more attracted to the spectrum of ambient field strength. I once, in one experiment that happened after the SETI talk, it was live on Jeremy Reese's channel. It's like 2.5 hours in, we did an experiment with magnets that were pointing toward the North Star in line with Earth's spin, and it gained a couple grams of weight when it was spinning.
Did you do that? That's interesting. Very interesting.
And some of the experiments were done out of the Faraday cage, like the one where I call it the blue boob experiment because it sort of looked like a blue boob. It was covered so that we didn't get any airflow flowing, perturbing the test. But definitely saw an effect where it was moving toward in all the rooms. So we know where everything is, where we're oriented. Roughly that direction right now.
I have a question. They were talking about moon water, that if you put water in a bottle and expose it to sun rays, it creates bits of magnets in them. Isn't that like moon water? I mean, look, my kids, really, they do this for fun, moon water. They collect rainwater and they put it in this and they call it moon water because they think the moon's rays. But you guys were talking about the sun's rays. So if I take a bit of this stuff and I put it under a microscope, I'm going to see magnet bits. I mean, isn't that what they were talking about? One is in glass, one is in plastic. And these things have been sitting here for months. So I don't know if that would be enough time to see something under a microscope. But, magnet bits, water. Isn't that aligned with what you're talking about, Mark?
There you go.
I'm sorry, I wasn't really paying attention to that question.
Like weight gain. You expose it to something else and it gained 4 grams. Well, this water, it's exposed to sun rays, and according to the previous speakers, they said that it creates bits of magnets in it. Just regular, water. And wouldn't that be mass increase from the original?
I have idea. I've never heard experiment, but exposing water to sun rays, I mean, that would lead to tidal flooding if that was true. The oceans would change in mass if that was really true.
Yeah, but I have it. They have it like half court, so it's sealed, completely sealed. No, like really, really sealed. And you know, two different types of containers. One is glass, one is plastic. Like, see, one suctioning kind of happened. One still holds its form, its form. So, you know, I mean, it's just, you guys were talking about something that it just happened. It's there. Like, isn't that the same thing? Sun rays produce all sorts of rays. Well, two different kind of rays in an encapsulated container that's made out of H2O. Is that creating magnets? It's a magnet. Different rays that are, crossing through. This is just sitting in the backyard. It's been exposed.
Magnetism is spin orientation of valence electrons.
No, I was talking about creating matter, excess weight, just by different rays bombarding each other in a closed, seal to create matter. I mean, this is, I believe, is what we've been talking about at the beginning.
No, nobody's talking about making matter using sun rays.
Then I think you are misunderstanding the whole, what quantum physics is.
To look at your point most generously in light of our speakers, or the invited speakers, Bob Greene is most congruent with your argument because he's talking about ionization. They're not universally accepted, but he talked about a kind of a black hole phenomena where ionic matter is disappearing. And he talked about another phenomena where elements are being transmuted under bombardment by ions. If to try to simplify and state it, I could be a little bit off. But in light of your remark of sunlight can conduct in the UV portion. So it's not impossible, but I think that
I didn't say it. The previous speaker said it. I just want to clarify. I mean, you're telling me about Mr. Greene, but you guys just had a speaker that was talking about the exact thing that I'm just trying to tell you guys.
My mistake. I was just saying that the original speaker said something that kind of relates to what you said.
Sir, science doesn't have mistakes. It's experience. You learn. There's no mistakes. No mistakes. You just learn. That's the whole thing. How are we going to know? And so, I just want to put the whole idea together. And could we create matter, heavier elements, from lighter ones? The first abundant element.
About cold neutrinos, and cold neutrinos are stationary in space. So he mentioned that some reactors only work in the springtime or in a particular phase of the moon because the moon might drag cold neutrinos around, or there might be in a particular position in the solar system. So based on where these factors are on the Earth, they will only work at specific times because, as he said, there was a researcher that said he would only, when he took his reactor from one physical place in his lab to another physical place in his lab, it would start producing strange radiation. So it's not necessarily that it's being exposed to the moon or the sun. Is that the cold neutrinos are not present or they're still in that area.
Thank you.
Can I go back and talk for a second a little more about the nonlinear damping?
think it's open.
Yeah, so there was a guy who worked around Area 51 back in the 60s, and he wrote a bunch of books about his experiences in the 80s called Millennial Hospitality. His name was Charles Hall. One of the interesting things that he mentioned was he saw these, he called them tall whites, were the creatures. He said that they had tic-tac shaped things. He's writing about this in the 80s, way before the Nimitz incident. He's talking about tic-tacs. And at one point, he even got to see the insides of one of them. They were like working on it. And he said that they ended up having to bring in truckloads, like over 1,000 miles worth of fiber optic cable to be able to like rebuild their craft. The cool thing about that, whenever you're dealing with solitons, you're creating what's called surface acoustic waves. And these are basically the same thing that I was talking about earlier with the vibrations between the two phases of a metal. You can get similar type of vibrations happening on the surface of fiber optics. And it's much far higher frequencies than any of these mechanical magnetic spinning things we're working with. It can scale pretty well. That was basically what I was gonna talk about.
Didn't quite get your last two sentences. Could you rephrase them?
The gist of the whole thing was that a dude in the 80s talked about tic-tacs, the flying tic-tacs that he saw around Area 51 and the creatures that flew them. He said that they used 1,000 plus miles of fiber optic to rebuild one of them, and that he got to look behind the panels one time and see like the fiber optics and the magnetic coils around them. From some of the research that I've done, it sounds like solitons being fired, which are just solitary waves being fired through fiber optics. You get something called birefringence, which is like this back reflection of the light, and it's exchanging its energy between photons, the light, and phonons, the acoustic vibration. You're damping, like Woodward's mega drive, you can capture these phonons and you can capture their momentum, and you can have propulsionless or not propulsion in space without exhaust. It takes a whole lot of energy for being able to scale these together in a way that is actually able to like move your craft, but it's far less than like out-to-air drives or anything. It's orders of magnitude less. That's all I got.
Going back to what Lulu was first asking, saying what do we all have in common? And I took a very broad view of that outside of kind of the APEC community or engineering writ large at all, but just life. And because I've had the opportunity to teach teach biology recently, and I think of a definition of living things to give my students. And many people say, well, it's kind of an ill-defined term, life, but if we were to try to name some characteristics all living things seem to share, there's an underlying order, there's kind of a resource economy, you know, gathering resources, using them. And what I found was interesting is the point some more kind of mathematical sources gave was that they all living things exhibit a sensitivity to initial conditions. And some of us that have been in the math side will recognize this off the bat as the definition of mathematical chaos. So on one hand, you have cellular structure is kind of a predestined or predefined kind of order. Many people cite that you have, you know, the cellular architecture defines life. That's probably a pretty narrow definition considering all the different domains of living creatures, but there is an order with all living things. This is what was noticed in early attempts to model meteorological systems, and they found that if they took the same input data but just rounded it to 2 different decimal figures than a previous run of the simulator, you got drastically different results. It's called the butterfly effect, and that's even interesting in the poetry of this thought that, you know, that is characterized, in fact, by the presence of a living being that affects a system that is unimaginably huger than it so profoundly.
I've got something to say that's changing topic a little bit. It's asking about vibration of plates and the sono cavitation type machines. And he said that the vibration and the formation of cavitation is right on the plate surface. And we got into discussing how it'll be like a cymatic pattern right on that surface. And so there'll be like, imagine sound waves crossing each other. There'll be nodes and antinodes. The antinode where there's the most amplitude of motion of that metal, creating the cavitation, I guess, right there near the plate. I hadn't thought of that it is occurring so close to the plate. And I'm sharing this because I think we can now start thinking of what metals are even better than steel, and getting them to the right shape and the right frequencies to all be tuned to have the maximum amount of antinode spots available, that sort of thing. Throw that out there.
Casual inspection of some of these cymatic patterns reminds one of Penrose tilings and other kind of forbidden symmetries along the lines of quasi-crystals. To my understanding, that those minerals don't have particularly desirable kind of bulk qualities as far as like tensile or other strengths or anything. Symmetries that are very useful, right? Like icosahedrite, I think they've proposed some uses in the engineering domain for that. Also, one of our presenters was echoing my appreciation, or I should say, we both chimed on the perhaps a quasi-crystal structure to space-time itself. If you look at some of these cymatic patterns, the way that the waves spread in such a perfect yet quasi-periodic way is quite fascinating, and it seems like something that could be exhibited on a deep this levels. I don't know if anybody has thoughts.
There's been a couple good researchers out there on octonians. Coal Fury is one of the good ones. Tevi and Dre, another one, right? And the octonians are like the Lego pieces for string theory. If you want to build a 24, a leech as a 24-dimensional structure, you're going to have to use these 8-dimensional things to up to it. And these 8-dimensional octonians, all of these wonderful symmetries in them, but because they are mathematically like as simple as you can get, right? They're the non-divisible or non-associative and can't remember the other one. But yeah, without octonians, you can't build the universe.
They're not quite a field. What do they call it? Division algebra, right?
That's the one.
They're analogous to a field, but one of the operations is non-commutative. The multiplication is non-commutative. And for some reason, to me, that always seemed like it was still an algebraic field. But because we had that convention that it be multiplicatively commutative, we don't have that option. Algebraic structure is a very beautiful thing, but sometimes you want to get rid of algebraic structure. A lot of like Feynman integral type calculations are done just at the level of a semigroup, and you may not even have a inverse or anything to work with, much less. And while in your like coordinate space, you may have the structure of a field or whatever. Of course, you'll have a vector space or a module somewhere in there. At the levels, very kind of crudely in a sense, and you want to slap down some of the symmetry to give you more freedoms. This is my feeling on it. I'm not a physicist.
The alien woo side of things, I've heard them talk about ternary computing, and I've seen some papers out there that suggest octonians work very well for ternary computing. They're also extremely useful for optical processing, but that's going down the holographic theory, and I don't touch that with 29.5 foot pole.
You only need quaternions for plenty of advances in 3D, simplifying, working with 3D. I think octonians have their use definitely in physics. Cole Fury, really, that's an amazing contribution that she was able to make at such an early stage. What I understand is these were kind of forgotten theories that got a good start in the 70s. But be that as it may, even if that's the case, and that's just what I thought I remember hearing, Cole Fury's ideas are very, very attractive. There's a guy many years before, he was way more underground. He had graduated from MIT with a degree in biology, if I remember right, and he had a similar idea to Cole Fury's, and I think she's actually largely building on it. Not to say she read his work, but that the mathematical structure is an extension. So he had the quaternion part. This guy, Doug Sweetser, he's kind of cool to listen to on YouTube, but he's a lot less definitive than, say, Cole Fury. Cole Fury's got a bunch of great publications out of, what is it, Oxford or Cambridge? I think she's got at least 2 well-cited publications out, and it's got its detractors. I forget what they say the problem is, ultimately kind of an octonian field theory, but I think it's promising. Our speaker, were you here? I'm sorry, I'm going to call you whimsically ambitious. I know you did give your name, but did you hear the second speaker? He gave a bird's eye view of every you could do to general relativity in the case of just differential geometry. So we're not going to bring in too much weirdness outside of what happened. I mean, because you get Lie groups and stuff when you do that. So, then you get your algebra Lie symmetries. But beyond that, we're not going to bring in too much outside of just straight up like geometry, Riemannian, pseudo-Riemannian geometry, right? And that was a freaking of the subject, right? So I didn't even really appreciate that by always including torsion, like a lot of the folks that I read always did, or professors pointed me to stuff. That's actually Einstein-Cartan gravity, right? So I was always very interested in. And just in crudest terms, can somebody, if anybody can kind of confirm this, but like a lot of us are talking about in here about like gravitomagnetism. And for me, what that is like our presenter was talking about heavy side gravity, just naively proposing Maxwell type equations for gravity. And when you look at those laws, there's a solenoidal field and there's the vorticial field, right? There's one that has the one that has divergence conducts teachings as it just pulls. It doesn't really spin on stuff. Now you can get into your different connections and all that stuff when you want to get fancy with differential jump. Go ahead.
Have you seen some of the Rodin coils that are made where they have the magnetic sphere inside the hole of the torus of the coil, and then when they power it up, the magnet it both levitates and rotates? Because it sounds pretty much exactly like what you're talking about. That's all I had to say. Have you seen those? The Rodin coils where they're spinning the magnets and they're levitating and rotating?
I think that's where respecting that gravity might have a curl, right? Would lead to the development of these machines, perhaps, if you have strong enough magnetic fields. There's a podcast called Physics Frontiers, and just recently did a overview of some electromagnetic field ideas for but it is technical general relativity and gravity theory stuff. Sorry if you were trying to talk, Bernard. I think your speaker went out in and out, at least on my end. But yeah, so I posted in the chat that one of the things I heard in there was that the gravity measurement that, if I remember right, came out in a somethings, in the prior decade, that the gravitational electromagnetic field strength was about 10,000 times higher than predicted. Has actually been scientifically, I wouldn't even say debunked. I think that what they implied is that the authors recanted this. They said that there was present device. However, everyone agrees that these fields exist. All right. So while the magnitude of the strength of the GEM field is still kind of open territory to pin down exactly what it is, the fact that there's another field of gravity that hasn't fully been appreciated. I think Howard was his name, was asked, and there's likely to be some, even though it's a little subtle, because while there's not really a magneton, it's part of the field that gives rise to photons, right? But it's still
Hello everyone, this is Daniel Nunez from stuff. And today I'm going to demonstrate something pretty fascinating, or I think it's pretty fascinating.
About like
There's
quantum
a type
gravity,
of
are there any people
directional
that believe gravity
quality to the wireless transfer that we can achieve
ever be quantized? Where are we on
using
that? Are we some of us
PoE vortex or advanced 2.0?
there's like that general relativity is not right, or we're skeptic about moving clocks run slow, all of this. Like that would be interesting to know as a community, like where our physics kind of views are.
Hey John, could you spell Doug Switzer's name? Sweetser. Sweet, thanks.
Chime in. I watched one of those David Wilcock courses, and they had their insider named Beskar, Chris Beskar. He's the CEO of Didactic AeroSpace, and he was saying that for their invisibility shielding of craft, they were what would I say? They built a layer that would contain these spinning vortices of energy. It sounds like TiVos. And he implied that the same principle happens if you want to do anti-gravity. You just get these donuts that are squeezed together, and you contain them in a bilayer of stuff, and the magnetic energy that is gravity is just going to get sucked in and never come out, and then you're away from the effect.
So that's almost bringing in kind of the gauge part of quantum gravity they were talking about, that you basically found a situation where gravity eats itself. And not to say, one way or the other from my end, but that's kind of what I'm hearing, and something like that might not be impossible. I just heard on a related idea, I heard something kind of negative to that exact result, but about why the mass, why is it that black holes can still gravitate, right? If all the mass has fallen into a singularity on the other side of an event horizon, how does gravity escape from the black hole if not even light can escape? And furthermore, recent results have shown that gravitational radiation propagates at the speed of light. How is it that the black hole has any effective mass at all? And explanation is pretty. I don't know if folks have thoughts on that, but it's a pretty interesting thought experiment. I had done some calculations in fractal geometry that led me to believe that a gravitationally collapsed system of a low enough fractal dimension might actually disappear in this way or not gravitate. But I never got beyond kind of making an analogy.
It sounds like the quasi-crystal universe that we live in, it devolves into like a chaotic crystal once you get down to the too small or too high energy density level.
And of course, last time we were talking about the Big Rip and the false vacuum decay. Remy was bringing up. Yeah, it looks like Remy might not be in here now, but between the false vacuum decay and now there's a new Cuban Missile Crisis. So let's all try and cheer him up next time we see. Reese, Remy.
I'd like to add in one more thought is if you think about those spin rings of energy in water, we've heard discussions about how water molecule is preserved within that those water molecules, like in a 6 or a bigger thing with that. So that leads me to think you could probably achieve the same thing with different atoms in a bilayer, trilayer, a superconducting ring of energy to persist.
You were mentioning a toroidal structure in the EVOs. The other interesting thing about the concept of an EVO, I'm not, I can't I've thoroughly heard about just the idea of it is that you have this vacuum that is existing within condensed matter. Is this not the case, right? You're within water or air or laboratory substances.
Yeah, like, and it seems that it's always Wheeler Theory Hypothesis on YouTube does really good demonstrations of that with his ferrocells. And then if you guys have heard of Ed Leeds Scallon and his magnetic current, he also seems to show the same thing and works with his the flywheel. It's pretty interesting toroidal systems.
There's a pretty recent paper out from the Royal Astronomy Society in Britain on toroidal just orbits in celestial mechanics. I was talking last meeting about the kind of spirograph nature of the orbits of the planets when viewed from, say, a planet or the barycenter of the solar system or the barycenter between that planet and the sun. There's different coordinate systems that are used in a paper from the company, actually, PA Semi. It's, for some reason, it's on the archive, and the author is the legendary physicist Pa Semi, but that stands for Palo Alto Semiconductors. And because no one wanted their name on this paper, and you look at what do orbits really look like, right? Because sure, it's wise probably to tell kids that the center of the solar system really is the sun, but there really is no center. There's no preferred coordinate frame in the universe. You might as well center your spacecraft, basically yourself as the center coordinate. That's what's going to be. When you do this, the orbits of the planets look much different. And they look like the output of a game called a spirograph. And if you think, we were talking about quaternions and octonions, right? So if I think of that spirograph as drawing in the complex plane, and I wonder, what if these are traces of quaternionic it's down onto the two-dimensional plane, then those rosettes that are formed, all the different kinds of epicycles, and there's these different families of these figures we talked about last time, such as the hypotrochoids even, they will trace out the exterior of a torus. And if the so-called ratios are not rational between years, in an analogy to an actual etch-a-scare spirograph toy, that will actually fill out the space. So in relation to the Royal Astronomy paper, Royal Astronomical Society, they envisioned a cloud of gas and dust. They actually computed that will be the attractor for all of the gas and dust in a general accretion disk around the star will actually trace out the surface of a toroid. The interesting thing about applying the toroid here is that it's a topological product of two circles. So it's really just two cycles occurring rational ratio between them is. And this was shown. This has a lot of the regularities actually of a fractal set, the Cantor set. If you look at if you trace out a what is that called, a phase, that's actually the wrong word, phase diagrams in thermodynamics. If you make a phase portrait of a system on its toroidal orbit, you'll get a strange attractor, and a section on that strange attractor will be a Cantor set. And the mathematics of this Cantor set will you can demonstrate with a Dirichlet series. This Dirichlet series relates to a change of coordinates in along the imaginary axis at a given real value to a Fourier series that traces out the original orbit that
this is the bit, isn't it? That confuses me. It's like
if
we choose to come here to get this sorted out. Just seems a little unfair, doesn't it? That you know, where we seem to be here, and there's this parasite messing up our experience.
And you know, I know in my own life, the times that I've made major changes, it was like it became more painful not to change than to change. That was when I made big changes.
You know, it's this whole ridiculous narrative of it's, you know, it's an unsafe world. There's not enough for you. It's scary. Everyone's out to get you, and clearly the old civilization was completely the opposite to that. It was all about empowerment, like literally.
Cosmic resonance, I think they called that one. Or
Cosmic resonance. That's a better name.
Real science, you can actually produce free electricity, and this is part of what Tesla was doing, is the differential between the top of the spire to the ground actually creates an electrical differential that you then connect to another wire that goes into the ground, your grounding, put that into the third phase in your circuit, and then you have a bell ringing circuit, and that actually produces plasma electricity out of the air. It's real technology. These things actually function producing electricity. It's crazy.
The movies are the truth and the news is the lies. They've completely flipped it.
You know, when you look at everything with new eyes and you come across information like she was born into a very wealthy family with elite connections, you know, it means something very different now to me than it would have even a few years ago. And it's our free will that they've really also messed with, because we've been lied to and we react based on lies. And just getting their independence and end up in civil wars for 20, 30 years happens a lot.
Because we keep choosing to pick up the gun and use it on ourselves instead of building and uniting and accepting that we are one people, one spirit, one harmony, on one plane that together, united, can achieve anything we dream of.
So do you want to, you know, wake up, or do you want to just keep going along because the change is too difficult?
And then give them pieces of information that they will then pursue themselves and look into, and then they'll wake themselves up.
I was going to mention it's the whole red pill, blue pill of the Matrix. I mean, that of the movie. And you can consider that movie as a documentary. because they're telling us something about what's happening here. So do you want to, wake up, or do you want to just keep going along because the change is too difficult? Wake up.